Hey everyone, welcome to this deep dive into the world of machine translation. In this course, we'll trace the evolution of translation systems from the early days of rule-based methods and recurrent neural networks through attention-based models and Google's GNMT all the way to the transformers that power today's AI. But this isn't just a timeline of models. Together, we'll uncover why these breakthroughs happened, what problems they solved, and how each step reshaped the way machines understand human language. But here's the exciting thing. We'll replicate some of the most important academic papers in the field, from RNN encoder decoder and sec-to-sec models to attention mechanisms to large vocabulary neural machine translation and Google's GNMT. Whether you are new to deep learning or you are looking to take your skills a step further, this tutorial will guide you with clear explanations, visuals, hands-on code, and real-world insights. So grab your coffee and let's begin this journey. This journey not just transformed translation or machine translation, but also laid the foundations of modern AI. Welcome everyone to the RNN and Machine Translation and Neural Machine Translation Atlas. In this atlas, we're going through a deep exploration of the fascinating world of neural machine translation and sequence models. Over the next several hours, we're not just going to go through a skim the surface. We're embarking on a journey across decades of research, breakthroughs, and hands-on replications of the most influential papers in AI. We'll start at the roots with vanilla RNNs, LSTMs, long short-term memories, and GRUs, gated recurrent unit, and then progress step by step through the landmark innovations that reshaped how machines learn to understand and translate language, from Chou's RNN encoder decoder to Sutskever's legendary sequence-to-sequence models and Bahdanau's breakthrough attention mechanism and Luong's refined attention variants, all the way to the massive leap of Google's GNMT revolution, which is the multilingual neural machine translation with zero-shot translation, and ultimately the transformer revolution. And we won't stop there. We'll also unpack the architectures behind GPT and BERT and explore modern interactive tools like the Transformer Playground to see how attention really works under the hood. But here's the best part. This is not just theory. This is not just history. For every major milestone, we'll replicate the original papers in PyTorch. That means you'll see real code translating from one language into another language, real training loops, real evaluations, and real results, exactly as researchers did, but in a way that's clear, approachable, and accessible, and also hands-on. If you've ever wondered, how did neural networks actually learn to translate human language? Why was attention such a breakthrough? How do transformers power today's GPTs, BERT, and beyond? Then this tutorial is your roadmap. So get comfortable, set aside distractions, and prepare for a 6-hour masterclass in the evolution of sequence learning and machine translation. By the end, you'll not only understand the history, you'll have it built in, step by step, with your own hands. Let's begin the journey. In this section, let's discuss the evolution and the evolving of RNNs, recurrent neural networks. Recurrent neural networks, RNNs, didn't appear out of nowhere. They have a long history that started with ideas from neuroscience and slowly evolved into the powerful models we use today. Early inspirations. Before modern RNNs, in 1901, Santiago Cajal noticed recurrent loops in the brain's cerebellum. By 1933, Raphael Laurenti Deneau described reciprocal connections in the nervous system. In 1943, McCulloch and Pitts created the first neuron model that allowed cycles, showing that signals could loop back. In 1949, Donald Hebb suggested reverberating circuits as an explanation for short-term memory. During the 1960s, Frank Rosenblatt designed cross-coupled perceptrons that used feedback and Hebbian learning. The 1970s brought more experiments. Nakano, 1971, Amari, 1972, and Little 1974 all proposed recurrent style models. In 1975, Sherrington and Kirkpatrick's spin glass model inspired Hopfield's later work. John Hopfield then created the famous Hopfield network in 1981 binary and 1984 continuous, a kind of associative memory system. Then we moved on to the modern RNN era. In 1986, Michael Jordan proposed the Jordan network, which fed context from the output layer. In 1990, Jeffrey Ellman introduced the Ellman network using hidden sets as memory. In 1993, Jürgen Schmidhuber built the neural history compressor, solving tasks that required very deep recurrence. The real breakthrough came in 1995 when Sepp Hochreiter and Schmidhuber invented the long short-term memory LSTM algorithm, fixing the vanishing gradient problem. Through the late 1990s and 2000s, LSTM became the default RNN choice. In 1997, Schuster and Paliwell introduced the bidirectional RNN, BRNN, which looked at sequences from both directions, forward and backward. From 2006 onward, stacked bidirectional LSTMs transformed speech recognition, translation, and even image captioning. In 2014, Kyung-Yeon Cho and colleagues introduced the GRU, a simpler alternative to LSTM. That same year, Sutskever, Vinyals, and Cook-Vealy created the sequence-to-sequence model, laying the foundation for attention mechanisms. Between 2015 and 2017, attention-based RNNs became the bridge to the transformer era. In 2018, Peters and colleagues released ELMO, a model based on deep bidirectional LSTMs that created powerful word embeddings. Specialized variants and extensions, we have Hopfield networks, 1982, associative memory models. Costco, 1988, introduced bidirectional associative memory, BAM, BAM. And also we have Jaeger and Haas proposed echo state networks with random reservoirs. Sorsa developed recursive neural networks for NLP structures. Graves et al., 2014, created the Neural Turing Machine, NTM, combining RNNs with external memory. Graves et al., 2016, extended it to the Differentiable Neural Computer, DNC. From 2018 onward, variants like Pixel RNN, IND RNN, HRNN, and MTRNN explored spatial, hierarchical, and multi-time scale modeling. RNNs grew from simple neuroscience observations into powerful AI models. They moved from early feedback loops and associative memory to Jordan Ellman's context models to LSTM and bidirectional RNN breakthroughs to GRU and sec-to-sec, and finally into attention-based architectures like ELMO. These innovations paved the way for today's transformers. Let's talk now about the evolution of machine translation at a general level. First, we started with rule-based machine translation that relied on dictionaries and handwritten grammar rules, worked well for controlled domains, but was brittle, labor-intensive, and poor at handling real-world language diversity. Then we moved on to statistical machine translation from 1990s until 2010s. Shift to data-driven methods, learning from large parallel corpora, used phrase tables and probabilistic alignments. So statistical machine translation relied on probabilistic alignments, provided better fluency than rule-based machine translation, but struggled with rare words and long-range dependencies. So we had a problem with statistical machine translation is that it struggled with rare words, unseen words, and long-range dependencies. Third, we moved on to neural machine translation, early RNN models. RNN is a specialized form of neural networks and is short for recurrent neural networks. Encoder-decoder architectures by Kyung-Yeon Cho et al., Sutskever et al. Replaced phrase tables. For the first time, translation was modeled end-to-end with neural networks. So this is the first time that translation was modeled end-to-end from start to end with neural networks, with pure neural networks. These handled variable length sequences, but were bottlenecked by compressing everything into a single vector. So here we were able to model variable length sequences. We were able to input a variable length input sequence and then generate a variable length output sequence, but it was bottlenecked by compressing everything into a single vector. Fourth, we have attention mechanisms. So these mechanisms allowed for dynamic input sequence length and output sequence length. Bahdanau et al. Introduced soft attention to allow models to focus on relevant parts of the source sentence. Then we have Luong et al., this paper, refined attention, global, local input feeding. This improved translation of long sentences and rare words, while also providing more interpretable alignments. So here the most important idea is that they introduced attention mechanisms that allowed models to focus on relevant parts, to focus on the most essential parts. Then we have scaling neural machine translation, scaling to large-scale models, like Google's GNMT. GNMT is short for Google Neural Machine Translation, added deep stacked LSTMs. LSTM is short for long short-term memory, word piece tokenization, parallelism, and production optimization. Reduced translation errors by 60%, by roughly 60% compared to phrase-based machine translation, bringing neural machine translation into real-world deployment. So here we have introduced the neural machine translation era into real-world deployment. Also, we moved on to transformer era, 2017. Today, Vaswani et al.'s attention is all you need paper replaced recurrence and also convolution with self-attention. So rather than using attention within recurrence mechanisms or within convolution mechanisms, we now need to just use self-attention as a standalone technique. Faster, more scalable, and better at capturing long-range dependencies became the foundation for modern large-scale translation and pre-trained language models such as BERT, GPT, and BERT, and NLLB. And NLB is a large project, and it is short for No Language Left Behind. It supports 200 and plus languages worldwide. Also, we have here modern, multilingual, and self-supervised machine translation, 2018 and until today. Pre-trained multilingual models like BERT, MT5, NLLB, No Language Left Behind 200, handle 100 and plus languages. So 100 and plus languages. Enabled zero-shot and few-shot translation, shifted the field toward self-supervised learning and massive pre-training on both parallel and monolingual data. Summary: translation has evolved. Translation has evolved over years from handcrafted rules, statistical co-occurrence, to neural encoder-decoder, to attention mechanisms, to transformer architecture, and multilingual pre-training. Each step reduced reliance on manual design. Each step reduced reliance on human involvement, improved fluency and context handling, and scaled toward today's large general-purpose language models that translate with near human quality. So this was a quick overview, a quick and general overview of the different stages of the machine translation field in artificial intelligence AI. Let's dive into machine translation techniques and compare between the most important phases: rule-based machine translation, statistical-based machine translation, and neural-based machine translation through various aspects. The first aspect is core approach. What is the core approach of rule-based machine translation? Hand-coded linguistic rules and bilingual dictionaries. So rule-based depends on bilingual dictionaries, while statistical machine translation used probabilistic models trained on parallel corpora. Neural machine translation depends on deep learning with encoder decoder neural architectures. Data dependency. Rule-based machine translation depends on data in a low level, relies more on expert linguistic knowledge, relies more on expert knowledge of the linguistic knowledge. While statistical machine translation, high. It really depends on data. The dependency of data in statistical machine translation is high, requires large aligned corpora, while in neural machine translation is very, very high, massive parallel corpora plus monolingual corpora for fine-tuning, especially in transformer-based neural machine translation. So we can conclude that data dependency in rule-based was low. It relied heavily more on expert linguistic knowledge. In statistical machine translation, the level of dependency on data is high because statistical relies on data, requires large aligned corpora, and also neural machine translation is of high importance. Data dependency is of high level, very high. Massive parallel corpora plus monolingual corpora for fine-tuning. From the context handling perspective, rule-based machine translation is poor, translates word by word or phrase by phrase, while statistical machine translation is limited. So context handling in statistical is limited. It depends on n-gram context, typically up to 5 grams. In neural machine translation is very strong. So context handling in neural machine translation based is very strong and very high. Full sentence or even document level context with attention mechanisms, thanks to attention mechanisms. Also, we have fluency of output. In rule-based machine translation, it's low to medium, grammar focused but often unnatural. In statistical machine translation, the fluency of output is medium. Statistical alignment may yield awkward phrasing, so you may see awkward translations or awkward phrasing in statistical machine translation. Why? Because the fluency of output is medium, while in neural machine translation it's high, very high. Natural and human-like outputs, better semantic coherence. So with neural machine translation era, we have better semantic coherence. And also for the linguistic generalization, rule-based machine translation is high. So it has a high level of linguistic generalization. Rule sets can apply across domains, assuming good design. In statistical machine translation, it's poor. So the linguistic generalization in statistical based models is poor, heavily corpus dependent. So it depends heavily on large scale corpus. In neural machine translation, it's medium to high. Good generalization when pre-trained on large multilingual corpora. And also for handling rare words, for example, out of vocabulary terms, if you see OOV, OOV is an important token in the world of NLP, natural language processing. It's out of vocabulary. For rule-based domain, poor and less explicitly covered in rules or dictionaries. So what is the level of the possibility that rule-based machine translation can deal with out of vocabulary terms? It's poor and less explicitly covered in rules or dictionaries. In statistical machine translation, poor and less seen in trained data. In neural machine translation, improved with subword units. For example, byte per encoding system. So handling rare words, it improved over the phases. First, we have poor and less explicitly covered in rules, and in statistical machine translation, it's poor and less seen in trained data, and in neural machine translation, it's improved with subword units. Support for morphologically rich languages. In rule-based systems, it's strong, can encode morphological rules explicitly. In statistical machine translation, it's weak, suffers in morphologically complex languages, while in neural machine translation, it's medium to strong, improves with morph-aware tokenization and pre-training. Interpretability. So how interpretable is each phase? In rule-based, we have high interpretability, transparent rules. Because we have transparent, well-defined rules, the interpretability ratio is high. While in statistical machine translation, it's medium. Alignments are partially interpretable. In neural networks, it's low, black box nature of deep models. So black box is that we don't necessarily know how these deep learning models reach the performance that they reach. So here we have interpretability. For rule-based models, it's very high because it's based on transparent rules, well-defined rules, while in statistical machine translation, it's considered medium level. Why? Alignments are partially interpretable, while in neural networks, it's very low, black box nature of deep models. We have also customization and domain adaptability. So how adaptable is each phase for different domains? For rule-based, it's high. Domain rules can be handcrafted. While in statistical machine translation, it's medium, requires domain-specific corpora. So if you want to specialize a specific statistical model to a specific field, then it requires domain-specific corpora. While in neural machine translation, it's very high via transfer learning, fine-tuning, prompt engineering. So transfer learning is leveraging a model's pre-learned patterns or a model's pre-trained weights to your own specific task. And also we have computational cost. So the computational cost for rule-based models is low to medium, CPU friendly. So rule-based systems are CPU friendly. You can train a rule-based model using a CPU device, while in statistical-based machine translation, it's medium. Depends on data volume and alignment processing. And in neural era, the dependency on GPUs is high. High GPU accelerated training and inference. Real-time translation capability. For rule-based, it's feasible with limited vocabulary and rules. But for statistical, feasible but limited by decoding speed. And for the neural era, here now feasible with optimized architectures. For example, transformers, quantization, beam search tricks. Some examples for rule-based systems like Systran, Apertium, and some examples for statistical-based models like Moses, Open Source SMT, Statistical Machine Translation Toolkit, and also IBM Model Series. And for neural-based models, we have Google Translate, Post 2016, DeepL, also Open Neural Machine Translation, Facebook FairSig, and also Meridian NMT. Model size. So what is the size of the model? How big is the model? The rule-based models are small. Depends on rule complexity because it has a set of predefined rules, and this is the model. So it's a small model. But for statistical machine translation, it's medium. The size here is medium. Phrase tables can be large. And for neural machine translation, large to very large, we have, for example, GPT-4, BERT, MT5, NLLB, Llama models with billions of parameters, with billions and trillions of parameters. Training requirements. So what are the requirements, the prerequisites for each of these phases? For rule-based, no training, just hand-coded. And for statistical-based models, requires word phrase alignment, corpus cleaning, language modeling. So you need to do some pre-processing here, like corpus cleaning, language modeling. And for neural era, requires parallel corpora, GPUs or TPUs, potentially days of training. And recent advances for rule-based models, here we have mostly static legacy. For statistical machine translation, suppressed by NMT, neural machine translation. And for neural machine translation, transformer-based models, multilingual NMT, zero-shot translation, and massively multilingual pre-training. And here we have main academic limitation. The main limitation and the main limit of the rule-based system is that lack of scalability and language coverage. It cannot model the real diversity or the real world diversity of a language. While statistical machine translation, limited context window, phrase alignment errors, and for neural, lack of interpretability. And as we said, what is the interpretability level for each phase? we said that the rule-based is very interpretable, high interpretable, because you as the rule writer, you can define whatever set of rules you want. So transparent rules, well-defined rules. But for statistical machine translation, the interpretability level is medium. Alignments are partially interpretable, so you can still interpret the alignments. But for neural machine translation, it's very low. You cannot interpret how a neural network reach a predetermined performance. So black box nature of deep models. You don't, as we said, you don't necessarily know how your neural network reach this performance. And this is the concept of black box model. And here we have lack of interpretability, high training cost, data bias risks. So we have the risk of data bias, because the data here is the dependency of data here is really high, while in rule based it depends on your rules, on your predefined rules. So this was the main aspects to compare between the different phases and compare between the different eras of machine translation: rule-based, statistical-based, and neural-based. Let's discuss long short-term memory paper by Hochreiter and Schmidhuber, 1997. The paper introduces long short-term memory, LSTM, a novel recurrent neural network architecture designed to overcome the vanishing and exploding gradient problems in training RNNs. LSTM enforces constant error flow through constant error carousels, CECs, regulated by multiplicative input and output gates. This design enables learning long-term dependencies spanning more than 1,000 time steps. Experiments show that LSTM significantly outperforms backpropagation through time, BPTT, real-time recurrent learning, RTRL, and other recurrent methods on long time lag sequence tasks. What are the problems that they faced? Problems addressed. Number 1, vanishing gradients. Error signals decay exponentially, preventing long-term credit assignment. 2, exploding gradients. Error signals grow uncontrollably, destabilizing training. Number 3, conflicting updates. Naive constant error flow units suffered from contradictory weight signals. Number 4, prior methods like PPTT, backpropagation through time, and the others failed on long time lag problems more than 100 steps. What are the solutions that they proposed and they used to solve these problems? Number 1, constant error carousel, CEC, linear self-connected units, weight equals 1, preserve error indefinitely. Second, input and output gates. Multiplicative gates control when information is written or read from memory. Third, memory cells and blocks, encapsulating CECs and gates from scalable to form scalable recurrent building blocks. Number 4, truncated error flow, gradient flow indefinitely inside cells but truncates on exit for stability. Fifth, bias and construction strategies prevent abuse or over-reliance on memory units. What are the purposes of this paper? Number 1, create an RNN architecture capable of learning long-term dependencies over thousands of time steps. So the traditional RNN suffered from handling or modeling or capturing dependencies from long-term dependencies. It quickly forgets what it learned earlier. So they proposed a new architecture, a brand new architecture called LSTM, long short-term memory, that can capture or model long-term dependencies without forgetting what it learned earlier. Second, demonstrate feasibility of stable gradient-based training in recurrent systems. Third, solve benchmark sequence tasks unsolvable by previous algorithms. So they solved benchmark sequence tasks unsolvable by previous algorithms. You can't get them solved without LSM. Methodology. First, architecture. We have input layer that receives inputs. Then we have hidden layer of memory cells with gates. We have the gating mechanism, and then we have output layer. and then fully recurrent hidden layer. Training, online learning, logistic sigmoid activations. They employed and leveraged logistic sigmoid activations for gating mechanisms, specific ranges for G, H, and gates, truncated BPTT. Third, complexity. O of W per time step, same as PPTT, more efficient, but more efficient than RTRL, real-time recurrent learning. Experiments. First, embedded REBA grammar recognition. Second, noisy clean sequence tasks with lags up to 1000 steps. Third, Bengeo's two-sequence classification with noise. Fourth, continuous value problems, adding and multiplication tasks. Fifth, sequence order tasks. What are the results of the paper? First, REBA grammar. LSTM succeeded, unlike RTRL, LMAN nets, or RCC. Second, long lag tasks, land dependencies over 1000 plus steps. PPTT, RTRL failed beyond about 10. Third, noise robustness, handled noisy signals where others collapsed. So the ability of LSM to handle noisy signals, to handle noisy gradients with where others collapsed and failed. Fourth, adding multiplication, land precise continuous value storage and computation. And fifth, scaling, training time grew slowly with sequence length, no exponential blow up. Then what are the conclusions? Number one, LSTM eliminates vanishing gradients via constant error flow and gated memory. Number two, it solved tasks no other recurrent algorithm could handle at the time. Third, output gates proved crucial to separate long-term memory from short-term noise. Fourth, generalized well to noisy, real-valued and distributed input sequences. Fifth, remaining limitations, potential abuse of memory cells addressed via bias strategies. This paper marked a foundational breakthrough in sequence learning by introducing explicit and gated memory. Hochreiter and Schmidhuber transformed RNNs from unstable tools into powerful temporal models capable of modeling long-range dependencies or long-lag dependencies. LSTM became the basis for advances in speech recognition, language modeling, and deep learning architectures that dominate modern NLP and AI. And since then, LSTM became the default RNN. And here we have the paper. You are more than welcome to explore it in your free time. Here we have the images of Sepp Hochreiter and Jürgen Schmidhuber. Introduced gated memory cells, CEC, input-output gates, enabling RNNs to learn dependencies across 1000 plus time steps, a milestone in solving the vanishing gradient problem and foundational to modern sequence models. By stabilizing error flow with memory cells and gates, LSTM solved the long-term dependency problem that crippled earlier RNNs, reshaping the future of deep learning. And here we have the paper. Feel free to explore it in your free time. So now we have finished discussing this paper, long short-term memory, that solved the problem of traditional RNNs and became capable of modeling long-range dependencies. Let's dive now into neural machine translation by introducing a series of very significant papers. The first paper we're going to discuss is learning phrase representations using RNN encoder decoder for statistical machine translation. This paper was introduced by Kyung-Yeon Cho et al. In 2014. Abstract. This paper introduces a novel RNN encoder-decoder architecture for sequence-to-sequence learning. So they introduced a new paradigm, a new framework, encoder-decoder architecture for sequence-to-sequence learning, applied within statistical machine translation, SMT. The model consists of two recurrent neural networks, an encoder that maps a variable length source phrase into a fixed length vector. So first we start with an encoder that maps an input sequence into a fixed length vector. It takes or receives a variable length input sequence and maps it into a fixed length vector. And a decoder that generates a target phrase conditioned on this vector, based on this vector. The model is trained to maximize the conditional probability of a target sequence given a source sequence. So you may wonder, why do we need conditional probability? Why? We are now modeling language, and in language we need context. We need to build coherent context. So we need to generate a token or generate a target sequence based on or conditioned on a vector. Empirical results show that using RNN encoder decoder scores as additional features in phrase-based SMT improves translation performance. Furthermore, the model learns semantically and syntactically meaningful representations of phrases. Problems addressed. What are the problems that they faced? Well, the first problem, phrase-based SMT relies heavily on co-occurrence statistics, which often fail for rare or unseen phrases. So statistical-based approaches rely heavily on co-occurrence, and in another word, frequency statistics, which often fail for rare or unseen phrases. The second problem is that traditional neural approaches, for example, feed-forward nets, require fixed size inputs and outputs, making them unsuitable for variable length sequences. And in languages, we need to model variable length sequences. Existing statistical machine transition models cannot effectively capture linguistic regularities or exploit sequence order beyond surface frequency counts. So these are the three problems that they faced, and they addressed these problems. They tried to solve these problems using this proposed solution. The first solution is introduce the RNN encoder-decoder paradigm or encoder-decoder framework. Encoder RNN compresses a variable length input sequence into a fixed length vector. So the idea is we are turning a variable length input sequence into a fixed length vector. And here, decoder RNN generates the target sequence conditioned on this vector. So depending on this vector, based on this vector, we generate. Second, propose a novel hidden unit with reset and update gates, a precursor to GRU. GRU is short for gated recurrent unit. And GRU is a simplified version of LSTM. GRU is a small version of LSTM. It has just two gates, reset and update gates, rather than 3 gates, enabling adaptive remembering and forgetting of context information. Third solution, use the RNN encoder-decoder to score phrase pairs in SMT phrase tables, integrating these scores into the log linear model of a standard SMT system. So these are the proposed solutions. In a short version, they introduced the RNN encoder-decoder. They introduced or proposed a novel hidden unit called GRU. They used RNN encoder-decoder to score phrase pairs in SMT phrase tables, integrating these scores into the log linear model of a standard SMT statistical machine transition system. So they integrated between this RNN encoder-decoder and SMT system, statistical machine transition. Purpose: to improve phrase-based SMT by providing better probability estimates for phrase pairs, to show that RNN-based models can learn continuous space representations of phrases that encode both semantic and syntactic properties, to demonstrate that neural sequence models can generalize beyond frequency statistics and yield better translation performance. Methodology. So what is the methodology they used or they leveraged to build this architecture? Well, the architecture is based on encoder. RNN reads source sequence. Think of the encoder as a reader that reads the input sequence and maps it into a fixed length vector. So reads source sequence, and the source sequence is the input sequence, and produces final hidden state that represents source phrase. So the encoder tries to understand the dependencies, the correlations, the relationships and produces a final hidden state represents source phrase. Then we have a decoder RNN that generates target sequence, but keep in mind, conditioned on encoder, based on encoder vector and previously generated tokens. 3. Training objective. What is the main objective of the training process? Is to maximize log likelihood of a target sequences given sources. In machine learning and in deep learning, every single model has an objective, has a training objective. Well, for example, in a regression problem or in a regression model, the objective is to decrease the loss function, which is typically mean squared error or mean absolute error. And in classification, we have another loss function, which is cross entropy loss, or for binary classification, binary cross entropy. And the main objective is to reduce that cross entropy loss. And here, when we model the language, or when we build a language model, for example in NLP, natural language processing, well, the training objective is to maximize log likelihood of a target sequence given sources. Experiments. Task. The task they try to solve is English-French translation, WMT 14 dataset. Baseline. What baseline did they compare their proposed model to? Well, it was Moses phrase-based SMT system. The BLEU score is 33.3. BLEU is a score that scores or evaluates a machine transition model, and it's short for Bilingual Evaluation Under Study. Enhancements tested. Baseline plus RNN encoder decoder, and also they conducted a study or an experiment of baseline plus neural language model, CSLM, and also they conducted an experiment of combined baseline plus CSLM plus RNN encoder decoder. So here we have 3 experiments. Training. They used a vocabulary set limited to 15,000 most frequent words. Model trained with Ada Delta optimization. And Ada Delta optimization was introduced in 2012 by Matthew D. Zayla, New York University. Embeddings visualized with Barney's Hut SNE for quantitative evaluation. Results? Well, BLEU score improvements. Baseline SMT 33.30, RNN encoder decoder 33.87, and CSLM plus RNN is 34.64 best. So the best experiment is this experiment. When they combined the CSLM plus RNN, they had a blue score of 34.64. Quantitative analysis shows RNN encoder decoder captures beta linguistic regularities, especially for long or rare phrases, compared to statistical machine transition probabilities. Learned embeddings for words and phrases cluster semantically and syntactically similar items together. So the algorithm here is able to cluster the words or the phrases that are semantically and syntactically similar to each other. Conclusions. The RNN encoder decoder successfully learns meaningful phrase representations, improving statistical machine transition performance. It complements existing neural models, for example CSLM, with improvements being orthogonal rather than redundant. The proposed architecture shows strong potential beyond SMT as a general method for learning sequence-to-sequence mappings. Future directions include replacing phrase tables entirely with neural-based models and extending applications to speech and other sequence tasks. This work marked a paradigm shift in machine translation, proving that phrase representations need not be handcrafted or solely frequency-based. So this paper tells us that you don't need phrase tables. You don't need handcrafted ways to be able to model language. You need an RNN encoder and decoder paradigm. The encoder takes or receives an input sequence, typically a variable length input sequence, and maps it into a fixed length vector. Then we pass this fixed length vector, this high rich representation vector, into the decoder. The decoder then takes this vector and say, thank you encoder, I will take this vector and based on it, conditioned on it, I will try to generate a variable length output sequence. by showing that neural sequence models can learn continuous space semantic and syntactic representations. It opened the way for modern neural machine transition and attention-based architectures that followed. And here we have the authors of the paper, Kyung-Yeon Cho, and also we have Dimitri Bahdanau with Yeshua Bengio, and also Bart van Marnborn. Seminal paper introducing gated RNNs. So they introduced the gated RNNs units, precursor to GRUs, gated recurrent units, and neural phrase representations. This paper, in short, introduced the RNN encoder-decoder architecture with reset and update gates, capable of learning phrase-level semantics and syntax. It demonstrated how neural models could complement and improve phrase-based SMT, laying the groundwork for end-to-end neural machine transition. And here you can see the paper. If you view in line, it will show up a pop-up with the paper. The paper is called Learning Phrase Representations Using RNN Encoder-Decoder for Statistical Machine Transition. And here the main idea is that they said here, in this paper we propose a novel neural network model called RNN Encoder-Decoder that consists of two recurrent neural networks. So you have two recurrent neural networks. The first the first RNN encodes a sequence of symbols into a fixed length vector representation, and the other decodes the representation into another sequence of symbols. The encoder and decoder of the proposed model are jointly trained to maximize the conditional probability of a target sequence. So they stated here clearly, they stated that to maximize the conditional probability of a target sequence, as we said, given a source sequence, the performance of a statistical machine transition system is empirically found to improve by using the conditional probabilities of phrase pairs computed by the RNN encoder-decoder as an additional feature in the existing log linear model. Quantitatively, we show that the proposed model learns a semantically and syntactically meaningful representations of linguistic phrases. And also, if we scroll down here, the idea here is like that. If we scroll down to the hidden unit here, hidden unit that adaptively remembers and forgets, in addition to a novel model architecture, as we said, they introduced three important things. The first thing, they introduced a novel architecture. But also, in addition to a novel model architecture, we also propose a new type of hidden unit, F in equation 1, that has been motivated by the LSTM long short-term memory unit, but is much simpler, which is GRU. GRU is a much simpler version, is a much simplified version of LSTM to compute and implement. Figure 2 shows the graphical depiction of the proposed hidden unit. Here we have this equation. As you can see, we have this logistic sigmoid function that decides whether to keep this information or to pass. And as you can see, we have the W, which is a weight matrix, and also U. So W and U are weight matrices which are learned. They are learned values. They are learned during the backpropagation and gradient descent optimization. And X and hidden state are, X is the new or the current time step, and H refers to the previous hidden state. So here, where this function, this symbol, is the logistic sigmoid function, and this jth denotes the jth element of a vector. X and H, now focus, X and H here are the input and the previous hidden state. So X represents the input, H represents the previous hidden state. The hidden state is the memory of the RNN that stores the previously learned information or representation, respectively. W and U are weight matrices which are learned. Similarly, the update gate Z is computed by this equation. The actual activation of the proposed unit H is then computed by this equation. And feel free to explore, to experiment with these equations and to read more on it. Here we have also a section on statistical machine translation. You can read in a commonly used statistical machine translation system, SMT, the goal of the system decoder specifically is to find a translation F given a source sentence E, which maximizes this conditional probability. We have P, which is the probability. So the probability of P, the probability of this generated sequence or this generated translation F given or based on or conditioned on E. E, which is what? A source sentence E, which maximizes this. So I think now we have covered enough of this paper. Feel free to experiment, to explore, to read more on this paper in your own time. I'll let you read it in your free time. You can see we have nice figures, RNN scores, and also we have here the quantitative analysis section. As you can see, we tried the following combinations: baseline configuration. So the baseline, what is the MOSIS system? MOSIS system, statistical machine translation. Then we have baseline plus RNN. Then we have baseline plus CSLM plus RNN. And also baseline plus CSLM plus RNN plus word penalty. And also here we have nice tables, as you can see. And here they visualized the vector representations, or the words embedding of the land word representation. The left one shows the full embedding space. So this is the embedding space, the space of the embeddings, while the right one shows a zoomed in view of one region, color coded. So you can see here we have Germany is near Ontario, and we have here Iraq, Japan, North British. As you can see, these are the vector representations. And we have more visualizations, and as you can see, this is the paper. So now we have discussed enough about the first paper. This paper is called Learning Phrase Representations using RNN Encoder Decoder for Statistical Machine Translation. And as we said, they introduced the encoder decoder paradigm that shifted the way we process language. In this section, we will replicate the paper Learning Phrase Representations using RNN Encoder Decoder for Statistical Machine Translation. This paper was introduced by Cho et al. This paper introduces a novel RNN encoder decoder architecture designed to learn fixed length vector representations of variable length phrases with the goal of improving phrase-based statistical machine translation SMT. So let's dive into discussing the code. Before building any model, we have to import the necessary libraries. So before building the sec-to-sec model, the necessary Python libraries are imported. First, we begin by import torch. It gives us tensors and allows us to apply auto gradient and the deep learning core. Then we have import torch.nn as nn, provides neural network building blocks like embedding layer, GRU layer, and linear layer. Import torch.nn as .f.functional as f contains extra functions, for example activation functions, loss functions, and etc. Then we have the utilities for data, for example from torch.utils.data, import dataset, data loader, allows creating custom datasets, sec-to-sec dataset, and batching with loaders. Then we have the scientific libraries for scientific computing, for example import numpy as np, numerical operations, though not heavily used in this demo. Then we have import random, used for random teacher forcing decision, whether to use true token or the predicted one. Then for visualization and making visually aesthetic plots, let's import matplotlib.pyplot as plt, included for plotting visualization. And then let's dive into the next section, which is creating the toy dataset. So this dataset is a dataset mimicking the WMT dataset, but it's a small one. It's a small scale. We have a toy parallel corpus. A tiny dataset is created with English to French pairs. For example, you can see here we have a dictionary that contains padding mapped to 0. Then we have E, we have SOS, which is start of sequence. Then we have EOS, which is end of sequence. This mimics what happens in real translation datasets, for example WMT, but here it's super small, so training is quick. And also here we have two vocabularies. We have source vocabulary and target vocabulary. You can see we have the word or the words I like dogs mapped into the French version whatever it was. Then we have I like cats mapped into the French version. You can see, as you can see, we have JME less cats. Then we have a dataset class. This dataset class is named, as you can see, sec to sec dataset, and we inherit from the dataset class from PyTorch. This is a dataset class in PyTorch, the base dataset class in the library PyTorch. Prepares sequences by adding SOS at the start, so we add the sentence of the start of sequence as a starting point, adding EOS at the end, and also converting word indices into indices. This ensures inputs and targets are ready for the model. So as you can see, this is the main functionality of this class, which is converting words into indices and adding the special token SOS at the start and adding the EOS token at the end. Then we have an encoder class. The encoder class uses an embedding layer, maps word indices into dense vectors, passes embeddings into a GRU layer. The GRU layer applies, as we discussed, the gating mechanism, which is the reset gate and the update gate behind the scenes. This will be all done behind the scenes because this is a class inside the PyTorch library. Then it retains only the final hidden state, which you can see here, the final hidden state context vector, which summarizes the source sentence. So this is the core idea in the paper Cho et al., which is compresses the input sentence into a fixed size vector. Then we have a decoder. As you can see here, the encoder, by the way, inherits from NN.module. This is the base module class in PyTorch that if you inherit from, this class will be able to be trained, will be able to have the ability to be trained and to be optimized. And you can see in the init method here, we define the set of the layers that will be used later. Whereas in the forward method, here we call these layers and execute them. When we train the model later, it will be executed the same order that we define into here. Then we have a decoder class. You can see the decoder class here also has an embedding layer, uses a GRU that takes previous token, teacher forcing, or predicted, and also takes a hidden state from the encoder or last decoder state, then predicts next word with a linear layer. The linear layer projecting GRU output to vocabulary size, to vocabulary space. This models one word at a time, decoding. So the decoder, in short, has an embedding layer to map these vectors into an embedding vector. Then we have a previous token, which is teacher forcing or predicted. Then we have a hidden state from the encoder or last decoder state. Then it predicts next word with a linear layer that projects the GRU output to a vocabulary space. The same idea, the decoder inherits from the module class, and you can see here the init, we pass into here the output dimension, the embedding dimension, and the hidden dimension. These are all hyperparameters you can fine tune and try the best values. Try until you find the best values. And in the forward method here, we define the way of executing these layers. Then after this class, we have a sec-to-sec model, wraps encoder plus decoder, combines the encoder and the decoder. Here in this sec-to-sec model, we initialize the init method and then pass the encoder, decoder, and start of sentence index, and then we define the encoder property, the decoder property, and SOS IDX. Then it equals the same values as we pass in these parameters. Then we have here a forward method. This forward method calls the whole model, which is sec-to-sec model. You can see here we have the training loop. So the training loop starts with SOS token. At each step, generate next word with teacher forcing, 50% chance, feed the true token, otherwise feed the predicted token. Then it collects predictions for the whole sequence. So teacher forcing helps learning early, but may be reduced later for more realistic decoding. Here the training, we have a loss as cross entropy loss, so the loss function, and also here you can see ignoring the padding tokens, and we have the optimizer, add an optimizer. In each epoch we apply the following: sentences are padded to equal length, model predicts target sequence, loss is computed on all tokens except starts of sentence. Then we have prints loss every 10 epochs. So we print the loss here every 10th epoch. You can see every 10th epoch the loss gets printed. We print epoch, the epoch number, whatever it was, with the loss value, with whatever it was. And here we calculate the loss. As you can see, we have the loss equals criterion, which is this variable that contains the cross entropy loss suitable for multi-class classification. And we do loss of backward, we do backpropagation, and then we do gradient descent. So these are also are all steps in the loop of the training loop. Then we have the evaluation. You can see here we have a function called translate sentence. Encodes source sentence into a hidden state. So it takes from me a trained model, a pre-trained model, and a sentence. Now we take this sentence and map it into a fixed length vector. You can see encodes source sentence into a hidden state, then starts decoding from start of sentence, predicts tokens until end of sentence or maximum length of 10, converts token IDs back into words. This simulates inference mode of sec to sec. Then we have the results section. If training went well, the input here you can see after we've trained the model. Here we have epoch 40, the loss has decreased from, you can see from epoch 0, we started the loss at 2.0. Then we trained the model for 40 epochs, for 50 epochs specifically, and you can see here the epoch 40 now, the loss is 0.11. So the loss has been decreased. And now if we pass the input I like dogs, it will translate correctly into the French version, which is GNMT chains. Same for cats. The same thing goes for the another sentence, which is I like cats. If we write in here I like cats and you will run that, it will say GMLS cats. So the key takeaway here is that we have a core idea encode into a context vector and then decode. The limitations are what? Fixed length context vector. Later improved, as we said, by Attention and Bahdanau et al. Paper. The most important thing here is that we have generated a tiny vocabulary and dataset, and we've used GRU instead of LSTM, both used in early sec to sec. So feel free to explore and use LSTM rather than GRU, and also note in here no attention mechanism is used. We still didn't apply any attention mechanism because this paper doesn't have attention mechanism. So the idea in here that we have replicated the model in a small scale on a small tiny dataset. So this was the section on replicating the paper, learning phrase representations using RNN encoder decoder with GRUs. Let's dive into sequence-to-sequence learning with neural networks by Sutskever, Vinyals, Cook-Vili, 2014. This paper is crucial in the world of sequence-to-sequence learning. The paper introduces an end-to-end framework for sequence-to-sequence learning using deep, long, short-term memory LSTM networks. The approach employs one LSTM to encode an input sequence into a fixed length vector and another LSTM to decode it into an output sequence. Evaluated on the WMT 14 English-French translation task, the model achieves a BLEU score of 34.8, surpassing a strong phrase-based statistical machine translation baseline, 33.3. Further, rescoring SMT and best lists yields a 36.5 BLEU, close to the best published system at the time. Notably, the method works well on long sentences, aided by the novel trick of reversing input sequences with ease, which eases optimization and improves performance. Problems addressed. So what are the problems they faced and how they addressed it? First problem, standard deep neural networks require fixed dimensional inputs and outputs, making them unsuitable for variable length sequence tasks such as translation, speech recognition, or question answering. So as we said, traditional neural networks, for example feed for nets, cannot handle variable length sequences, which is really poor. And then second, here we have existing SMT systems rely on statistical alignment and phrase tables, but cannot fully leverage deep learning's representational power. So the second problem is that existing SMT systems rely heavily on statistical alignment and phrase tables, but cannot fully leverage deep learning's representational power. Third, training recurrent models for sequence-to-sequence mappings faces challenges due to long-term dependencies and optimization difficulties. So we have the problem of long-term dependencies and optimization difficulties. So here we have the problems. How did they solve it? Proposed solutions. The first solution is use a two-stage LSTM model. So we have here a two-stage LSTM model. The first stage is encoder LSTM, reads the input sequence and produces a fixed length vector. So it produces a fixed length vector. Second, decoder LSTM that generates the output sequence conditioned on this vector. So you can see the ideas here are similarly to the previous paper. Employ deep LSTMs, 4 layers, 1000 hidden units each to improve capacity. So here they employed a deep LSTM network, 4 layers. So a four layer encoder LSTM and a 4-layer decoder LSTM with 1000 hidden units each. So you have 1000 hidden units each in each layer to improve capacity. Introduced a simple yet powerful trick: reverse the words in the source sentence during training. This creates short-term dependencies between source and target words, reducing optimization difficulty and significantly improving BLEU scores. So in short, the proposed solutions are: 1. Use a two-stage LSTM model, encoder and decoder. Second, employs deep LSTMs, 4 layers, 1000 units each to improve capacity. 3. Introduce a simple yet powerful trick, which is the idea of reversing the words in the source sentence. Why? This creates short-term dependencies between source and target words, reducing optimization difficulty and significantly improving BLEU scores. Purpose: to demonstrate that large LSTMs, large long short-term memory, can serve as a general solution for sequence-to-sequence learning, making minimal assumptions about input and output structures. So this architecture makes minimal assumptions about input and output dimensionality, about input and output structures, to show that neural networks can outperform phrase-based SMT baselines on large-scale machine transition tasks, and then to establish a foundation for end-to-end neural sequence learning applicable to translation and beyond. Methodology. So what is the methodology that they leveraged or they used? Data. They used WMT14 English-French dataset, which is a popular dataset for building models that translates English to French, 12 million sentence pairs. The model architecture is 2 separate LSTMs. So we have 2 separate LSTM encoder that reads an input sequence and maps it to a fixed length vector, and we have a decoder that, based on this vector, it generates a target sequence. 160,000 source vocabulary, 80,000 target vocabulary, out of vocabulary mapped to unknown. So every single token that is out of vocabulary, which is OOV, out of vocabulary, gets mapped to unknown token. Ensemble of 5 LSTMs, 384 million parameters. Training. They use stochastic gradient descent with gradient clipping. So note that the previous paper they used ADA delta, while here they leveraged stochastic gradient descent with gradient clipping. Also batching by sentence length to reduce wasted competition. So they batched the sentences to reduce wasted competition. 3. Parallelized across 8 GPUs. So they leveraged 8 GPUs to parallelize across it. Decoding. Left to right beam search, beam size 1 to 12. Evaluation. The BLEU scores, as we said, bilingual evaluation under study, scores on test set, comparisons to SMT baseline, analysis of long sentence performance, and land representations. Results: direct translations, ensemble of 5 reversed LSTMs. So they used an ensemble of 5 reversed LSTMs that results in 34.81 BLEU, outperforming SMT baseline, which is 33.30, rescoring SMT and best lists. Single LSTM produces a 35.6 to 35.8 BLEU. Ensemble, while an ensemble of 5 reversed LSTMs results in a 36.5 BLEU. So you can see here the ensemble of 5 reversed LSTMs is better than what? Better than the single LSTM. If you have a single LSTM, it produces or it results in 35.6, while ensemble of 5 reversed LSTMs, it results in 36.5 BLEU, close to state-of-the-art 37.37. Quantitative analysis. Land representations capture word order. So the model successfully captured word order and are robust to syntactic alternations, active versus passive, whether it was active phrase or passive phrase. Performance on long sentences remained strong, contradicting earlier concerns about memory bottlenecks. Key insight: reversing source sentences improved perplexity from 5.8 to 4.7, and BLEU from 25.9 to 30.6 for single models. So the idea or the data pre-processing technique of reversing source sentences really improved perplexity and BLEU scores, which are metrics and scores for building machine transition systems. Conclusions: a simple encoder-decoder LSTM framework can achieve competitive or superior results in large-scale machine transition. Second, the reversal trick provides a crucial optimization advantage, highlighting the importance of data pre-processing for sequence learning. Neural networks can successfully replace phrase-based SMT by learning direct sequence mappings. And also, the work establishes a general paradigm for end-to-end sequence-to-sequence learning, paving the way for subsequent advancements such as attention and transformers. This paper embodied a leap in thinking. Translation and sequence learning could be modeled end-to-end without explicit alignment tables or hand-engineered rules. So remember, the previous paper incorporated or integrated the RNN encoder-decoder within a statistical machine transition system, while in this paper they used only the RNN encoder-decoder without incorporating it or without integrating it with any statistical based approach. So here, this paper embodied a leap in thinking. Translation and sequence learning could be modeled end-to-end from start to end without explicit alignment tables or hand-engineered rules by introducing a two-stage encoder-decoder with LSTMs. So note that they used LSTMs rather than GRU. It proved that deep learning could map variable length sequence directly. The simple yet radical idea of reversing input sequence sentences highlighted how data representation choices affect optimization. So we here emphasize that data representation choices affect on optimization. Its success paved the way for attention mechanisms and transformers, redefining the paradigm of sequence transduction. So here, this is the paper, Sequence to Sequence Learning with Neural Networks by Ilya Sutskever, Oriol Vinyals, and Cook V. Lee in 2014. First demonstration of end-to-end neural machine transition with LSTMs. This work showed that deep LSTMs could learn to translate entire sentences directly, outperforming phrase-based SMT baselines and inspiring the attention revolution. And here we have the paper, you can check it in your free time. If you do view inline, this is the paper, as you can see, Sequence to Sequence Learning with Neural Networks. Abstract. Deep neural networks, DNNs, are powerful models that have achieved excellent performance on difficult learning tasks. Although deep neural networks work well whenever large labeled training sets are available, they cannot be used to map sequences to sequences. In this paper, we present a general end-to-end approach to sequence learning that makes minimal assumptions on the sequence structure. So the idea here, and the beautiful thing here about this paper, is that they introduced a model that makes minimal assumptions about input and output structure, about input and output dimensionality. Our method uses a multi-layered long short-term memory LSTM. And if you don't know LSTM, LSTM is an architecture or is an algorithm in recurrent neural networks. It's best suited to deal with time series or text datasets, and it was introduced in 1997 by Sepp Hochreiter and Schmidhuber to map the input sequence to a vector of a fixed dimensionality, and then another deep LSTM to decode the target sequence from the vector. Our main result is that on an English to French translation task from the WMT14 dataset, the translations produced by the LSTM achieve a BLEU score of 34.8 on the entire test set, where the LSTM's BLEU score was penalized on out of vocabulary words. Additionally, the LSTM didn't have difficulty on long sentences. For comparison, a phrase-based SMT system, statistical machine translation system, achieves a BLEU score of 33.3 on the same dataset. When we use the LSTM to re-rank the 1000 hypotheses produced by the aforementioned SMT system, its BLEU score increases to 36.5, which is close to the previous best result on this task. The LSTM also learned sensible phrases and sentence representations that are sensitive to word order. So the algorithm here is sensitive to word order and are relatively invariant to the active and the passive voices. Finally, we found that reversing the order of the words in all source sentences but not targeted sequences or sentences improved the LSTM's performance markedly, because doing so introduced many short-term dependencies between the source and the target sentence, which made the optimization problem easier. And here you can feel free to read through the paper. As you can see, we have nice figures, nice diagrams, and also here the model. This section is really important. The recurrent neural network RNN is a natural generalization of a feed-forward neural network to sequences. Given a sequence of inputs x1, x2, x3 to xt, which is the last time step, a standard RNN computes a sequence of outputs y1, y2, y until yt by iterating the following equation. We have this equation, as you can see, the same equation, sigmoid function, the logistic sigmoid activation function. Then we have here the w, which is the weight matrix multiplied by the x, plus the weight also multiplied by the previous hidden state. Okay. The RNN can easily map sequences to sequences whenever the alignment between the inputs and the outputs is known ahead of time. However, it's not clear how to apply an RNN to problems whose inputs and the output sequences have different lengths. So the problem here they faced is that how to make the RNN able to map a variable length input sequence into a variable length output sequence with complicated and non-monotonic relationships. The simplest strategy for general sequence learning is to map the input sequence to a fixed sized vectors using one RNN, the encoder, and then to map the vector to the target sequence with another RNN. This approach has also been taken by Kyung-Yeon Cho, which is we discussed in the previous paper. While it could work in principle since the RNN is provided with all the relevant information, it would be difficult to train the RNNs due to the resulting long-term dependencies. However, the long short-term memory LSTM is known to learn problems with long-range temporal dependencies. So if you have long-range temporal dependencies, then LSTM is a good choice for you. So an LSTM may succeed in this setting. The goal of the LSTM is to estimate the conditional probability. So the probability of the y, of the generated y tokens given or based on the x's, the given source sentence, where x1 until xt, where this part, the x's, the inputs, is an input sequence, and y1 to yt is its corresponding output sequence, whose length is t dash may differ from t. So the length of t dash, the generated output sequence, may differ from t. The LSTM computes this conditional probability by first obtaining the fixed dimensional representation v, so the vector of the input sequence from this x1 to xt, given the last hidden state. So note here the idea that they just keep the last hidden state. In the next paper, we will discuss why this is a bottleneck, given by the last hidden state of the LSTM, and then computing the probability of y1 until yt with a standard LSTM LM formulation whose initial hidden state is set to the representation v and x's. And here the most important thing is that here, the last thing, our actual models differ from the above description in 3 important ways. First, we used 2 different LSTMs, 2 separate LSTMs, one for the input sequence and another for the output sequence, because doing so increases the number of model parameters at negligible computational cost and makes it natural to train the LSTM to multiple language pairs simultaneously. Second, we found that deep LSTMs significantly outperformed shallow LSTMs. So if you use a deep LSTM, it will outperform shallow LSTM. So we chose an LSTM with 4 layers. Third, we found it extremely valuable to reverse the order of the words of the input sequence. So for example, instead of mapping the sentence A, B, C to the sentence alpha, beta, gamma, the LSTM is asked to map C, B, A to also again alpha, beta, gamma, where alpha, beta, gamma is the translation of A, B, C. This way, alpha is in close proximity to alpha, B is fairly close to beta, and so on. A fact that makes it easy for SGD, stochastic gradient descent, to establish communication between the input and the output. We found this simple data transmission to greatly improve the performance of the LSTM. So feel free to read this paper in your free time. I will let you read it in your free time. As you can see, we have here nice figures. Also, they visualized these. John admires Mary. John is, you can see here, we have a 2-dimensional BCA projection of the LSTM hidden state that are obtained after processing the phrases in the figures. And also you can read through the paper, okay? By doing that, or by saying that, now we've finished discussing the paper sequence-to-sequence learning with neural networks, Sutskever, Vinyals, and Cook-Vili 2014, that introduced the idea of using encoder, decoder, deep LSTMs to encode a variable length input sequence and map it to a variable length output sequence end-to-end based on neural techniques. Let's dive into replicating the paper sequence-to-sequence learning with neural networks. This paper introduces an end-to-end sequence-to-sequence sec-to-sec learning paradigm or framework using deep LSTM's long short-term memory. Unlike prior neural models limited to fixed input-output sizes, this method handles variable length sequences by encoding an input sequence from a fixed vector and decoding into an output sequence. The model achieved state-of-the-art machine translation results on English to French WMT14, surpassing strong phrase-based SMT statistical machine translation baselines. Let's dive into replicating the paper. So the first idea is we need to import the required and necessary packages. First, we import Torch. Torch is a deep learning core. It contains tensors, autogradient, and GPU CUDA accelerating interface. Then we have torch.nn, which contains the building blocks like embedding layers, LSTM layer, which we'll use later, linear layer to project the logits into the vocabulary space. Then we have torch.optim, the optimizer or the optimization library that contains several other optimizers like Adam and many other optimizers like SGD, stochastic, gradient descent, and so on. Then we have matplotlib.pyplot package for visualization and plotting different loss curves. Then we have a random library for randomness if needed. And then we have the device runs model on GPU if available, otherwise CPU. So this code, device torch to device, CUDA if torch.CUDA is available, else CPU. This is the most important idea behind it, is that it will check if our collab instance, our current collab instance contains a CUDA GPU device or not. If it contains, it will return true. And if this condition returns true, so if torch.CUDA is available true, then it will use CUDA. So it will check up and use CUDA. Otherwise, else it will use the normal CPU. Then it will store that into the device function and store it into the device constant. Then let's dive into what is the dataset. Well, we will generate a toy dataset. As you can see, we will use the function generate data for reverse sequence task. First, we pass in the batch size equals 32. Then we pass the sequence length equals 10. And also we have a parameter of vocab size equals 20. The main idea here is that when we generate the x's here, torch.randint, then pass 1, vocab size, then we specify the shape as batch size, sequence length. The y is the same as x, but in the flipped order. So we flip the x and store it in a variable called y. Then we return the x moved to the device and return y moved to the target device. So we move or transmit the data into the target device for compatibility, because later when we train the model and the data lives on the same hardware device. Then let's call the function by calling generate data and pass the batch size, for example, as a demo equals 2, sequence length equals 5, and vocab size equals 20. Here, the range of the values range between 0 and 20, and the sequence length here is 5. Note we have here 1, 2, 3, 4, 5. We have 5 values, and the batch size, the number of samples in each batch, is 2. So for the first batch we have 2 elements. For the second batch we have 2 elements. Each element has a sequence length of 5, and the values range is, the maximum value is 20. So you can see we have 11, we have 9, 12, 14, and so on. This is a controlled toy task for testing if sec2sec can learn ordering. The sequences are visualized using matplotlib. So you can see here we have the matplotlib idea. We have the import matplotlib.python.splt to get the library. Then if you go down to here, this is the same function, generate data, to generate the data. Then we have here generate one small batch. We call the function generate data and store the x batch, store the x. It returns x and y, and then we unpack it into x batch variable and y batch variable. Then we create a figure and axes using matplotlib by going plt.subplots and then pass the length of the x batches, 1, and then we have the figure size as 8,6. Then we loop through the axes, and for each axis we move the x batch into the CPU, then into NumPy, and then the same idea for the y. We move the y batch onto the CPU, and then we convert it into NumPy array. Then we use the plot function to plot these line plots, and then pass the range of the length of input sequence and pass the range of the length of target sequence, and then as the y-axis we pass the input sequence alongside the target sequence. Then we set the title as example I+, the set x6 as range of length as input sequence. Then we have the legend, we show the legend, and then finally we show the plot. As you can see, the input is the line blue, the blue line, and the target is the red line. As you can see, just the reverse order. So we will pass the model, we'll train the model how to take x as a vector and map it into the reverse vector. So we will teach the model how to reverse the order of the sequences. This is a task to test whether the model is able to learn sequence mappings. Then let's define the encoder. The encoder is a simple class. You can see here we have class encoder that inherits from nn.module. Module is the base class in PyTorch. Then we specify the init. You can see def underscore underscore init, then we have double underscore, and we pass into here the vocabulary size, embedding size, and the hidden size. These are all have parameters that you can set and define as your own values and test until you find the best values. Then here we have self.embed. Self.embed is an attribute that equals the embedding layer. Then we pass the vocabulary size and map the vocabulary size into the embedding size that you define into here. After we get the embeddings, we pass these embeddings as input to the LSTM, and the LSTM will map these embeddings into hidden size. And we have to set the batch first equals true. Here we define the layers. We define what layers will we use later. Then in the forward method, we can execute and call these layers. As you can see, first we pass the X, the input sequence, and map it into vector embeddings, rich representational vectors, and then we will take these embeddings and pass them as values to the LSTM, and the LSTM will apply the gating mechanism and will study these datasets sequentially, or study these vectors sequentially, and it will return a hidden state and a cell state. Then we return hidden state and cell state. So the main idea into here, converts token into embeddings, runs through LSTM, returns hidden and cell states. So the first thing is convert tokens into embeddings, then runs through LSTM, then we return the hidden state and cell state. The decoder class, as you can see, if you go down, we have class decoder that inherits from an index module. This class, here we define the init method that will contain the definitions of the layers. As you can see, it takes from me vocabulary size, embedding size, and hidden size. First, we apply the embedding layer. The embedding layer, what is job? It takes from me a vocabulary size and convert it from tokens into rich representational vectors, the embedding size that you define here. For example, 512 or 1024, whatever value you need. How much details do you want to encode each token? Then we pass these embeddings, as you can see, we have the embedding layer, pass these embeddings into the LSTM layer. Here we have the LSTM takes from me the embedding size, so whatever the embedding size here, the output, and maps it into a hidden size. And we have to set the batch first equals true. Then we have a last linear layer. This linear layer, you can see the encoder lacks this layer. Why? Because this layer here will be the projection layer that projects the learned logits into the vocabulary space, and the model will be able to decode, to translate, or to reverse the order of the sequences. Here we have the forward method, def forward. It takes from me Y and H and C. Then we take the outputs of this LSTM layer and pass it as input to the fully connected layer, which is this, the linear layer. And this linear layer will project into the vocabulary size, will map the hidden state or the hidden size back to the original vocabulary size, and will output the vocabularies. Then we have logits. Then we return the logits alongside with the hidden state and cell state. So the main aspects here takes previous tokens and hidden states. So here we pass the hidden state and cell state to the LSTM alongside with the new embeddings, then produces logits, the vocabulary distribution. Then the next class is the sec-to-sec class. This class combines both the encoder and decoder. So def underscore init, it takes from me vocabulary size, embedding size set as 64, and the hidden size equals 128. Here we have self encoder. So the encoder property or the encoder attribute. We instantiate an object from the encoder class and pass the normal parameters: vocabulary size, embedding size, hidden size. Whatever you want to set them, you can set them. Then we have the decoder. We instantiate an object from the decoder class and pass the vocabulary size, embedding size, hidden size. Then in the forward method here, we call the encoder, pass the source sentence into the encoder. The encoder will study the correlations, the relationships in this source sentence, and will produce a hidden state and cell state. due to the LSTM layer. Then we'll take this hidden state and this cell state and pass them alongside the target to the decoder. The decoder will use the target in addition to the hidden state and cell state, guiding the decoder, coming from the encoder to guide and help the decoder. Then the decoder can make predictions, make outputs, and store them into logits. Then we return logits. You may wonder, why do we have an underscore here? Because we want to emit this value which is here. We do not want to get this H and C, so we emit it here. Because remember, the decoder class here returns two values, the logits and a tuple containing hidden state and cell state. We just need to use the logits here. So we emit this by putting an underscore. We don't need to use it. We don't necessarily need to have it or use it. So the main idea of sec2sec combines encoder plus decoder and uses teacher forcing during training. Then let's train the model. Now we have a model, let's train it. So we have some hub parameters here, some really simple hub parameters. As we said, we have the vocabulary size equals 30. Then the model, we instantiate a model using the sec2sec class, which combines both encoder and decoder, then pass the vocabulary size. Then we move this model. We have to put this model on the target device by going .to device. Then we instantiate an object of the loss function, in other words, also known as aka criterion, which is cross entropy loss, very helpful for multi-class classification. Then we set the optimizer as the Adam optimizer. Here we have the optimizer as Adam because Adam is the most well-used optimizer for deep learning, and we pass the model, this variable, dot parameters, and the Adam optimizer will take these parameters and tell you, thank you, I will try to optimize them. I will try to update them to better represent the data. Then we set the learning rate as 1e raised to the power of -3, and then we have here a empty list that will store the losses in every epoch. So in every epoch, we will store the loss value here. At the end, after the training loop, we will be able to plot the losses. Why? Because we have stored them. We have tracked them. Then the epochs equals 1000. We will train the model for 1000 epoch. You can fine tune it in your own time. Then we have here a training loop. The training loop is super easy. We have training loop runs 1000 epochs. The main idea here is that for each epoch in range epochs, we generate data. We move that data into the device by going .to device. Then we pass the X through the target model and pass the target or the truth Y to the model. So we pass the X and Y into the model. This is the forward pass, the first operation. We do the forward pass X's and Y's to the model. The model will try its first forward pass and produce logits. Then we'll take these logits and pass them to the loss function. The loss function will judge whether these logits are really good or really bad or poor. So we will take these logits and reshape it for shape compatibility and then compare it to the ground truth Y. So we have the ground truth Y. Then the loss will judge and store its value in the loss variable. Depending on the loss, we will zero the gradients of the optimizer. We will initialize the optimizer or reset it again. This is a reset operation, very recommended by the PyTorch team. They said you have to zero the gradients before the backpropagation. Then we apply the backpropagation algorithm. Here triggers backpropagation to start and compute the gradients of the loss function with respect to the weights or with respect to the current weight parameters. And then we apply the Adam optimizer. Here, optimizer.sep, we apply the Adam optimizer to fine tune the weights and update the weights and make the loss lower and lower. So loss curve is plotted with matplotlib to confirm learning. You can see here we have printed the epoch every 10th epoch we print the loss. So you can see here epoch 10 the loss was 3.3, but over time the loss is getting down and down and down, lower and lower and lower until we reach here for the final epoch we reach 0.25. Then if we go to the next cell, you can see here this is the loss going down and decreasing. We have plotted it using the matplotlib by going plt.plot and then pass the list losses. This was the empty list before the training, but after training this list was populated with the loss values. Then we have the X label as epoch, we set the Y label as the loss, and you can see the correlation here. As long as the epochs increase, the loss decrease. And lastly here we have a function to predict. Here we turn the model into evaluation mode, and then we say with torch.noGrad, so do not use gradient. Here we tell PyTorch we don't need to enable gradient based algorithms. We don't want to enable training. We need to set the model into evaluation mode, into inference mode. Then we pass the we take the sequence and unsqueeze it, because why? Because we need to add a batch dimension to the first 0 dimension. We add a batch dimension to be compatible with the model. Then we pass this sequence or the sentence into the encoder of the model. The encoder of the model will compute the hidden state and cell state, and then pass these two values into the decoder alongside with the input, and the decoder will produce the logits. And then we take the argmax of the logits, we compute the argmaximum, then we take the prediction and append to the outputs. Then we slowly and gradually build the outputs list. Then at the end we return the outputs, or finally we return outputs. And you can see here when we input a sequence, for example 2, 2, 11, 12, 6, 25, 15, 15, 7, 23, the truth output should be like that. You can see here the flipped version: 23, 7, 15, 15, 25, 6. So it flips it the other way around. Then we have the prediction here: 23, 15. The model has got this wrong. Then we have 7, then 6, 15, 25, 12, 11, 2, 19. So here you can see the model has got some points right, some points wrong. Feel free to change the learning rate, to play around with the hyperparameters and see which are the best values that results in the best result. Then you can see here we have a visualization that visualizes the sec-to-sec prediction. Here you can see we have the input in the blue color, we have the target in the reverse, the truth, and the prediction. So this is a quick visualization using matplotlib. You can see here we have the bar plot function. We pass the x, comma target sequence, comma width, and we have another bar plot that represents the prediction. So this bar plot represents the target and the color is a light green, and this bar plot represents the prediction and it's in the color salmon, and this bar plot represents the input x minus width and it's in the color sky blue. And you can see some are matching and some are varying. So here in position 5 the input really matches the prediction, but here you can see the input, for example in the target, for example the target here matches the prediction, and also here the same idea goes here. So this is the idea of replicating sec-to-sec library, which is teaching a model by inputting some sequence and teaching the model how to flip this input sequence, how to learn, how to reverse. We are teaching the model how to mirror or how to reflect the input into the flipped version. This is the idea of this lab or this task. So this is the lab for replicating the paper sequence to sequence learning with NeuroTalks. This was a groundbreaking paper that introduces the idea of encoder and decoder, and as you can see we have replicated the classes of encoder and decoder in this way. So we have an encoder class with embedding layer and LSTM layer. Then we have a decoder class with both the same layers, embedding and LSTM, but with a new layer which is the linear layer, which is a linear layer that maps the hidden size into the vocabulary size. Let's dive into neural machine translation by jointly learning to align and translate by Bahdanau, Kyung-Yeon Cho, Yoshua Bengio, 2015. The paper proposes an improved neural machine translation (NMT) model that simultaneously learns to align and translate. Unlike earlier encoder-decoder frameworks, like the previous papers, that compress a source sentence into a single fixed length vector, the proposed model here introduces an attention mechanism, allowing the decoder to selectively focus and attend on relevant parts of the source sentence while generating each target word. This approach improves performance on English-French translation, reaching results comparable to state-of-the-art phrase-based SMT, and yields interpretable soft alignments between source and target tokens. Problems addressed. So what are the problems that they faced and how did they solve it? One, or the first problem, fixed length bottleneck. So we have the bottleneck of the fixed length. Recall that the encoder maps a variable length input sequence into a fixed length vector. This fixed length vector is a bottleneck. Prior encoder-decoder models required encoding an entire source sentence into one vector, which caused severe performance degradation on long sentences. The second problem is that lack of alignment modeling. Earlier neural machine translation systems, like the previous papers, had no explicit mechanism to capture word-to-word or phrase-to-phrase correspondences, like phrase-based statistical machine translation. The third problem is that scalability, need for a neural architecture that could handle long sequences while maintaining translation quality. So we need a neural architecture that could handle and deal with long sequences, long sentences, while maintaining translation quality. So these are the problems. In short, fixed length bottleneck, lack of alignment modeling, so we lack the alignment of the modeling, and also scalability, to be able to scale the model. How did they solve it? Well, proposed solutions. The first solution introduced a soft attention mechanism. So in this paper, they invented and introduced a soft attention mechanism that attend and focus selectively on relevant and most important parts. For each target word, the model computes a context vector as a weighted sum of source annotations, where weights represent soft alignment probabilities. The second solution is that use a bidirectional RNN encoder to generate annotations for each subword, for each source word, capturing both left and right contexts. So the bidirectional RNN is a special kind of RNN that processes text or process data from two directions, from left to right and from right to left, capturing more fine-grained details and more information. Jointly train encoder, decoder, and alignment model end-to-end via maximum likelihood estimation. The fourth solution is that replace the fixed vector bottleneck with adaptive context vectors, enabling the decoder to dynamically retrieve relevant information from the source sentence. So in short, they introduced a soft attention mechanism, used a bidirectional RNN encoder to generate annotations for each source word, capturing both left and right contexts. Third, jointly train encoder, decoder, and alignment model end-to-end via maximum likelihood estimation. And fourth, replace the fixed vector bottleneck with adaptive context vectors, enabling the decoder to dynamically retrieve relevant information from the source sentence. Purpose to overcome the limitations of fixed length sentence representations in NMT. So to overcome what is the purpose of this solution? The purpose is to overcome the limitations of fixed length sentence representations in NMT. Because when you map a variable length input sequence into a fixed length vector, this results in, or this leads to, a bottleneck where you will map different sentences, different length sentences into the same dimensionality. That will cause some bottleneck issues, Like, for example, you will encode long sentences and short sentences with the same amount and level of details to demonstrate that neural attention mechanisms improve both translation quality and interpretability, to provide a unified framework where alignment and translation are jointly optimized, reducing reliance on external statistical machine translation components. Methodology. Architecture. So what is the architecture that they have used? Encoder. Bidirectional RNN generates a sequence of hidden states, annotations. Attention mechanisms computes alignment scores between decoder state and encoder annotations, normalizing them into weights. So we normalize them into what is so-called weights. Decoder, conditioned on previous outputs, hidden states, and attention-derived context vector. The dataset that they've used is English-French WMT14 parallel corpus, 348 million words, shortlist vocabularies of 30,000 most frequent words for both source and target. Models compared. They compared their proposed model with the baseline, which is an RNN encoder decoder without attention, so RNN NNDEC, proposed attention-based neural machine transition, RNN search. So these are the models that they compared. First, we have here the baseline, RNN encoder decoder without attention, and then we have the proposed, which is attention-based NMT. Training. Optimization. For the optimization purpose, or for the optimization strategy, they used mini-batch SGD stochastic gradient descent with added delta and with gradient clipping. Trained on GPUs, NVIDIA Titan Quadro. Evaluation, BLEU or BLEU scores, and quantitative alignment visualizations. Results, quantitative, RNN search consistently outperforms RNN NNDEC across sentence lengths. So the RNN that is provided with the attention mechanisms consistently outperforms the RNNs without attention. As we said in here, we have two experiments. We have the baseline, which is RNN encoder decoder without attention. They called it RNN NNDEC. And we have the proposed model is attention-based neural machine transition, and they call it RNN search. So here, RNN search, which is the attention-based neural machine transition, outperforms the RNN NNDEC across sentence length. BLEU scores. RNN NNDEC 50 is 17.82, but RNN search, the attention-based neural machine transition, is 26.75. So you can see the difference here is large, from 17.82 to 26.75, 34.16 on sentences without unknown token. Extended training, RNN search 50, which is 28.45, 36.50 without unknown, matching phrase-based statistical machine transition, Moses 33.30 and 35.63. Qualitative land alignments are linguistically meaningful and often monotonic, but capable of non-trivial reorderings. For example, adjective-noun swaps, when you swap the adjective with a noun. Soft alignments handle ambiguous cases. For example, article, gender in French, better than hard alignments. Demonstrated robustness on long sentences, on long-range dependencies, where baseline models failed. So the baseline models failed modeling and capturing long-range dependencies, whereas this model demonstrated robustness on long sentences. The conclusions here are the following. The proposed attention-based encoder decoder overcomes the fixed length bottleneck of early neural machine transition models. The model achieves translation performance comparable to state-of-the-art SOTA statistical machine transition while providing interpretable alignments. Attention allows the model to handle long sequences and linguistic reordering naturally. This work established attention as a foundational principle in neural machine translation and deep learning, directly inspiring subsequent architectures like the transformer. In the paper, attention is all you need. This paper redefined the landscape of machine translation by introducing attention, a mechanism that allowed neural networks to focus and attend on relevant parts of the source sentence during decoding, instead of forcing information into a single fixed length vector, which is a bottleneck. It enabled dynamic, flexible context retrieval, making translation of long and complex sentences feasible. Philosophically, it shifted neural machine translation from compression to selective focus, from just blindly compressing data to selective focus, inspiring not only subsequent attention variants but also the transformer revolution, the transformer era. Attention in neural machine translation. Neural machine translation by jointly learning to align and translate by Dimitri Bahdanau, Kyung-Yeon Cho, and Yeshua Bengio in 2015. Landmark work introducing the attention mechanism in neural machine translation. This work overcame the fixed length bottleneck of early neural machine translation models by learning soft alignments, enabling dynamic focus on source words, and laying the foundation for modern attention architectures. And also we have here the paper. Feel free to read the paper in your own time, but let's take a quick look at it. As you can see here, we have this neural machine translation by jointly learning to align and translate. Abstract. Neural machine translation is a recently proposed approach to machine translation. Unlike the traditional statistical machine translation, the neural machine translation aims at building a single neural network that can be jointly tuned to maximize the translation performance. The models proposed recently for neural machine translation often belong to a family of encoder decoders and encode a source sentence into a fixed length vector, which is a bottleneck. Why? Because think of it, when you encode long sentences and short sentences both to the same amount of detail or to the same level of detail, then you would waste competition. You would waste a lot of computational units for nothing. So here we have a family of encoder decoders and encode a source sentence into a fixed length vector, from which a decoder generates a transition. In this paper, we conjecture that the use of a fixed length vector is a bottleneck in improving the performance of this basic encoder-decoder architectures, and propose to extend this by allowing a model to automatically soft search, attend, and focus selectively for parts of a source sentence that are relevant, that are associated, that are of high or most significant to predicting a target word, without having to form these parts as a hard segment explicitly. With this new approach, we achieve a translation performance comparable to the existing state-of-the-art, best-in-business phrase-based system on the rank of English or on the task of English to French translation. Furthermore, qualitative analysis reveals that the soft alignments found by the model agree well with our intuition. And also, you can read through here in your own time. You can see that they are referring back to Sutskever, sec to sec, and also for Cho, with an encoder and decoder for each language, or involve a language-specific encoder applied to each sentence, whose outputs are then compared, and also an encoder neural network reads and encodes a source sentence into a fixed length vector. And also you can see here, in order to address this issue, we introduce an extension, a gold extension to the encoder-decoder model, which learns to align and translate jointly. Each time the proposed model generates a word in a translation, it soft searches. This is the idea. It soft searches for a set of positions, for a set of parts in a source sentence where the most relevant information is concentrated. The model then predicts a target word based on the context vectors associated with these source positions and all the previous generated target words. Here you can see the most distinguishing feature here, the most important distinguishing feature of this approach from the basic encoder decoder is that it doesn't attempt to encode a whole input sentence, a whole input sequence into a single fixed length vector. Instead, it encodes the input sentence into a sequence of vectors and chooses a subset of these vectors adaptively while decoding the translation. This frees a neural translation model from having to squash all the information of a source sentence regardless of its length into a fixed length vector. So instead of blindly just squashing all of the inputs into a fixed dimensionality, we show this allows a model to cope better with long sentences, to perform better with long range dependencies. In this paper, we showed that the proposed approach of jointly learning to align and translate achieves significantly improved translation performance over the basic encoder-decoder approach. The improvement is more apparent with longer sentences. But can be observed with sentences of any length. On the task of English to French translation, the proposed approach achieves with a single model a translation performance comparable or close to the conventional phrase-based systems. The phrase-based systems, which is statistical machine translation. So now they reached or close to the phrase-based systems performance. Furthermore, quantitative analysis reveals that the proposed model finds a linguistically plausible soft alignment between a source sentence and the corresponding target sentence. And also you can feel free to read the rest of the paper. You can see here we have these equations. You can see h equals f of x comma h, which is the hidden state. And also you can see here in the encoder-decoder framework, an encoder reads the input sentence, a sequence of vectors, into a vector C. The most common approach is to use an RNN such that this RNN. And if you scroll down, here you can see learning to align and translate. Here they said we propose a novel architecture for neural machine translation. The new architecture consists of a bidirectional RNN as an encoder and a decoder that emulates searching through a source sentence during decoding a translation. And you can see here they have this diagram, the graphical illustration of the proposed model trying to generate the TAIF target word given a source sentence x1, x2 until xr. And feel free to read through the rest of the paper. You can see these are the representations. You can see here the words, the agreement on the European economic areas was aligned, and they align with each other closely. So now we have finished discussing the paper of introducing attention, neural machine translation by jointly learning to align and translate. Let's dive into the next paper. Let's dive into replicating the paper Neural Machine Translation by Jointly Learning to Align and Translate by Dimitri Bahdanau, Kyung-Yeon Cho, and Yeshua Bengio, 2015. So the first thing we need to do is to import the necessary and required libraries. By doing so, import Torch for tensor operations and torch.nn as nn that contains several building blocks for building neural networks, and we have import torch.optim as optim for optimizers. The first block is the encoder block. So we have here, we define the encoder class. It's a neural network that reads the input sentence. Then we have inside it the init method. The init method, this is the constructor. It sets up the encoder with vocabulary size, how many words in the source vocabulary, embed size, how big each word vector should be, and hidden size, how big the GRU's memory should be. So the vocabulary size is how many words in the source vocabulary. The embedding size is how big each word vector should be, and the hidden size is how big the GRU's memory should be. Then we have the self.embedding property or attribute that contains an embedding layer. This layer turns word IDs into dense vectors, like word meanings in numbers. Then we have self.rnn equals nn.gru, the GRU layer that takes from me the parameter embedding size and map it to hidden size. Then set the bidirectional property or attribute equals true, then batch first equals true. This is the GRU, a kind of RNN that reads the sentence. So it reads a sentence. We set the bidirectional equals true, means it reads forward and backward. Then we have the batch first parameter equals true, means input looks like batch, comma, time, comma, features. We start by batch, then the time, then the features. After we've defined the components, we will call them using a forward method. This forward method takes from me a self to denote that it's a parameter and the x. The forward method defines how the encoder processes input. Then we have the embed or the embedding variable. Turn the input word IDs into vectors. Shape becomes batch, comma, sequence length, comma, embedding size. After it, we have the outputs, comma, hidden equals self.rnn, and then pass embedding. Run the vectors through the GRU. Outputs is information for every word in the sentence. So the outputs contains information for every single word in the sentence. Whereas the hidden is the GRU's final memory state. The GRU's final hidden state. One for forward and one for backward. Then we return them. Return outputs, comma, hidden. Return both the word by word outputs and the final memory state. Let's define the class attention. The attention class decides which parts of the input sentence the decoder should focus on. Then we have inside this class the init constructor. Set up attention using the decoder's hidden size. So we pass the hidden size parameter. Then we have self.attention equals nn.linear and then pass hidden size times 3, comma, hidden size. A linear layer that will mix the decoder state h with encoder outputs to h. The 3, so we multiply the hidden size here by 3. Together, that's 3h, so 3 hidden size. After it, we have the self.v property equals nn.linear, a simple linear layer. Another linear layer that reduces everything to a score, one number per input word. So now we have defined the components that will be used inside the forward method. The forward method contains the hidden, the decoder's current state, and encoder outputs all the encoder's word representations. Then we have this variable src length, copy the decoder's hidden state across all time steps so we can compare it to every encoder word. Then we have the energy variable equals torch.tanh. We apply the tanh function and pass into it the self.attention layer, which is this layer, self.atten, which is this attention layer. So we apply this linear layer and pass into here and invoke it. Then we pass torch.concatenate, and then we concatenate the hidden alongside with the encoder outputs, and then specify the dimensionality equals to combine the decoder state and encoder outputs, then squish them through a tanh activation. That will produce an output limited between -1 and 1. Turn those combined vectors into raw attention scores, one per word via the self.v, and then pass the energy. All we're doing here is we're taking the energy and passing through the v property, which is this linear layer, then it compresses it, then we compress it using the squeeze function. Then we normalize these scores via the softmax function. Normalize the scores with softmax so they become probabilities how much to focus on each word. Here you can see we are taking the attention scores, passing them to the softmax activation function, and it will produce a normalized probabilities. Then we store them inside the attention weights variable. Then we make a context vector, a weighted sum of encoder outputs based on attention weights. We retain context, comma, attention weights. Retain the context vector to help prediction and the attention map for visualization. This is the attention class. We move on to the decoder class. Here we have decoder, class decoder, that inherits from NN.module, the base class in PyTorch for building neural networks models. The decoder class generates the output sentence one word at a time. Then we have the init, the constructor. It needs vocabulary size, how many words in the target vocabulary, embedding size, size of word embeddings, and then we have the hidden size, size of GRU's memory. The first thing, we instantiate a property called embedding, or an attribute that contains the embedding layer. You can see we have NN.embedding. This embedding layer turns target words into vectors, into rich representational vectors. Then we have the self.rnn equals nn.grew, the grew layer implemented in the PyTorch library. We pass embedding size plus hidden size times 2, comma hidden size. Then we set the batch first equals true. So the grew that runs the decoder, its input is both the current word embedding, E, and the context vector, which is 2 multiplied by H. Then we have self.fully connected equals nn.linear. A simple linear layer predicts the next word by mapping decoder state and context to vocabulary size. So depending on the decoder state and the context, we predict the vocabulary size. Then we have this attention layer, self.attention equals attention. I attach the attention module we built earlier. So we built earlier the attention class. As you can remember, we have this attention class. You can see here we have the attention class, this class that we have built earlier, attention. We have instantiated a new layer that is from the attention class, instantiated from the attention class, and pass into here the hidden size. Then now we have defined the components, the necessary components, necessary elements. Now we need to combine them into the forward method. How should they be executed in the forward fashion method? So by going def forward, then pass self, x, hidden, encoder outputs. Forward pass, given the current word, given the current decoder state, and encoder outputs, predict the next word. And a time dimension to that word. Here we have unsqueeze. We are adding a time dimension to the word, which is, you can see, b batch, 1. Then we have here embedding equals self.embedding, and then pass x. Turn the word ID into an embedding vector. Then after that, we use the attention mechanism. You can see, use attention, look at encoder outputs, and decide where to focus. The attention mechanism is a machine learning technique that directs deep learning models which to prioritize and which to attend to which words to focus on the most relevant and the most salient details and ignore those with less details. So you can see we have the torch.cat to concatenate the embedding alongside with the context.unsqueeze1, dimension 2, join the word embedding with the attention context. Then we output the output, hidden equals self.rnn, and then pass rnn input, hidden. So we are passing the rnn input that we concatenated earlier alongside to the hidden state, and we are passing them to the rnn, which is the grew layer. This grew layer will apply the gating mechanism, will apply the reset gate and update gate, and study the correlations and relationships, and then produces an output and hidden state. Run them through the decoder, grew, get new output plus updated hidden state. Then we have the prediction equals self.fully connected, then pass torch.concatenate, and then pass output.squeeze1, context dimension equals 1. Make the prediction, combine decoder output plus context to produce logits over vocabulary. Then finally, we retain the prediction, hidden, attention. Retain the word prediction, update the hidden state, and attention weights. Now let's combine these mechanisms into the sequence to sequence wrapper. So we have a class called sec2sec. This is the full model. It connects encoder plus decoder. We have the init, the constructor, store the encoder, decoder, and the device, whether it was GPU or CPU, depending on your available hardware device. So you can see we have encoder, decoder, device. Then we have here self.encoder, self.decoder, self.device equals the past encoder, decoder, device parameters. Then we have the forward method. Here in the forward method, forward pass takes a source sentence, so you can see a source sentence and a target sentence for training, and also teacher forcing ratio controls how often we use the real next word versus the model's guess. And as you can see, we have the batch size, target length equals target.size. Figure out how many examples and how long the target sequences or sentences are. This figures out how long each source sentence and target sentence are. Get the number of the words in the target vocabulary. Then we create a tensor to store all decoder outputs by going outputs equals torch.zeros. Then we pass the batch size, comma, target length, comma, vocabulary size dot to self.device. After this step, we have the encoder outputs, comma, hidden, which will be equal self.encoder, then pass the source. So simply we are passing the source sentence, the pre-processed source sentence, we are passing it to the encoder. The encoder will map this source sentence into rich representation vector, and store the encoder outputs in addition to the hidden state. Run the encoder on the source sentence, get all word outputs plus final hidden states. Then we have, since the encoder is bidirectional, we merge the forward and backward states to start the decoder. So we merge them here via the syntax. We are here indexing hidden, start from the beginning until the first token, plus here hidden, start from the first until the last. So combine bidirectional GRU states to combine the forward and the backward pre-processing or processing of the GRU. GRU here is bidirectional. It reads the text left to right, and right to left. Then we start the decoder with SOS token. This is a special token, start of sentence token. So as you can see, we have here for token in range 1, comma, target token, loop over each time step in the target sentence. Then we produce output, comma, hidden, comma, attention by using self.decoder and pass input, hidden, and encoder outputs. Run one step of the decoder, then get predicted word, get the new hidden state, and attention. Then as you can see, we have the save the prediction in our output tensor by giving outputs. Then we index using the colon mark, comma, t, comma, colon mark equals output. And as you can see here, we have the teacher force. Then the next step equals torch.rand pass 1.item that is less than teacher forcing ratio. Decide randomly whether to use teacher forcing or not. Randomly. Then input equals target indexing on it colon, comma, t. So start for the first index or the first dimension is all, comma, t, that's the specified token. If teacher force, else use output.argmax. If teacher forcing, use the real next word, otherwise use the model's predicted word. Then finally we return the outputs. Return outputs, return all predictions. So this is the idea of the blocks. Here you can see simply we have a pairs, sentence pairs. We have English language mapped to French language, English language mapped to the French version, and so on. We have some sentences. Feel free to change them to whatever you want. So this is a toy dataset that we'll try on. They are stored in tuples, and all these tuples are combined within a list. After this, we have build vocab function. You can see def for defining a new function called build vocab and pass in here the sentences. Then we have this set. Set is an object inside Python. So set here is really valuable. Why? Because set doesn't accept duplicated items. So these vocabulary words will not be duplicated. So we use the set object inside the Python programming language. Then we store it inside tokens. For each sentence, in these sentences, let's go ahead and tokens.update. Let's update this set object and pass or insert on it the sentence.split. So we need to split the sentence, to segment it, to tokenize it. Tokenization is the process of segmenting a source sentence into subunits, into sub-tokens, to break it, to split it. Then here we have a dictionary comprehensive where we say token, map each token to the index plus 2. For each index and token, enumerate sorted tokens. So all we're doing here is that we are looping through the sorted version of the tokens. So we have token set. We are sorting it alphabetically. Then we are looping through it. when we loop through it, we have two variables. We have the index and the token. We map this token to the index plus 2. So we have here a dictionary that will be populated through this loop, and then we have vocabulary, we have padding. Let's map it to 0, map it to 0. We have SOS, which is a special token, start of sequence, map it to 1. Then we have end of sequence, map it to the length of vocabulary, and at the end we retain the vocabulary. That is as simple as it is. Then you can see here we are calling the build vocab function twice, one for the source sentences and one for the target sentences, one for the English version sentences and one for the French version sentences. Then we are passing into here source for SRC in pairs. So we are looping through these sentences. Here we are looping through these. I am a student. He likes apples. She loves music. We are looping through this and getting these sentences, and we are doing the same but looping through the next target sentences. So in the French version, for each target in pairs. And note we emit here via underscore. We emit the English version, while in the English version loop we emit the French version by doing underscore. So all we're doing here, we are calling the function build vocab and passing the sentences, whether it was English version or French version. After this, here we have inverse target vocabulary. We have a dictionary, I mapped to T. For each token, comma index, we are looping through the tokens and indices. For each token, comma index, in target vocabulary dot items, we are getting the items. Then we are mapping the index back to the token. So we are inversely mapping the index back to the token instead of the mapping token to the index. We are inversing the operation, inversing the way. And then we have a simple nice function called encode. Takes from me sentence, comma vocab, comma max length equals 8 as the default value. Then we take the sentence and split it, tokenize it, store this into tokens variable. Then we do some list comprehension here via for each token in tokens. Please add this special token at the beginning of the sentence. Add this special token, which is start of sentence. And then loop through all tokens, bring them here, put them here. At the end of the sentence, finally inject this token, end of sequence. Then we have indices, the same idea. We add the padding, multiply by the max length minus the length of indices to add the padding. Then we return at the end, we return a new torch tensor and pass into here the indices, the indexes. Here we are calling the function stack and then passing the same list comprehensions we seen above. For each source in the pairs, here we are emitting the French version. We are taking the English version language and then passing this source to the encode function that accepts from me or takes from me the sentence as the source version and the source vocab, and the same idea here but for the French version. We are emitting the English language but enabling the French version language and passing it to the encode function to encode it. To encode encode function, all it does, it starts the sentence with the special token SOS, it ends the sentence with the special token end of sentence, but it encapsulates here the rest of the tokens. So vocab T for T in tokens. The next step here is, you can see we have hyperparameters, some general hyperparameters that you can set. Embedding size equals 32, hidden size equals 64, and device equals CUDA if torch.CUDA is available, else CPU. So all we're doing here is that we are checking if we have a CUDA enabled GPU or not. So if torch.CUDA is available, if you really do have a GPU, then this will be true. Thus, you will use CUDA. Otherwise, you will use a normal, slow CPU. Then we have encoder. Let's instantiate a new object from the encoder class by going encoder, pass into here the respected hyperparameters, and move this encoder model to the target device. By the way, we've discussed these hyperparameters earlier. Then we have a decoder equals decoder object or decoder class. This decoder variable will instantiate a new object from the decoder class, and then we pass these hyperparameters. Then we move we move it to the target device to be compatible with the data. So the data and the model need to be on the same hardware device in order for the model to be able to compute on the data, or in order for the model to be able to interact with the data. Then we have the model, instantiate the whole model. This model connects the encoder and the decoder, sec to sec. We pass the encoder, we pass the wonderful decoder, we pass the device, and then we move this target, this model to the target device by going to device. So we are sending this whole model, this whole part of the model into the device, target device, whether it was CUDA or CPU, depending on your hardware or available hardware. Then we set the optimizer as the add optimizer. So the add optimizer is a well optimizer method or strategy. We pass the parameters of the model to optimize them, and then we set the learning rate as 0.01. Then we have a criterion which is cross entropy loss, and then we pass ignore index equals target vocabulary, ignore the padding. So we do not want to treat the padding as a real token, and the model will be judged by the padding. Then you can see here we have a nice small training loop. We set the epochs to 200, then we loop through that for each epoch in the range of epochs. So loop through this number of epochs, whether it was 200 or 100 or 10 epochs, whatever you define. Then we set the model mode into the training mode. So we need to set the mode of the model into training by going model to train function. Then we zero the gradients of the optimizer. Why? To speed up the optimizer. Then we pass the source sentences alongside with the target sentences and do our very first forward pass to the model. So here we are doing the forward pass, the forward fashion pass. Then the model will compute its outputs. These outputs from the first time are not that good outputs, aren't that wonderful outputs. We need to optimize the weights in order to produce really well-performing outputs. So we need to take this output and compare it to the truth target outputs using the criterion. The criterion function, the cross entropy loss, will judge and will compare the results of the model with the ground truth and judge the model, whether it's a well-performing model or a bad, poor model. Then we do a backpropagation to compute the gradients. Then we call Adam. Hey Adam, please help us and update the weights. And then every 10th or every 50th, every 50 epoch, we will print the results, the loss function. You can see here. By the last epoch 200, we have a loss of 0.00. The epoch 50, we have loss at 0.0008. By the end, we have a loss value of 0.0002, which is, you can see the loss is decreasing. The loss is getting lower and lower and lower. Then here we have a nice function to translate. It takes from me quickly sentence, a trained model, source vocabulary, target vocabulary, inverse target vocabulary, and the maximum length. Then here all it does is that it adds a batch dimension via the unsqueeze method. Then it moves this target sentence into the target device in order for the model to be able to interact with it. Then we have a target index where we add the start of sentence token. We need to add it manually. So the target index equals target variable. Then we index on the SOS token. Then we pass this target or the source sentence. We pass it through the encoder. The encoder will apply the GRU. So first we will map this source sentence into the embedding vectors. Then the GRU will come and help us to regulate the flow of information, to study more fine-grained details on this embedding vectors. So the GRU has two gates, reset gate and update gate. Then it produces a high, very rich representation vector. Will be encoded outputs, hidden. Then we need to combine the bidirectional states. So because we are processing from both directions, from left to right and from right to left, we need to combine them via hidden and then square brackets, :1 plus we need to combine or add the hidden 1 colon. At the end here we have a for loop that will loop through the maximum length, which is 8 by default. You can change it, and then we pass this target index to the tensor function to turn it from a normal array into a tensor and move it to the target device. Then we use the decoder now and pass the target tensor alongside with the hidden in addition to the encoder outputs, and it produces the output plus the hidden state plus the attention scores. Then we take this attention scores, you can see here we take the output and take the argmax function or apply the argmaximum function. This argmax will give me the index or will retain the index of the largest value inside this output, and this will be the predicted token, the desired token that the model thinks or believes that this is the most appropriate token should be generated. Then we append it to the target index here in this list, which should start with start of sequence. At the end we have an if condition. If this predicted token equals the end of sentence, meaning that the model has finished predicting or has finished generating, we need to break this wonderful loop and get out of it. Then at the end, finally, we return a new string and join. Join is a method that converts a list into a string. So now we have a list of the predicted tokens. We do not want list. We need it in a string format. So we use join. We start with an empty string. Then we join alongside with the list. We do some for loop here. For I in target index. If this I isn't in this group, 0 or 1 or end of sentence, then do the following. Inverse target vocabulary index on the I. You can see here we have called this function translate and passed the English versions, and it correctly and successfully mapped them into the French versions. So this is the replicating of the neural machine transition by jointly learning to align and translate paper, where we implemented the attention mechanism, the encoder decoder framework to translate from variable input sequence into a variable output sequence length. Let's dive into the paper on using very large target vocabulary for neural machine translation by Jean, Cho, and et al. 2015. The paper addresses the vocabulary limitation in neural machine translation, NMT, where training and decoding complexity grows with target vocabulary size. The authors propose an importance sampling-based algorithm that enables training with very large vocabularies efficiently and introduce candidate lists for efficient decoding. Empirical results on WMT14, English to French and English to German, show that large vocabulary NMT matches or outperforms short list-based models and achieves near state-of-the-art BLEU scores. What are the problems that they faced? The first problem, standard NMT requires limiting target vocabularies. For example, 30,000 to 80,000, replacing rare words with unknown. Second, performance degrades heavily when translations require many out-of-vocabulary OOV words. Third, computational cost of softmax normalization grows linearly with vocabulary size. Fourth, conventional fixes, for example, hierarchical softmax, class-based models, noise contrastive estimation, reduce training complexity but not decoding complexity. What are the solutions that they used to mitigate these problems? The first solution is that approximate training with importance sampling. Train using only a sampled subset of the vocabulary per update, reducing normalization cost. Second, partition-based vocabulary subsets. Divide training corpus, define per partition vocabularies to fit GPU memory. Third, candidate lists in decoding. Use dictionaries and unigram statistics to restrict possible target words at test time. Fourth, unknown replacement strategy. Replace unknown tokens using word alignments or bilingual dictionaries. So you can see here in short what are the proposed solutions. First, approximate training with importance sampling. Second, partition-based vocabulary subsets. Third, candidate lists in decoding. And fourth, unknown replacement strategy, where they replaced unknown words or tokens with the unknown token. Purpose: enable very large target vocabularies in NMT without prohibitive computational costs. Second, improve translation accuracy, especially for rare words. Third, match or surpass state-of-the-art SMT, statistical machine transition, and neural machine transition systems. What is the methodology that they used? The datasets that they have used is English to French, 12 million sentences from the Europe RL, Common Crawl, UN, News Commentary, Gig Word. Second, English to German, Europe RL, Common Crawl, and News Commentary. The models: number one, baseline. The baseline model that they compared their proposed architecture with is RNN search with attention. Bahdanau et al. 2014 with 30,000 vocabulary English to French and 50,000 vocabulary English to German. So we have 30,000 vocab for English to French and we have 50,000 vocab for English to German. Second, proposed models: RNN search LV 500K vocabularies trained via importance sampling. So the models, we have a baseline model which is RNN search with attention, which is Bahdanau et al. 2014, and we have the proposed models which they called RNN search -LV 500,000 vocabularies. So you can see the increase of the number of vocabulary. Here in Bahdanau we have 30,000 vocabulary, where they have here in this paper they have 500,000 vocabularies trained via importance sampling. Training details: number one, beam search. Beam equals 12, and they used dropout to prevent and mitigate the risk of overfitting, and they used gradient clipping. 2, candidate lists with K equals 15,000 to 50,000 for decoding. Third, bilingual dictionary for unknown replacement. And then we have the evaluation here: BLEU scores on WMT14 test set and the development on use test 2012 and 2013. Results: from English to French, the results are the following. On baseline RNN search, which is of Bahdanau, they achieved 29.97 BLEU, whereas in this proposed new architecture RNN search-LV, they achieved 32.68 BLEU. So they enhanced the BLEU score from 29, roughly 30, to 32.68. Plus unknown replacement. If you add the unknown replacement strategy, then we will have 34.11 BLEU. And if you combine many models and ensemble collection, we have 37.19, which is near SOTA. And then we have from English to German, we have a baseline 16.46 BLEU. Then we have the RNN search LV, the new proposed model, 16.95 BLEU. And then if you combine the unknown replacement, we have an increase of 18.89 BLEU. And if you combine multiple models, several other models, which is an ensemble, we have 21.59 BLEU, better than previous SOTA of 20.67. Decoding speed. Candidate lists brought decoding time close to baseline despite larger vocabularies. So the decoding speed came from the idea or the concept of candidate lists. Candidate lists brought decoding time close to baseline despite larger vocabularies. Conclusion: large vocabulary NMT trained with importance sampling outperforms short list based models. Second, candidate lists enable practical decoding speeds. Third, unknown replacement and ensembles further boost performance. And then fourth, the approach achieves near state-of-the-art on WMT14 benchmarks and surpasses phrase-based SMT. This work demonstrated that neural machine transition need not be constrained by artificial vocabulary limits. By making large vocabulary models practical, it paved the way for handling rare words, unseen words, more effectively, and influenced later architectures where scaling vocabulary size became standard. For example, subword methods like byte pair encoding and eventually large-scale transformers. On using very large target vocabulary for neural machine transition by Sebastian Jean and et al., Kyung-Yeon Cho, Ronald Mismisic, and Yeshua Bengio introduced important sampling training for large vocabularies, candidate lists for decoding, and showed that neural machine transition can scale effectively to hundreds of thousands of target words. This work removed the vocabulary bottleneck in NMT, showing that large-scale vocabularies could be both trainable and decodable, paving the way for modern subword and large-scale transformer approaches. And you are more than welcome to check out the paper. If you click view online, it will show a pop-up window that displays the paper. And you can see here we have the abstract, neural machine transition, a recently proposed approach to machine transition. And the most important idea here, in this paper, we propose a method based on importance sampling that allows us to use a very large, a very massive target vocabulary without increasing training complexity. We show that decoding can be efficiently done even with the model having a very large target vocabulary by selecting only a small subset of the whole target vocabulary. The models trained by the proposed approach are empirically found to match and in some cases outperform the baseline models with a small vocabulary as well as the LSTM based neural machine transition models. Furthermore, when we use an ensemble of a few models with very large target vocabularies, we achieve performance comparable to the state-of-the-art measured by BLEU on both the English to German and English to French transition tasks of WMT14. And as we said, you can feel free to explore the rest of the paper. So this was the paper that scaled up the vocabulary size that was commonly used for 30,000 to 80,000. They scaled it up to nearly about 500,000 vocabulary size. Let's dive into replicating the paper on using very large target vocabulary for neural machine translation by Jean, Cho, and Yeshua Bengio et al. 2015. The paper tackles the scalability issue of neural machine translation NMT with large vocabularies. So let's dive straight away into the code. First, we need to import and get the required libraries and necessary libraries. Here we have import torch for tensor operations, import torch.nn as nn for building different neural networks building blocks, and then import torch.optim as optim for optimization strategies, import torch.nn.functional as f for loss functions and activations, import matplotlib.pyplot for visualizations and making plots, and lastly import random for randomness and generating random numbers. Then we have here device checks if a GPU is available. If yes, runs on CUDA, else runs on a CPU. This is as an analogy. Decide if you want to boost your speed up or just run with a normal CPU. Then we have a toy dataset that we have created earlier. We have a toy dataset English to French. You can see we have a list that contains several pairs English sentences paired with French versions. So here I am a student. The English version is mapped to French version, G, Swiss, and student. He is a teacher. It gets mapped to a French version, Il est un professeur. So a tiny parallel dataset, English to French, to train the model on. In research, this would be replaced by WMT14 dataset with millions and millions of examples. But here we have a small scale dataset. After that, we have a tokenize function. You can see it's just as simple as it is. Def tokenize, it's called tokenize to segment the text. Then we pass the sentence and it returns that same sentence but turned into a lowercase using the .lower function. Then we split to tokenize it. So it takes from me a sentence, then it returns that same sentence but lowercase and split it, or broke down into small units, small subsets. Then we have here source vocabulary, and we have the target vocabulary. You can see we have the source vocab equals padding. Padding gets mapped to 0. SOS, start of sequence. EOS, end of sentence. And UNK, unknown word, gets mapped to 0, 1, 2, 3 respectively. Then we have a for loop. You can see for source and target in pairs. So for each source sentence and target sentence, for each token in tokenized source, so we will use our function tokenize and pass the source sentence. So we will loop through these sentences. For example, this sentence, we play football, we will tokenize it, and then for each token, if this token not in the source vocabulary, then do the following: source vocab token equals the length of the source vocabulary. For each token in tokenized target, the same. If token not in isn't existing in target vocabulary, which is this, then do the following: target vocabulary at index token, set it to the length of target vocabulary. Then we have the inverse, which is for a dictionary comprehension. For each k, v in target vocabulary in items, for each key and value in this target vocabulary items, let's map v to k. After this, we have the encoder class. You can see here we have encoder class that inherits from NN.module. So here we have an embedding layer, converts token IDs into dense word vectors, and then we have bidirectional GRU. You can see reads the sentence forward and backward, like reading both ways for full context. At the last, we have a linear layer, compresses the two directions into one hidden state. So here we have an embedding layer that maps the input dimension into the embedding dimension. After that, we have another RNN layer, which is in this case the GRU, gated recurrent unit, that applies two gates that maps embedding dimension to the hidden dimension, and then set the bidirectional property to true to handle the text and to process the text from both directions, left to right and right to left, to learn more rich representations. And then we have fully connected layer, which is a simple linear that maps hidden dimension times 2 into the vocabulary, into the space of hidden dimension. Now we have defined the components, the elements, the items separately. Let's call them in the for method. So here we have, as you can see, this is the for method, collects the last forward state and the last backward state, combines them and squashes them with tanh. This is the sentence summary vector. You can see here we are combining or concatenating the forward time step or the forward state and the last backward state at the dimension 1, and then we are squashing them with tanh function, and then we store it in the variable hidden. Then finally we return outputs alongside with the hidden dot unsqueezed 0. After this, we have an attention mechanism. Class attention, we name it as attention. You can see the A is capital, Pascal case. Then it inherits from NN.module, the base class in PyTorch for building neural networks models. Attention compares the decoder hidden state with all encoder outputs. The decoder hidden state will attend to every single encoder output. After that, you can see here we have a simple linear layer with the properties self.v equals set into nn.linear. Heading dimension, we map it to 1, bias equals false. Then we have a forward method. You can see here we have the forward method torch.tanh, then self.attention, torch.cat, concatenate hidden, encoder outputs. So all we're doing here is that we are concatenating the hidden alongside with the encoder outputs at the dimension 2. Then we are applying the attention mechanism on it. Then we squash it with the tanh value, with the tanh function. Then we store it in the energy variable. Then we have the attention variable equals self.v, and then pass energy dot squeeze at index 2 dot transpose 0, 1. Energy equals the similarity score between the encoder and decoder. Softmax gives attention weights across source tokens. the analogy in here, at each step, the decoder decides which English word to look at most, which English word to focus on most. After that, we have the decoder class, decoder, which combines GRU plus attention. So here we have self.rnn equals nn.GRU, the gated recurrent unit layer that takes from me the in features as hidden dimension times 2 plus embedding dimension, and then map it to the hidden dimension. So decoder uses embedding of the current word, then it finds the context vector from attention, then we have the previous hidden state. So we have a GRU layer that takes from me hidden dimension times 2 plus the embedding dimension, comma, it maps this input features to the output features, which is the number of hidden dimensions. Then we have this RNN that we will use later in the forward. Here we have a linear layer, which is called fully connected output, that will generate the tokens that takes from me hidden dimension times 3 plus the embedding dimension, and then it maps this to the output dimension. Finally, we have self-attention equals the same attention that we have initialized earlier. Then after that, in the forward method here, you can see we have predicts the next French word. We have a large vocabulary bottleneck, normally vocabulary 100,000 plus words, huge softmax layer. But here in this paper, Jean et al. Suggested importance sampling. The importance sampling based approach only compute over a subset of candidate words. Here, candidate subset simulates that trick. So here we have this strategy, which is if candidate subset is not known, then logits equals logits. Then we slice here. You can see we have colon, comma, candidate subset. Then we return the logits, comma, hidden, the computed logits alongside with the hidden. And as we said, here we have this function BMM, which is batch matrix. Matrix takes from me this array, and multiply it by the encoder outputs dot transpose. We have to transpose it by this dimensionality 0,1. Then dot transpose on the outer side by 0,1. And then we have this concatenation. We concatenate or combine the embedded representation with the context at dimension 2 and store it as RNN input. So this is the main idea behind the forward method. Let's move on to the sec-to-sec class. So now we have the sec-to-sec class. As you can see, sec-to-sec wrapper. We start by defining the class and calling it sec-to-sec, sequence to sequence. It inherits from NN module. Then we have this encoder. Encoder, we initialize it, and the decoder, we initialize it. As you can see, we are passing the encoder and decoder as parameters, then storing them inside these properties. In the forward method here, runs the encoder, starts the decoder with SOS, starts of sentence, then step by step apply attention, predict next word, and then we do teacher forcing, sometimes use ground truth, sometimes use prediction. This loop is the translation process in action. So here we start step by step. First we run the encoder. You can see we run the encoder, self.encoder, then pass the source sentence. The source sentence gets processed by the encoder. The encoder tries to understand and gets an internal rich representation of the source, then store its outputs inside the encoder outputs with the hidden state. Then we pass this, the output with the hidden state, we pass it to the decoder alongside with the input for the decoder to be able to generate and to talk freely. Then the decoder will produce output in addition to hidden. Then we do some teacher forcing steps, as we said, randomly. So random with random, we will generate random numbers. If this random number is less than the teacher forcing ratio, then it will apply the teacher forcing. Otherwise, it will not apply the teacher forcing mechanism. So here, teacher forcing, sometimes use ground truth, sometimes prediction. And here we have an if condition, target at t. If teacher force, else use the top one. Then we return outputs. So this is the sampling, the importance sampling based approach. Then we have the model. Here you can see we have some hyperparameters, input dimensionality, output dimensionality as length of source vocab, length of target vocab. Then we have the encoder embedding, decoder embedding, hidden dimension as 64, 64, 128. So here we will initialize these hyperparameters with the default values. Then we have attention. Let's initialize it and instantiate a new object from the attention class, pass the hidden dimensionality, and also we have the encoder equals the encoder class, and pass into here the input dimensionality alongside with the encoder embedding and the hidden dimension dot to device. We need to move this encoder to the target device. The same goes for the decoder. We pass the output dimension, decoder embedding, hidden size, and then the attention dot to device. Then we instantiate a new model sec to sec, pass the encoder that we have created, the decoder that we have created earlier, dot to device. So here we are initializing the model alongside some important hyperparameters that we need to initialize with these values. You can see the encoder embedding is 64, decoder embedding 64, hidden size is 128. You can fine tune and play around with these values as you can. You are more than welcome to try different values. Then we have the optimizer, the add optimizer. As you can see, optimizer equals add optimizer, torch.optim.addom. We pass the parameters that we need to optimize and fine tune using the add optimizer, and we set the learning rate as 1e minus 3. Then the criterion, the loss function that will compute how far the model's predictions are to the ground truth. Here we have nn.cross entropy loss, ignoring padding tokens using ignore index equals target vocabulary padding. So we need to ignore the target vocabulary padding. Why? We don't need to account for it in the loss function cross entropy loss. Here we have the same idea of the training loop. You can see def train model. It takes from me the number of epochs. Feel free to play around with the number of epochs. N epochs equals 30. Then we have the losses. Here we have an empty list. Then for epoch in range n epochs. So now we are looping through the number of epochs, whatever it was, 30, 50, 100. Then we need to set the mode of the model into training mode via model train. This is the first step. The second step is initialize the loss as 0. Then increment the loss as we go. Then we have a for each source sentence and for each target sentence in pairs, go ahead and train the model on them. So for each source sentence and for each target sentence, loop through them and train the model. Here we have source tensor and target tensor, where we encoded these source and target tensors, encoded them via the encode function. Then we added a batch dimension for compatibility issues for the model. Then we moved this data to the target device because the model lives on the GPU or on the CPU, and the model will not have access to the data if the data is in another different GPU or CPU, or is in another different hardware. Then we have the optimizer with 0 grad. It's best recommended to 0 the gradients of the optimizer. Then here we have the model and then pass forwardly the source tensor and the target tensor. We do a forward pass. The model here will do a forward pass with random weights. It will produce lots of errors. Then we will take this output and compare it with the ground truth here, target tensor, and the loss function, the criterion, will compute how far does this output from the target tensor. This is the loss calculation. The loss calculation. Based on this loss calculation, we will apply the back propagation via this function, loss backward. Then we apply the optimizer step, which will trigger Adam to update the weights. After this, you can see here we have total loss, the total amount of loss. We increment by the loss.item. So we take the loss value, because it's a tensor, we just need the scalar value. We do not want the brackets. So we take dot item. We just need the scalar value. So instead of being like that, a tensor of 0.12, it will be like that. 0.12. So a scalar rather than a tensor. Dot item. At the end, we have here average loss. We will divide the total loss by the length of the pairs, and then append that average loss every time to the losses list, and every epoch we will print the loss. So loss as average loss dot 3. We will take the first 3 decimal places and then return losses. Here you can see we have the training results. Epoch 1, the loss started as 3.0, and then the loss started to decrease, as you can see, decreasing or getting lower and lower. And this epoch 7, we have 0.7. Epoch, for example, 15 or 16, we have the loss 0.06, and it keeps getting lower and lower. It keeps decreasing and reducing until we have the epoch 30. The loss is now reduced. We have 0.01. and then we will plot that losses using the plt.plot function and pass the losses list. As you can see, the loss now is decreasing, reducing, and getting lower and lower. So over time, the loss is getting lower or decreasing. Then we have this same function, translate, takes from me sentence and maximum length as 20. Then we set the model into evaluation mode. As you can see, the evaluation mode turns off gradient tracking, turns off the backpropagation, turns off the optimization of the function, the optimization of the model, just keeps the inference mode. Then we have here torch.tensor. We pass the encode function to encode this sentence and turn it from raw text into a representation that the model can deal with. Then we have source vocabulary dot unsqueeze to add a batch dimension. The same idea, we will use the encoder. We will leverage the encoder to process the source tensor. Then we have the encoder outputs alongside with the hidden. After this, you can see here we are starting with SOS special token, start of sentence. Then we move it to the target device, and then we have the outputs as an empty list. Then we have for underscore in range maximum length. We are looping through the maximum length here, which you can define as any number. For each loop here, we will go ahead and use the decoder, pass the input, this hidden variable, encode the outputs, this that we have gotten from the encoder, pass them to the decoder to be able to guide the decoder. Then the decoder will be able to give us output. Then we will return the index with the largest value via the argmax function, and then we will check if top1.item equals target vocabulary end of sentence, then break off the loop and get out of it. Otherwise, output should append. We need to append or to add the inverse target vocabulary top1.item, and then input equals top1. At the end, return string.join outputs. This outputs list will be populated. This list after this loop will be populated with a lot of tokens. At the end, we will convert it from a list format into a string format by using the join method. Then we show transitions by towing the set. As you can see, for source and target in pairs, go ahead and translate every single source. So here we are looping through the source and target in pairs. For every single source and target, go ahead and pass the source sentence into the translate function. This function will work and encode this source sentence, pass it to the encoder. The encoder will understand and pass the understood representations into the decoder. The decoder will try to generate the corresponding values or the corresponding sentence. You can see here we have the source, I am a student. The prediction here is Swiss and intuitant. Then the target, here you can see detect language. We pass the prediction. We can get rid of this prediction word. You can see here we have Swiss and intuitant, and the target is Swiss and intuitant, which means both I am a student, I am a student. So the model successfully, correctly translated from French language into English language. Our model can translate properly and successfully, and the rest for other sentences. So here we can take the sentence est un professor, which means he is a teacher. You can see he is a teacher, he is a teacher. So the model can successfully translate the targets, the source sentences into the corresponding target sequences. So this was the replication of the paper on using very large target vocabulary, but on a small scale, because we don't have that much computing power and we don't have access to very large datasets. Let's discuss the paper Effective Approaches to Attention-Based Neural Machine Translation by Luong, Pham, Christopher Manning, 2015. This paper systematically explores and evaluates architectural variants of attention mechanisms in neural machine translation, NMT. The authors proposed two key models: global attention, where the decoder attends to all source words, and local attention, where the decoder selectively attends and focuses to a subset of source words. Additionally, they introduce an input feeding approach to incorporate past alignment decisions. Experiments on English German WMT tasks show that these attention models improve translation quality by up to 5 BLEU over non-attentional baselines and establish new state-of-the-art results 25.9 BLEU in WMT15 English to German. So the main contributions here, or the key contributions here, is that they explored and evaluated architectural variants of attention mechanisms. Second, they introduced the global attention, where the decoder attends to all source words, and local attention. The other type of attention is called local attention, that selectively attends to a subset of source words. Additionally, they introduced this idea of input feeding approach to incorporate and to inject past alignment decisions. Experiments on English German WMT tasks showed that these attention models improve transition quality by up to 5 BLEU over non-attentional baselines. What are the problems that they faced? Well, the first problem, previous NMT neural machine translation attention models like Bahdanau et al. 2015 lacked exploration of alternative architectures. So they lacked exploration of alternative and other architectures. The second problem, global attention requires attending to all source positions at every decoding step, which is computationally expensive. Third, existing models didn't effectively capture coverage of alignments across translation steps, leading to over or under translation. Fourth, unclear which alignment functions dot, general, concat, location work best for NMT. So the problems, in short, previous neural machine translation attention models lacked exploration of alternative architectures. Second, global attention requires attending to all source positions. Third, existing models didn't effectively capture coverage, all the coverage of alignments across transition steps. And fourth, unclear which alignment function, whether it was dot or general or concatenation or location, work best for NMT. The proposed solutions here is the global attention. So the first solution here is that they introduced the concept and the idea of global attention that attends to all source positions when predicting each target word. Second, local attention focuses on only a small window, a small subset around a predicted source position. Local M assumes monotonic alignments, and we have local P. So these are the two types of local attention. We have local M and local P. Local M assumes monotonic alignments. Local P predicts alignment positions dynamically via a learned function combined with Gaussian weighting. 3. Input feeding approach feeds attentional context vectors into subsequent decoding steps to inform future alignment decisions. 4th, systematic comparison of alignment functions, whether it was dot or general or concatenated or location, to identify optimal scoring methods. So in short here, they introduced global attention, local attention, input feeding approach, and systematic comparison of alignment functions. They compared between dot, general, concat, location, and which one of these methods best suits with the attention-based models to identify optimal scoring models. Purpose. What are the purposes of this proposed solution? 1. To investigate how different attention architectures affect neural machine transition performance. 2. To improve efficiency, accuracy, and alignment quality in neural machine transition systems. 3rd, to move beyond the single Bahdanau style attention model and establish design principles for future NMT attention mechanisms. The methodology they used here, first we have datasets. So which datasets did they use? Well, WMT 14 English to German, 4.5 million sentence pairs, 116 million English, and 110 million German words. 2. Vocabulary limited to top 50,000 most frequent words. Architectures. 4-layer stacked LSTMs with 1,000 hidden units each. So they stacked 4 layers, deep LSTMs, with 1000 hidden units in each layer. Second, embedding size 1000. Third, trained with SGD. Dropout. We have the dropout. Dropout is a technique that reduces the risk of overfitting by emitting or dropping out some randomly neurons. So dropping out some neurons to prevent feature kill adaptation. And then we have gradient clipping, and also the idea or the data pre-processing system, the data pre-processing technique, which is reversing source sentences. So the architecture is stacking 4-layer stacked LSTMs with 1000 hidden units each. Second, the embedding size is 1000, so each sentence is get embedded into a vector of 1000 elements. And also we have trained with SGD dropout with probability of 0.2, meaning 20% of the neurons will be dropped out. Gradient clipping, and also we have reversed source sentences. Evaluation. Tokenized BLEU comparable with NMT work. Second, NNest BLEU for WMT official results. Also evaluated alignment quality with alignment error rate AER. Comparisons. They compared their proposed model against phrase-based SMT baselines. Also, they compared their proposed model with against Bahdanau et al. 2015 and Jean et al. 2015 attention models. Results. English to German, WMT 14. The base model, reverse plus dropout, so they used the technique of reversing the sentence. Why? To shorten the range dependencies, to learn short dependencies. BLEU 14, and also to ease the optimization, to ease and improve the optimization and gradient based optimization. Second, we have global attention, BLEU 16.8. So the base model, its score is 14, but the global attention, its score 16.8. So you can see the improvement rate. Then we have input feeding. The BLEU score is 18.1, so better than global attention. Then we have local P attention, BLEU 19. So the local P attention is better than the input feeding. As you can see, input feeding is 18.1, but local P attention is 19. Unknown replacement. If you replace the unknown tokens, then we will have a 20.9 BLEU score. Ensemble, 8 models. If you combine and merge 8 models, ensemble models, the BLEU score will be 23.0, which is SOTA, state of the art at the time, 23. English to German, WMT 15. Ensemble plus unknown replacement. The BLEU score is 25.9, surpassing prior SOTA 24.9. German to English, WMT 15. Base, reverse, the BLEU score is 16.9, and the base model, so here the baseline model is 16.9. As we mentioned earlier here, the baseline model is 14. But here the best model is global dot plus dropout plus feed plus unknown. The blue score here is 24.9, approaching SOTA or state of the art, which is 29.2. Qualitative. Attention improved translation of rare words and proper names. So attention improved the translation performance of rare and unseen words and proper names. Better performance on long sentences. Better performance on long range dependencies, addressing a major weakness of non-attentional NMT. Alignment error rates, AER. Local attention, which is 0.34 to 0.36, comparable to Berkeley aligner, which is 0.32. Conclusions. Both global and local attention mechanisms substantially improve NMT, with local predictive attention offering efficiency and interpretability advantages. Second, the input feeding approach enhances coverage, preventing repetition or omission in transition. So the input feeding approach is similar or analogous to the residual connections in CNNs. What is the purpose of a residual connection? Residual connections are a way to inject the raw signal, the raw and identity signal, to the later and deeper layers. Why? The residual connection, think of it as it tells the later layers, don't forget what you need to see. Don't forget who you are. Don't forget the identity, the real identity of the image. So you need to remember what the real image looks like, plus the transformed or the transformed version of the input. Here we have the input feeding approach that enhances coverage. Also, the input feeding, think of it as a way that tells the RNN here, or tells the attention-based model, do not forget what you paid attention to. Don't forget what you learned contextually. So you need to align and to remember what you previously learned and gained from information. So the input feeding approach enhances coverage, preventing repetition or omission in transition. Different alignment scoring functions yield different strengths. Dot product works best for global models, general for local models. Attention-based NMT systems not only outperform earlier non-attentional baselines, but also rival and surpass traditional SMT, statistical machine translation. This work established a systematic framework for attention in neural machine translation, laying the groundwork for later developments such as multi-head attention in transformers. Here, this paper marked a tuning or a turning point. It transformed attention. It refined attention from a single experimental idea, which is Bahdanau et al., into a systematic framework for neural translation by introducing global and local attention and the input feeding mechanism to preserve the contextual vector. It crystallized design principles that shaped all later models. Its careful analysis proved that attention wasn't just a hack, but a foundational paradigm, paving the road directly to multi-head attention and transformers. Effective approaches, we have this paper, it's called Effective Approaches to Attention-Based Neural Machine Transition by Min Thang Luong, Hugh Pham, and Christopher D. Manning, 2015. Introduced global versus local attention, input feeding, alignment function comparisons. So they compared between the different alignment functions, dot product, general. By analyzing global and local attention models, this work showed how different attentional mechanisms improve translation, setting the stage for the evolution of modern sequence architectures. And here we have the paper. So feel free to read the paper in your own time. View in line. So as you can see, this is the paper from Stanford University. If you scroll down, we have this abstract. An attentional mechanism has lately been used to improve neural machine transition NMT, as we've seen in Bahdanau et al., by selectively focusing on attending on parts of the source sentence during translation. However, there has been little work exploring useful architectures, useful variants, useful other types for attention-based neural machine translation. This paper examines two simple and effective classes of attentional mechanisms: a global approach, which always attends and focuses to all source words and computationally expensive, and a local one that only looks at a subset, only looks at some small subsets of source words at a time. We demonstrate the effectiveness of both approaches on the WMT translation tasks between English and German in both directions. With local attention, we achieve a significant gain of 5 blue points over non-attentional systems that already incorporate known techniques such as dropout. Our ensemble model, using different attention architectures, yields a new state-of-the-art. So the ensemble collection yields a new state-of-the-art result in WMT 15 English to German translation task with 25.9 blue points, an improvement of 1 blue points over the existing best system backed by the NMT and Ngram re-ranker. And here you can feel free to read through this paper. So the idea here, if you read here, neural machine translation, a neural machine translation system is a neural network that directly models the conditional probability, which is the probability of y given x of translating a source sentence. Given the x's to a target sentence, it generates or predicts the y's. A basic form of NMT consists of two components: an encoder, which computes a representation for each source sentence, and a decoder, which generates a target, one target word at a time, and hence decomposes the conditional probability. And you can see here they have these diagrams. Here we have this diagram, which is really illustrative. Global attention model. At each time, step T, so at each time here, step T, the model infers a variable length alignment weight vector. So we have a weight vector A based on the current target state H and all source states. And then we have here global align weights. As you can see, a global context vector C is then computed as the weighted average according to A over all the source states. So here we have C, which is a global context vector C, and then we have this attention layer that attends and focuses on relevant parts. Then we have, based on this hidden state, it generates the output. And you can see here we have the context vector, which is C, based on global align weights. And if you scroll down, they also have this diagram, as you can see, or another. Here we have local attention model. The model first predicts a single aligned position P of T for the current target word. A window centered around the source position P is then used to compute a context vector C, a weighted average of the source hidden states in the window. The weights alpha are inferred from the current target state H, and those source states are in the window. Here you can see that we have local weights. So then we have global weights, if you recall in this image. Here we have global align weights, while in this second diagram we have local weights. Then we have align position, context vector, then we apply an attention layer, and then it generates an output Y. And here you can read the experiments. We evaluate the effectiveness of our models on the WMT transition tasks between English and German in both directions. And also, if you scroll down, here they have the training details. For example, here, if we read here, we limit our vocabularies to be the top 50,000 most frequent words for both languages. Words not in these shortlisted vocabulary are converted into a universal token called unknown. When training our NMT systems following Bahdanau, we filter out sentences pairs whose lengths exceed 50 words and shuffle mini batches as we proceed. Our stacking LSTM models have 4 layers. So these are the details about the model and training. Have 4 layers, each with 1,000 cells and 1,000 dimensional embeddings. We follow Sutskever in training NMT with similar settings. Our parameters are uniformly initialized in between -1 and +1. We train for 10 epochs. Here they said we train for 10 epochs. And as you can see, here we have this table. And if you scroll down to the last, you can see here the image. Here we have the English language and get translated to German language. And if you scroll down, you can see here alignment visualizations. Shown are images here. You can see, if you scroll up, these figures now shown are images of the attention weights. So these are the attention weights learned by various models. Top left, the global. So this is the global model, the global attention model. Local M, the top right is local M. So this is the top right. At the top right hand corner, here we have the local M, and bottom left we have local P. The gold alignments are displayed at the bottom right corner. So you can see these are the gold alignments displayed at the bottom right corner. Here we have the English language, and it gets mapped to German mappings or German alignments. So now we've finished discussing this paper, which is really crucial. They redefined what attention is. Attention in the Bahdanau paper was a single idea, but here they formalize attention as a whole framework. Effective approaches to attention-based neural machine transition, Luong, Pham, and Manning. 2015. Let's dive into replicating the paper, Effective Approaches to Attention-Based Neural Machine Translation by Luong, Pham, and Manning, 2015, Stanford NLP Group. Let's dive into the coding. So the first thing, we need to require or import the necessary libraries. Import Torch, Torch with NN as NN, Torch with Optim as Optim. So we import Torch, the PyTorch library, then we import NN, the building blocks, layers, activations, losses. It contains many other building blocks for building neural networks. Then we have Optim, optimizes like Adam, SGD, etc. Then we have Matplotlib and NumPy for visualizations and dealing with NumPy arrays. Then we set device. If a GPU is available, use CUDA. Otherwise, use CPU. Think of this as checking. Do we have a graphics card accelerator, or should we run on the regular CPU? Now let's dive into the encoder class. So we have a class encoder that inherits from NN.module. NN.module, all PyTorch models inherit this. So every single PyTorch model must inherit from NN.module. All PyTorch models inherit from this. Then we have self.embedding, turns word IDs into word vectors, dense, meaningful numbers. Self.RNN, a bidirectional LSTM, it reads forward, left to right, and backward, right to left, like listening to a sentence twice, both ways. So here we have the LSTM layer and the embedding layer as components. Now we need to call them in the forward method by going def forward and then pass self to denote that this is a method, comma x. X is a batch of token IDs, Then we call self.embedding and pass the x. So emb is lookup word embeddings. Then we have outputs, which is the hidden state at every word used for attention. Then we have hidden, comma cell, which is the final summary states. We return outputs, comma hidden, comma state, hidden, comma cell, which is the final summary states. Outputs is a memory of each word. So outputs represents a memory of each word, while hidden and cell is a compressed memory or compressed summary. After this, we have the global attention class. So we start by going class, we name it global attention, and it inherits from NN.module. Takes bidirectional LSTM output, 2 times hidden size, and projects it down to hidden size. So here we take the hidden size times 2, then we project it down to hidden size, and we set the bias to false to prevent the bias term. After this, we have a forward method. In the forward method, we have encoder projector, reshape encoder outputs. So it's a normal linear layer, which acts as an encoder projector, reshapes encoder outputs. Then we have scores, the dot product scores, which gives us the similarity between the decoder's hidden state and each encoder output. After this, we have the attention weights, which is a softmax function that gives me or results in probability distribution over words. Then we have context, which is the weighted sum of encoder outputs, which results in the focused meaning, the focus on the most relevant parts. It's like shining a spotlight on all words, brighter where it matters more. The next step is we have the local attention class. As you can see, we have class local attention, and it inherits from NN module. Instead of scanning all words, it predicts a position PT, the most relevant source word. Window only look at a neighborhood around PT. So we have WB, which is a window, which is a linear layer that projects the hidden size into the same hidden size space. And then we have VP, which is another linear layer that projects the hidden size into one neuron. Then we have the forward method to combine these windows. As you can see, we have here predict an alignment position. We have B, comma T, comma H equals encoder outputs dot size to get the size of the encoder outputs and unpack its values to B, T, H, batch size, and then the sequence length, and then the H. Then after this, which is the hidden state. After this, here we have the context, comma weights equals empty lists. Then we have for B in range B, P equals integer PT at index B dot item. This slice a local window around PT, so it does a slicing, then computes scores and attention only inside the window. It computes the attention and scores using the matrix multiplication, then get context vector like zooming in with camera lens instead of scanning the whole photo. And as you can see, we matrix multiply the window by the hidden at index P and store its value in the scores variable. After this, we normalize the scores by passing the scores into the softmax function, and it will normalize these values and pass into the window or store it in the window in the W variable. After this, we have the matrix multiplication function to multiply the W by the window and store it in the C variable. Then we append the C into the context and append W into the weights, and finally we return them back. The next step is we have decoder with attention. Here we start by class, the keyword class, then name it as decoder with attention that inherits from NN.module. Embedding, convert predicted token into a vector. Then we have RNN, which is input, word embedding plus context vector. We combine the word embedding with the context vector. After this, here we have the fully connected layer, predict next word from output plus token plus context. So based on the output combined with the context, we combine them and predict the next word. Then we have attention layer, plug in either global or local attention. Then we execute them inside the for method. So take one word at a time. Here we take one word X, and then we unsqueeze X, add a batch dimension. Then we pass this X, this new X, with the new batch dimension into the embedding layer to convert or represent this X into very rich representation vector. Then we pass this embedding size into the attention layer, as you can see, get attention context. After that, we concatenate word. We concatenate the word plus the context and feed to LSTM. The LSTM applies the gating mechanism, the forget gate, input gate, output gate, the candidate memory, and predict the next word. Pass it to the fully connected layer, then it will predict the next word. Think of the decoder as the French speaker who glances back at English words with attention before speaking. So here you can see we have the torch.concatenation. We concatenate or combine output plus the context vector at dimension equals 1. Then we pass it to the fully connected, and then the fully connected layer will return the predictions. Then we return predictions alongside with the hidden state and also in addition to the context vector and the attention weights. After this, let's move on to the sec-to-sec wrapper. Let's combine everything together. Let's put everything together. By going, you can see here, sec-to-sec, the encoder or ties encoder plus decoder together. Then we have a for method. You can see here, we have self, src, target, teacher forcing equals 0.5. Source is English, target is French. Then we have the pre-allocated storage for predictions by going enc out, hidden equals self.encoder and then pass source. So run encoder, then combine forward plus backward hidden states. After this, we need to slice on the target by going target 0, colon, 0, and then this is the input. And as you can see, we have the context equals torch.zeros. We initialize a 0 sensor and pass it to here b, hidden at index 0 dot size 1. We need to get the size at index 1, then we move it to the target device dot to self dot device. At the end, we loop through the range of 1 until t. Then we execute the decoder or run the decoder. The decoder returns output vector, hidden vector, context vector. Then we slice on the output equals out, and at the end we return the outputs, as you can see. And here the input is simply if torch.rand1.item is less than teacher forcing. So if it is less than the teacher forcing, then use this. Otherwise, use out.argmax, and at the end, please return the outputs. So decode step by step. Then we have teacher forcing. Sometimes use ground truth. Sometimes use models guess. So sometimes use the ground truth. sometimes use the guess, like letting the student practice with hints 50% of the time. Let's move on to the datasets. So the dataset here is a small, tiny dataset used for play around with the model. You can see we have pairs, we have English sentences mapped to French sentences. So we have English pairs mapped to French pairs. We define tiny English to French pairs, build vocabularies with padding, start of sequence, end of sequence, and unknown, and decode into tenses. Decode it at the end into tenses and retain it. This is our mini parallel corpus. And here simply we build the vocabulary. As you can see, we call the function and pass here a list comprehension. Here we emit the French language, and here we emit the English language. Then here we have inverse target vocabulary, which we invert by looping through for token comma index in this target vocabulary. Let's inverse this. Let's make the I first and maps to the T second. Then we have this encode function that starts with the special token SOS, then concatenates with the tokens and also the unknown token, then ends with the end of sentence, and then we pad the rest of the tokens or the rest of the sentence to fill. At the end, we return torch to tensor indexes. And here we call these functions the encode function twice for the English and for the French. And then we stack them together and store them in these variables: source tenses, the English version, and target sentences, the French version. After this, let's go to the training details. So here we have embed size, comma hidden size equals 32, comma 64. Then the attention equals global attention. We instantiate a new object from the global attention class and pass into here the hidden size, as you can see. So swap the local attention if you want to use local attention. And by the way, in the paper that they find that local attention is more effective and more efficient than the global attention. Then we instantiate the encoder. As you can see, we have encoder and pass these hyperparameters and move this encoder to the target device. The same idea for the decoder. We instantiate this decoder with attention, and we pass these hyperparameters. Then we send this decoder to the target device for the model to be able and compatible with the data. Then we have the model sec to sec. We initialize a new sec to sec object and pass these hyperparameters. We pass the encoder, this encoder, decoder, and we pass the device. Then we move this actual model to the target device. After that, we have the criterion, the loss function, which is cross entropy loss function. And we pass ignore index equals 0. And also we have the optimizer equals Adam optimizer. The Adam optimizer, we pass in the model parameters for Adam to be able to modify them, to fine tune the weights, to update the weights, to better represent the data. Then we have learning weight equals 0.01. So we have cross entropy loss for classification at each word, and we have ignore padding tokens via ignore index equals 0, and the optimizer is the Adam optimizer, learning weight set as 0.01. Then we have a small tiny training loop. You can see for epoch in range 200, run for 200 epochs, then do a forward pass. You can see here we are doing a forward pass, and this we are taking the model, passing the source sentences alongside with the target tenses and giving them to the model. We tell the model, this is the English version, this is the French version, learn the mappings. Then the model will try to learn the mappings, how to map these words to these words, and will give me a result output. Then we take this output and judge it via the criterion loss function, compare it with the ground truth. Here you can see the target tenses. Then we do backpropagation, optimize a step to trigger Adam to optimize and fine tune the weights. At the end, for every 50 epoch, we print the results. So we backpropagate, update weights, print progress every 50 epochs. This is the study session where the translator improves. As you can see, epoch 50, we have the loss 0.005, and epoch 100, we have the loss 0.0014. Epoch 150, the loss is 0.0009, and after all the training has done, at the very last epoch 200, the loss is 0.0006. the lowest possible loss. Then we have the translate function. This function is simply translating the sentences. So switch to evaluation mode. We first switch the model mode into evaluation mode. Encode input English. By going encode, we take the sentence. So here we need to provide the function with a sentence that you would like to translate, the sentence of interest, the model, the trained model, then source vocabulary, target vocabulary, inverse signing vocabulary, and we have the maximum length. We have to encode this sentence. So you pass sentence into the encode function and pass the source vocabulary. Then we unsqueeze to add a batch dimension, because the model will not succeed when handling with unbatched sentences. It must handle with batched sentences. Then we move it to the target device. After that, we initialize or we inject a start of sentence token. First, we inject an SOS special token. After that, we have the model.encoder. We pass this source sentence into the encoder. The encoder will try to find the patterns, will try to understand the hidden representations, and then will provide me with an encoder output and the hidden state. After that, we combine the hidden state with the second hidden state here, because we need to combine the forward pass with the backward pass, because we are processing the text in both directions, from left to right and from right to left. And at the end here, we initialize the context vector with the zeros, and then you can see we have 4 in range maximum length. We loop through that, and then for each loop here, we are taking the X alongside the hidden, in addition to the encoder output and context, and provide the decoder. The decoder will be able to walk through and generate. Then the decoder will give me output alongside with the hidden and context. And then we will take the index of the largest value via the argmax function. We apply argmax on the output, and then it results in a prediction. This prediction we will return if prediction equals target vocab, end of sentence, then break the loop and get out of it. At the end, we convert this list, which contains the tokens, we convert it into a string format. So string.join, then we pass into here for each index in the target index, which is this list that is populated with the tokens later here in this for loop. If I isn't in this list, then give me the inverse target vocabulary at index I. And at the end, we call this function, this nice function, translate, and pass I am a student, she loves music, and magically the model has learned how to map English version sentences into French sentences. So we can see here, let's take I am a student, or the French version, which is G, Swiss, and étudiant. And if you take them, Control C, and paste them in Google Translate, you can see here, detect language. It will detect that this is a French language. This is a French language, as you can see, and it translated it into the English language. I am a student, she likes music. So you can see we have successfully trained the model to map English version sentences into French sentences. So this was the idea behind replicating the paper, effective approaches to attention-based neural machine translation in PyTorch. Let's discuss long short-term memory networks for machine reading by Cheng, Dong, and Lapta, 2016. This paper introduces a machine reading simulator, a neural model that processes text incrementally while leveraging memory networks and attention to enhance reasoning over sequences. By replacing the standard LSTM's single memory cell, so they replace the LSTM's single memory cell with a memory tape and embedding intra-attention. The model LSTMN, short for long short-term memory network, learns to induce token-level relations and token level correlations and saw richer contextual information. Experiments in language modeling, sentiment analysis, and natural language inference demonstrate that the approach matches or outperforms state-of-the-art baselines. So as we discussed earlier, attention mechanism is a machine learning mechanism or machine learning technique that directs deep learning models what to prioritize or what to pay more attention to and focus on the most relevant parts. As their name suggests, the attention mechanism are inspired by the fact that humans or animals pay more attention to specific parts and ignores the less important details, making that learned information more richer and more robust. Problems. What problems did they face? Vanishing, exploding gradients in RNN training. So the problem of vanishing or exploding gradients in traditional RNN recurrent neural networks, limiting their ability to handle and model long-range sequences or long sequence learning. 2. Memory compression. Standard LSTMs collapse long sequences into a single vector, hindering generalization. 3. Lack of structural bias. Sequence models ignore latent syntactic semantic relations among tokens. So in short, the problems are vanishing, exploding gradients in traditional RNN. 2. Memory compression, because remember, LSTMs collapse long sequences into a single vector. That means you will encode, this will cause a bottleneck. That means you will encode long sentences and short sentences into the same amount of details, hindering generalization. Lack of structural bias. Sequence models ignore latent syntactic semantic correlations and relations among tokens. What are the proposed solutions to solve these problems? The first solution is that introduce long short-term memory networks, LSTMN, for machine reading. Replace single LSTM memory cell with a growing memory tape. So now we have a growing and evolving memory tape. Second, add an intra-attention mechanism. So intra-attention mechanism is a self-attention mechanism to selectively retrieve relations between tokens, to selectively attend to and pay more attention to those important relations between the tokens. Third, store contextual representations without recursive compression. So without recursive compression, we now store contextual representations without the need to recursively compress the data. Third, extend the framework to encoder-decoder architectures with shallow and deep attention fusion for sequence-to-sequence tasks. So in short here, the solutions are introduce the LSTM network, and second, extend the framework to encoder-decoder architectures with shallow and deep attention fusion for sequence-to-sequence learning. Purposes. What are the purposes of this solution? Number 1, to design a neural machine reader capable of simulating human-like incremental text comprehension. So the idea of LSTMN is to build a machine reading system that incrementally process data or process text. 2, to enable recurrent models to memorize longer sequences effectively and induce lexical relations. Third, to provide a general purpose reading simulator adaptable across multiple NLP tasks, natural language processing tasks. The methodology they used, the model architecture, is extend LSTM, the traditional LSTM network, the traditional LSTM algorithm with a memory tape and intra-attention addressing. Second, each token is linked with adaptive memory slots. And number 3, attention computes weighted relations among past tokens. And as we said, the attention mechanism computes attention weights that reflect how important and what is the importance level of each part. Second, fusion with sequence to sequence. Shallow fusion. LSTMN replaces LSTM in encoder decoder. So rather than using LSTM, the traditional LSTM network, we use now LSTMN and replace LSTM in encoder decoder. Deep fusion combines intra and inter attention for richer alignments. So they combined the intra attention, the self attention, and the inter attention for two different attentions coming from different sources for richer alignments. The cross attention experiments, language modeling on pen tree bank, perplexity evaluation, sentiment analysis on Stanford sentiment tree bank, and natural language inference on SNLI corpus. Results. What are the results here? The language modeling. What is the performance and the level of performance of the language modeling model? Single layer LSTMN achieves perplexity 108, outperforming standard LSTM 115. So here the single layer LSTMN achieves perplexity outperforming standard LSTM. Deep LSTMN further improves perplexity 102. Sentiment analysis competitive with state-of-the-art CNN and tree-based models. Two-layer LSTMN achieves 87% binary accuracy. And on natural language inference, deep fusion LSTMN reaches 86.3% accuracy, surpassing previous LSTM-based approaches, for example, MLSTM 86.1%. The conclusions here are LSTMN effectively overcomes limitations of traditional LSTMs by explicit memory representation and intra-attention reasoning. So here they refined and enhanced the memory mechanism. By what? LSTMN effectively overcomes the limitations of traditional LSTMs by explicit memory representations. 2. Demonstrates consistent improvements across language modeling, sentiment analysis, and NLI. Contributions extend beyond LSTMs, offering a general blueprint for integrating structured memory and attention in recurrent models. Future work extending on nested structure reasoning and applying on tasks requiring explicit compositionality and dependency modeling. This work challenged with the limits of recurrent sequence models. So recurrent sequence models face many limitations. So this work challenged with limits of recurrent sequence models by embedding explicit memory structures and intra-attention inside LSTMs. That helps to focus, to selectively pay more attention to relations between specific tokens. Instead of collapsing an entire sequence into a single vector, LSTMN preserved a growing memory tape, simulating how humans fixate and recall tokens incrementally. Philosophically, it signaled a shift from viewing RNNs as pure compressors to viewing them as reasoning readers, capable of modeling latent relations across words. It bridged the gap between memory networks and LSTMs, paving the way for more structured and interpretable neural reading systems. And here is the name of the paper: Long Short-Term Memory Networks for Machine Reading by Jianping Cheng, Li Dong, and Mirella Lapta. Introduced by the LSTMN, a hybrid of memory networks and LSTMs for machine reading. The LSTMN learns to induce token-level relations, learns to learn the correlations and relations between the token-level relations, and store contextual representations without collapsing them, like in the traditional sequence-to-sequence RNN, offering a general-purpose machine reading simulator that outperforms standard LSTMs. And here is the paper. If you want to read more, feel free to read it more in your free time. So we have the name of the paper: Long Short-Term Memory Networks for Machine Reading. And you can see the abstract here. In this paper, we address the question of how to render sequence-level networks better at handling structured input. We propose a machine reading simulator which processes text incrementally from left to right and performs shallow reasoning with memory and attention. The reader extends the long short-term memory architecture, the traditional LSTM architecture, with a memory network. So now we have a memory network in place of a single memory cell. So instead of a single memory cell, we now have a memory network. This enables adaptive memory usage during recurrence with neural attention, offering a way to weakly induce relations among tokens. The system is initially designed to process a single sequence, but we also demonstrate how to integrate it with an encoder-decoder architecture. Experiments on language modeling, sentiment analysis, and natural language inference, which is NLI, show that our model matches or outperforms the state of the art. And here we have the introduction. Feel free to read it more. And if you scroll down here, you can see the LSTM memory, a long short-term memory, recurrent neural network. LSTM is a recurrent neural network, process a variable length sequence x1, x2 until xn by incrementally adding new content into a single memory slot. So LSTM works by incrementally, and by time move across, it incrementally adds new content, proposed new content into a single memory slot with gating mechanism, controlling the extent to which new content should be memorized and which new content should be forgotten. Old content should be erased and current content should be exposed. At time step t, the memory C, which is the memory CT, and the hidden state H are updated, are evolved with the following equations. And you can see here, these are the equations. Here we have sigmoid of the W, which are the learnable weights, multiplied by the previous hidden state, comma, the current time step. So X is the current time step, whether it was a token or a point in time series or whatever data point. Then we apply the sigmoid function, the sigmoid logistic activation function on this equation, which is, here we have the forget gate, the input gate, the output gate, and we have this tanh, which is the candidate member. We apply the sigmoid also with this equation, and apply sigmoid with this equation, and then we apply the tanh with this equation. Then we have the cell update here. We take the value of the forget gate and multiply it by the previous cell state. Then we add, it's an additive approach, we add the following amount, which is multiplying the input gate by the candidate member. If you see this C with a hat, that's a candidate member. Then we have the hidden state. The hidden state is here, we multiply the output gate by the tanh of the cell state. So we take the tanh value of the cell state and then we multiply by the output. This is the new hidden state. And this hidden state gets recursed or gets reversed back, and it's a feedback loop through all text or through all time series points until we finish processing. Where I, F, and O, so I are the input gate. I short for input gate. F short for forget gate. O short for output gate are gate activations. Compared to the standard RNN, the LSTM uses additive memory updates, and it separates the memory C from the hidden state. It separates, so here note, it separates the memory C from the hidden state, which interacts with the environment when making predictions. While here they have LSTMN, the first question that arises with LSTMs is the extent to which they are able to memorize. So what is the extent to which the LSTM algorithm or the LSTM network is able to handle, is able to remember, is able to stay active and able to remember the past context? So the first question here that arises with LSTMs is the extent to which they are able to memorize sequences under recursive compression. Because the problem or the limitation of recursive compression, it compresses the data. So the hidden state is a compressed version of all past tokens. It's a compressed version of all past data points. LSTMs can produce a list of state representations during composition. However, the next state is always computed from the current state. So the next state is always computed from the current state. That's to say, given the current state h, the next state, which is ht plus 1, is conditionally independent of states h1 and ht minus 1 and tokens x1 until xt, while the recurrent or the recursive state update is performed in a Markov manner. It is assumed that LSTMs maintain unbounded memory. For example, the current state alone summarizes well the tokens it has seen so far. So the current state alone summarizes well the tokens it has seen so far. This assumption may fail in practice, for example, when the sequences is long-range dependencies. Is long-range. And you can see here we have input gate, output gate, and forget gate. Here we have this forget gate, F, then it inputs some data and forgets it. Then here we have the C, T minus 1, which is the past cell state. And also we have here output gate and input gate. Feel free to explore that architecture more in your free time, as always. And if you go down, you can see this diagram. This is a nice and wonderful diagram. As you can see here, we have encoder and decoder. So decoder with shallow attention fusion. The encoder, here we have encoder input. Then the encoder input gets passed to intra attention. As we said, intra attention is a mechanism that focuses and pay attention to the relations and correlations between tokens. The self-attention mechanism, later formalized as the self-attention mechanism. Then it computes the attention weights and passes those to encoder memory tape. So they refine the memory mechanism here. Then it passes to encoder hidden state tape. And then we have this cross attention mechanism, which is inter-attention, along with the decoder attention. The same process, decoder input gets passed to intra-attention, the self-attention mechanism. Then it passes to decoder memory tape. Then it passes to decoder hidden state tape. And also we have here the cross attention that combines and concatenates the attention power from the encoder and decoder. Then we have here the prediction. And here we have the decoder with a deep, here with shallow attention fusion. But here decoder with a deep attention fusion. The same idea also, encoder input gets passed to intra-attention. The intra-attention focuses on the most relevant parts. As we said, attention mechanism is a machine learning technique that directs deep learning models to pay more attention and to prioritize specific parts. And then it passes to encoder memory tape, and then we have encoder hidden state tape. Then we have this cross attention, which is inter-attention, decoder memory tape. Then it passes to decoder hidden state tape, and then it makes predictions. Here you can see, you can read more. LSTM ends for sequence-to-sequence modeling. The encoder uses intra-attention, while the decoder incorporates both intra and inter-attention. The two figures present two ways to combine the intra and inter-attention in the decoder. So this was the paper. You can feel free to explore it more in your free time. Now we have finished discussing this paper. Let's move on to Attention is All You Need paper. Let's dive into Attention is All You Need paper by Ashish Vaswani et al. 2017. The paper introduces the transformer, a giant architecture, a novel neural sequence transduction model that relies entirely on attention mechanisms. So entirely relied and based on attention mechanisms, dispensing with recurrence and convolution. The transformer achieves superior translation quality, faster training, and greater parallelizability compared to RNN and CNN based models. On WMT14 English to German, the transformer obtains 28.4 BLEU, surpassing previous best results by over 2 times BLEU, or double times. On WMT14 English to French, it sets a new single model state-of-the-art with 41.8 BLEU while training in just 3.5 days on 8 GPUs. The architecture also generalizes well to tasks beyond translation, such as English constituency parsing. What are the problems that they faced? Number one, sequential bottleneck of RNNs. As we said and discussed, recurrent neural networks or traditional recurrent neural networks suffer from vanishing gradients, suffer from exploding gradients, and cannot deal and handle long-range dependencies. Why? Because it doesn't have any gating mechanisms. Then they invented LSTM, long short-term memory. This architecture introduces 3 new gates for get gate, input gate, output gate, and also a candidate memory and cell update. Together, they form a framework that can handle and model long-range dependencies and also reduces the problem of vanishing gradients. And also then they invented GRU, gated recurrent unit. GRU is a simplified version, a simplified architecture of LSTM with fewer parameters and also faster training and faster convergence rates. GRU also is able to handle long-range dependencies. But here we have a bottleneck of RNNs in general. Recurrent models process tokens step by step, hindering parallelism and slowing training. So RNN handle data sequentially, in a sequential order, step by step, token by token, data point by data point. But the transformer introduces the idea of parallelizability, highly parallelizable operations. So here we have recurrent models, process tokens, step by step, hindering parallelism and slowing training. Number 2, difficulty modeling long-range dependencies. So as we said, long-range dependencies, RNNs and CNNs require many steps to connect distant tokens, to connect far away tokens. 3, computational inefficiency. Convolutions and recurrences increase training costs, limiting scalability. 4, limited interpretability. Previous models lacked mechanisms to clearly expose syntactic and semantic dependencies. So in short, these are the problems. 1, sequential bottleneck of RNNs. 2, difficulty modeling long-range dependencies. 3, computational inefficiency, because as we said, convolutions and recurrences increase training costs, limiting scalability, and also limited interpretability. Previous models lacked mechanisms to clearly expose syntactic and semantic dependencies. So what are the solutions? How to solve these problems? The first solution is develop the transformer. So the proposed solutions: 1, develop the transformer. The transformer architecture now is adopted in many fields, in computer vision, in natural language processing, in multimodal models, and in many fields, but built entirely on self-attention and feed-forward layers. So it's entirely built on self-attention mechanisms with feed-forward layers, in addition to feed-forward layers. 2, replace recurrence with scaled dot product attention. So the scaled dot product attention here is introduced for the first time, the scaled version of the attention mechanism, scaled dot product attention and multi-height attention, enabling direct modeling of global dependencies. 3, introduce positional encodings, sinusoidal functions to capture order information in sequences. Number 4, employ residual connections. Employ residual connections, layer normalization and dropout for stable training. And number 5, optimize training with the Adam optimizer and a novel learning rate schedule called warm-up plus inverse square root decay. So in short, the proposed solutions are: develop the transformer architecture that was built entirely and based entirely on self-attention with feed-forward layers. Number 2, replace recurrence with scaled dot product attention and multi-height attention, enabling direct modeling of global dependencies. Number 3, introduce position encodings. Why? Because the transformer as a standalone architecture doesn't capture the order of the tokens, doesn't learn the order and the sequential order of the text of the time series. Then they introduced a solution called sinusoidal functions to capture order information in sequences, to preserve the order and to maintain the order of the sequences. Number 4, employ residual connections. That was introduced in Residual Connections in Deep Networks paper by Kaming He. The residual connections is a way to make later layers to to make deep layers aware of what of the identity of the raw original input. So it tells the later layers, hey, those later layers, be aware of the image. It looks like that. Don't forget who you are. Don't forget who you are. And then we have layer normalization. And also we have dropout, which is a technique introduced in the paper AlexNet introduced in the paper AlexNet, yeah? They incorporated it in AlexNet to prevent overfitting and also to prevent feature co-adaptation for stable training. Number 5, optimize training with the Adam optimizer and a novel learning rate schedule, warm-up plus inverse square root decay. Purposes: to eliminate the computational constraints of RNN and CNN sequence models. So we need to eliminate the computational constraints, the computational difficulties of RNN and CNN sequence models. 2, to demonstrate that attention-only architectures can outperform state-of-the-art machine transition systems. Number 3, to provide a scalable, interpretable, parallelizable framework applicable beyond translation, for example, parsing multimodal tasks. And now, the transformer architecture is a state-of-the-art model in every single field, in computer vision, in NLP, natural language processing, in LLMs, large language models, in multimodal models, and so on. Methodology, architecture. The architecture that they used here is an encoder, 6 layers of self-attention, plus feed-forward networks. The decoder is also 6 layers with masked self-attention to mask the future tokens, and encoder decoder attention. Hidden dimension, they use 512 dimensionality for the vectors. Feed forward dimension 2048. So the feed forward dimension, they used 2048 neurons inside the feed forward layers. And also we have 8 attention heads. Big model, larger hidden 1024. Feed forward layers have 4096 and 16 heads. Instead of using 8 attention heads, they used also in the large model, in the large variation, 16 heads. Training. The dataset that they used is WMT 14 English German, 4.5 million pairs, 37,000 byte per encoder tokens. English to French, 36 million pairs with 32,000 tokens. The hardware is 8 NVIDIA P100 GPUs. Training time 12 hours base, 3.5 days big. So the training time, the baseline model needs 12 hours and the big model took 3.5 days to train. Evaluation, BLEU for translation. So they use BLEU as a score, as a metric, as an evaluation metric for translation. Also we have English constituency parsing, WSJ, and also ablative studies on attention heads, dimensions, dropout, and positional encoding to preserve the order of the sequence. Results: English to German, transformer base reached 27.3 BLEU, the transformer big model 28.4 BLEU plus 2 times BLEU over prior best ensembles. In the dataset English to French, the transformer big 41.8 BLEU, new single model, state-of-the-art SOTA at 25% training cost of GNMT, Google Neural Machine Transition. Parsing. The transformer achieves 91.3 F1, WSJ only, competitive with RNN grammar models. So it's a real competitive with RNN grammar models. Semi-supervised setting, 92.7 F1, surpassing prior baselines. Ablations. Multi-head attention improves BLEU by up to 0.9 over single head. Larger models consistently outperform smaller ones, and sinusoidal versus land positional encoding nearly identical performance. The conclusions. Here we have some conclusions. The first conclusion is that the transformer introduces a paradigm shift. Attention alone is sufficient for sequence modeling. Number 2, it achieves state-of-the-art performance in translation and parsing at a fraction of the training cost. Number 3, The architecture improves parallelization, efficiency, and interpretability compared to RNN CNN models. This work laid the foundation for subsequent advances in large-scale pre-training, for example, BERT, GPT, and multimodal transformers. So the transformer now became a new, or started a new era, opened the way for next research papers like BERT, GPT, and multimodal transformers. Future directions include applying restricted local attention for very long sequences and extending to other modalities, for example, speech, images, video, which they've already done. This paper marked a paradigm shift. It argued that attention alone is enough. Attention alone is all you need. You don't need recurrence. You don't need convolutions. The only thing you need is attention to attend and focus on the most salient parts, on the most relative parts, and ignore those less important details to make the information more abstract and more robust features. Here, attention alone is enough to model sequence transduction by discarding recurrence and convolution entirely. The transformer proved that language understanding, language modeling, could be achieved through parallelizable global interactions between tokens. Its clean architecture not only accelerated training but also improved interpretability, laying the foundation for today's large-scale pre-trained models such as BERT and GPT. Attention is All You Need by Vaswani and et al. Introduced the transformer, a fully attention-based architecture for neural machine transition and beyond. The transformer dispensed with recurrence and convolution, relying entirely on multi-head self-attention. It achieved state-of-the-art BLEU scores while being faster, more scalable, and more interpretable, a decisive moment in deep learning history. And also we have here the paper. You can view it and read more if you'd like. Attention is All You Need. Abstract. The dominant sequence transduction models are based on complex recurrent or convolutional networks. So recurrent and convolution are computationally inefficient, are hard to train, hard to optimize. They face many limitations. They face many challenges in training, optimization, and also to model long-range dependencies. So the dominant sequence transaction models are based on complex recurrent or convolutional networks that include an encoder and a decoder. The best performing models also connect the encoder and decoder through an attention mechanism, as we've said in the Bahdanau attention, Luong attention, and the earlier works. We propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. Experiments on 2 machine transition tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. So they saw that it require significantly less time to train than the RNN based models. Our model achieves 28.4 BLEU on the WMT 2014 English to German transition task, improving over the existing best results, including ensembles, by over 2 times BLEU. On the WMT 2014 English to French transition task, our model establishes a new single model state-of-the-art BLEU score of 41.8 after training for 3.5 days on 8 GPUs, a small fraction of the training costs of the best models from the literature. We show that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing, both with large and limited training data. And also feel free to read through the introduction, here the background, and model architecture. We can read through here. Most competitive neural sequence transaction models have an encoder-decoder structure. So the most competitive neural sequence transaction models have an encoder-decoder structure. Here, the encoder maps an input sequence of simple representations x1 to xn to a sequence of continuous representations, which is the Z. Z1 until Zn. Given Z, the decoder then generates an output sequence Y1 until Ym of symbols, one element at a time. At each step, the model is autoregressive, consuming the previously generated symbols as additional input when generating the next. And here we have the architecture, the nice and wonderful architecture of the transformer. You can see we have inputs, and these inputs now, we receive some sort of sentence. For example, I went to school yesterday. Then we have to tokenize it to segment the text into tokens. It's called a tokenization. Then we take these tokens and map them into integers. For example, I is 0, went is 2 or 1, 2 is 3, and so on. Then we map these integers into continuous vector representations via the input embedding. We turn them into vectors, into high, rich representational vectors. Then we keep or preserve or maintain the positional encoding or the order of the sequence via positional encoding, the sinusoidal function. And then we pass it into the encoder. Here the encoder consists of multi-layers. We have the multi-head attention layer that attends and focuses on the most relevant parts, on the most significant and salient parts, and ignores those that are less important. Then we have a residual connection. As we said, they adopted the idea of residual connection. Why? To tell the layer, do not forget who you are. Keep in mind that you are like this. You look like that. Then we have an add and norm layer. Then we pass the output into a feed forward. So the idea here is that they combined the idea of attention, self-attention with feed forward layers. We don't have recurrence. We don't have convolutions. The only thing we have attention alongside with feed forward layers. Then we have add and norm layer. Then we pass that rich or very rich representation vector, we pass it to the decoder via a cross attention. This is called a cross attention because the attention is coming from two different sources. Then here we study it further and pass it to multi-head attention, add and norm. We do some layer normalization. As we said, layer normalization is adopted here to normalize the outputs, and we have add residual connection. Then we pass into a feed forward layer, add a norm, then into a linear layer. This linear layer projects it into the vocabulary space, which is via the softmax, and the softmax normalizes those logits into probability values bounded between or limited between 0 and 1. Then we output the probabilities. Then it predicts the next token, and it does that auto-regressively to be able to talk, to speak, to generate. This is the core idea of the transformer. And as you can see, the transformer follows this overall architecture using stacked self-attention and point-wise fully connected layers. So we have point-wise fully connected layers, dense layers, linear layers for both the encoder and decoder, shown in the left and right halves of figure 1, respectively. Encoder and decoder stacks. The encoder is composed of a stack of n. Here we have also the n. N means you can repeat this block for whatever times you need. N, whatever times you need. So here n equals 6. Why? Because they stacked 6 layers. If you get back here we have an encoder of 6 layers. In the architecture, encoder of 6 layers, self-attention plus feed-forward networks. So the main idea here is that, as they said here, the encoder and decoder architecture consists of 6 layers, identical layers. Each layer has 2 sub-layers. The first is a multi-head self-attention mechanism, and the second is a simple position-wise, fully connected feed-forward network. We employ a residual connection around each of the 2 sub-layers, followed by layer normalization. That is, the output of each sub-layer is layer norm x, and then we add the sub-layer of x, where sub-layer is the function implemented by the sub-layer itself. To facilitate the residual connections, all sub-layers in the model, as well as the embedding layers, produce outputs of dimension d model equals 512. As we said, they encoded those words into 512 dimensionality vector. And here the decoder is also composed of stack n equals 6 identical layers. In addition to the 2 sub-layers in each encoder layer, the decoder inserts a 3rd sub-layer, which performs multi-head attention over the output of the encoder stack. Similar to the encoder, we employ residual connections around each of the sub-layer, followed by layer normalization. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with the fact that the output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at positions less than I. And here you can see, here we have this is self-attention, and here this is self-attention, but here this is the masked multi-head attention where we mask on the future tokens. And also we have here the cross attention. So we have multi-head self-attention, we have here masked multi-head self-attention, and here we have the cross attention. Why? Because this is coming from two different sources. And feel free to read through that. Also we have here the V and Q and K. Multi-head attention. As you can see, we have linear, and they introduced the idea of scaled dot product attention. The scaled dot product attention works well for text and for NLP tasks. And then we have concatenation and linear layer. This is called the multi-head attention. We apply the V, K, Q matrices. And also we have the scaled dot product attention. Here we have matrix multiplication, scale, and then we have mask, then we have softmax and matrix multiplication. So here we have a lot of ideas. Feel free to read through them later. This is the equation: attention, Q, K, V. So the Q vector, the key vector, and the V vector equals softmax. We apply softmax, and then we have the Q matrix, multiply it by the K transposed, and then divide by the square root of dk, and then multiply by the V. Here you can see the two most commonly used attention functions are additive attention and dot product attention, multiplicative attention. Dot product attention is identical to our algorithm, except for the scaling factor, which is this idea. So they introduced the scaling factor to scale the attention by dividing by the square root of the d of k. Dot product attention is identical to our algorithm, except for the scaling factor, which is this. Additive attention computes the compatibility function using a feed-forward network with a single hidden layer, while the two are similar in theoretical complexity. Dot product attention is much faster. So the dot product attention is much faster and more space efficient in practice, since it can be implemented using highly optimized matrix multiplication code. And also here we can read through multi-head attention. You can read through your own time, and this was the paper of attention is all you need. As you can see here, we have the scores of BLU. You can see they reached 28.4, the score of the BLU score. Had English to German, and we have English to French. In the task of English to French, we have 41.8, and in the task of English to German, we have 28.4. And also you can see here the alignments between these words. You can see the align with the law. You will never be. We have a lot of diagrams. You can read them later in your own time. So now we finished discussing the paper Attention is All You Need, that was introduced in 2017 and changed how we think about AI. Let's discuss Google's neural machine translation system, Bridging the Gap Between Human and Machine Translation by Wu et al. 2016. This paper presents GNMT, Google Neural Machine Translation, Google's large-scale neural machine translation system designed to overcome critical shortcomings of earlier neural machine translation models. GNMT employs an 8-layer LSTM encoder-decoder architecture with residual connections and attention, combined with word piece modeling to handle rare words, model and data parallelism for efficient training, and quantization-aware inference for production deployment. GNMT achieves state-of-the-art performance on WMT14 English to French and English to German benchmarks, and reduces translation errors by 60% compared to Google's previous phrase-based systems, approaching human-level accuracy in side-by-side evaluations. What are the different problems that they faced? The first problem, slow training and inference due to deep recurrent networks. Number 2, poor handling of rare or unseen words leading to mistranslations. 3. Incomplete translations where models fail to cover all input tokens. 4. Difficulty scaling to production systems with large datasets and real-time demands. What are the different solutions that they use to solve these problems? Number 1, architecture. Deep stacked LSTMs, 8 encoder plus 8 decoder layers. So we have an encoder of 8 layers and a decoder of 8 layers. These layers are LSTM layers. So deep stacked LSTMs, 8 encoder plus 8 decoder layers with residual connections to not forget who you are. So we tell the later layers, the deep layers, don't forget who you are. Remember that you look like this, and we pass it via a residual connection. Residual connections helps the training be easier and stabilizes the training, to stabilize training and make the gradients alive and strong, robust. 2. Parallelism. Model parallelism across GPUs and residual attention linking. Bottom decoder, and we have top encoder for efficiency. So the top encoder passes its vector representations into the bottom of the decoder, and then the decoder use this guidance, use this vector to understand and then generate and proceed. We have here word piece model, WPM, subword units to balance flexibility of characters with efficiency of words, enabling robust rare word translations. Number 4, beam search refinements, length normalization and coverage penalty to ensure complete translations. Number 5, quantization aware inference, low precision arithmetic optimized for TPUs, tensor processing units, to accelerate decoding with minimal loss in quality. Reinforcement learning refinement, fine-tuning models to directly optimize BLEU, though with limited impact on human judgment. So here, in short, these solutions are as the following. The architecture, they used deep stacked LSTMs, long short-term memory, 8 encoder plus 8 decoder with residual connections to stabilize training. 2. Parallelism. The idea of parallelism. Model parallelism across GPUs and residual attention linking. Bottom decoder, and we have top encoder for efficiency. 3. Word piece model, WPM. Subword units to balance flexibility of characters with efficiency of words, enabling robust rare word transition. Number 4, beam search refinements, length normalization and coverage penalty to ensure complete transitions. And number 5, quantization aware inference. And number 6, they leveraged reinforcement learning refinement to fine-tune the models. Purpose: to develop a robust, accurate and efficient NMT neural machine translation system suitable for real-world production, like Google Translate, a real-world product to translate between different languages, to close the gap between phrase-based SMT, between phrase-based statistical machine translation and neural methods, both in transition quality and deployment feasibility. Number 3, to explore architectural, algorithmic, and systems level innovations enabling scalability to massive datasets and multilingual use cases. So the main purpose here is that they developed a robust, accurate, and efficient neural machine translation system suitable for real-world production, like Google Translate. The methodology here is number 1, architecture, 1 bidirectional plus 7 unidirectional encoder LSM layers with residual connections in addition to attention mechanisms. Dataset: they used WMT14 English to French, 36 million sentence pairs, and English to German, 5 million pairs. Google's massive internal production datasets. Also, they used Google's massive internal production datasets. The training: number 1, optimizes. Adam optimizer for early stages, plus SGD, stochastic gradient descent for later refinements. They used also gradient clipping, dropout parallel training across 96 GPUs. Reinforcement learning fine-tuning with glue sentence level reward. So the training here, they used optimizers, add optimizer for early stages and SGD for later refinements. Number 2, gradient clipping with dropout, and also in addition to parallel training across 96 GPUs. And also they used reinforcement learning fine-tuning with GLEU sentence level reward. The inference level here, they use quantized models on TPUs with batch beam search decoding. The evaluation metrics, BLEU scores plus human side-by-side ratings. So you have BLEU scores in addition to human side-by-side ratings. So human engaged in the process. Results: WMT 14 English French, best single model 38.95 BLEU, WBM 32,000, and also we have RL refinement, which is reinforcement learning refinement, plus 1 BLEU 39.92. So if you combine reinforcement learning refinement, then you will gain one more point in the BLEU. Then we have ensemble of 8 models, 41.16 BLEU SOTA at the time. WMT 14 English to German, best single model, achieved 24.61 BLEU, WBM 32,000, and also we have an ensemble of 8 models, 26 BLEU. Production data, 60% fewer transition errors versus phrase-based NMT. Human evaluations, Google neural machine transition outputs approach average human translator quality in some language pairs. So in some language pairs, it surpassed the approach of average human translator quality. Conclusions. Number 1, GNMT demonstrates that deep LSTMs with attention, so they used LSTMs with attention and alongside with word piece modeling, in addition to system level optimizations, can outperform phrase-based systems at scale. Word pieces effectively solve rare word translation and improve robustness across languages. Quantization and parallelism make large neural machine transition models practical for real-time production. Number 4, although reinforcement learning fine-tuning boosts BLEU scores, it has limited effect on perceived transition quality. So although reinforcement learning fine-tuning boosts BLEU scores, it has limited effect on perceived transition quality. GNMT marks a turning point in practical neural machine transition, reducing the gap between human and machine transition. GNMT, Google Neural Machine Translation, represented a watershed moment in the history of neural transition. It was the first time a massive scale neural system powered a global product like Google Translate, proving that deep learning had matured beyond research demos and could serve billions of users daily. By addressing practical bottlenecks, rare words, scaling across GPUs, efficient inference on TPUs, and robust handling of long sentences, GNMT showed that neural machine translation wasn't just a theoretical curiosity but an industrial reality. GNMT's use of word-based models solved the long-standing rare word problem, while its 8-layer residual LSTMs demonstrated that deep recurrent architectures could be trained and deployed at scale. Its beam search refinements, length normalization, and coverage penalties highlighted how decoding strategies mattered as much as model design. Most importantly, GNMT closed much of the gap between human and machine translation, reducing errors by 60% compared to phrase-based SMT statistical machine translation, and delivering output that, for some language pairs, rivaled professional translators in human evaluations. This paper was a philosophical turning point. It cemented that idea that neural networks could be engineered, optimized, and scaled into production systems, paving the way for the transformer revolution that followed. And here we have this paper, as you can see, by many authors. And feel free to read through the paper. Here you can see view inline. It shows a pop-up window that says Google Neural Machine Translation System bridging the gap between human and machine translation. Here, the most important thing, if you go down and scroll down to the diagram, note this. In this diagram here, we have the idea of the bidirectional system. Bidirectional bottom layer. First, we process the text. We process the text in two directions, from left to right and from right to left. Why? This makes the features land more robust, and it lets the network learn what are the future tokens, what are the coming tokens. The structure of bidirectional connections in the first layer of the encoder. LSTM layer, LSTM processes information from left to right, while LSTM layers, LSTM processes information from right to left. So from both directions, trying to understand the past and the future at the same time, trying to look to the future, look ahead, and look backward. Output from LSTM and LSTM-B are first concatenated and then fed into the next LSTM layer, LSTM. So you can see here we have the diagram. We have concatenation. We concatenate and combine the features, then we pass it to LSTM layers, more LSTM to study more fine-grained details, and then generate the X or the Y's. And here you can see segmentation approaches. They use, for example, neural machine translation models often operate with fixed word vocabularies, even though translation is fundamentally an open vocabulary problems, names, numbers, dates. There are two broad categories of approaches to address the translation of out of vocabulary, OOV. So OOV is out of vocabulary words. One approach is to simply copy rare words from source to target, as most rare words are names or numbers where the correct translation is just a copy. Either based on the attention model, using an external alignment model, or even using a more complicated special purpose pointing network. Another broad category of approaches to use subword units, for example, characters, mixed word characters, or more intelligent subwords. And feel free to read through word piece model. And if you scroll down, you can see here we have the equations, we have W's, the weights, we have sigmoid, we have tanh, sigmoid, tanh, we have the input gate, forget gate, output gate, and the cell update, where we multiply the forget gate by the past cell state, and then we add, or it's called an additive concatenation. We multiply the input gate by the input gate. Here we have the I dash gate. Then we multiply the output by the cell state. If you scroll down, now let's discuss the idea of this table. This table contains some example translations from PBMT, phrase-based machine translation, and if we click on 15, it will refer us to this paper. We can copy this paper and search for it in Google. You will see Edinburgh's phrase-based machine translation systems for WMT14, and you can see here we have the PDF. You feel free to read in your own time. And if you get back now to our table, and our GNMT, Google Neural Machine Translation System, the NMT before reinforcement learning table 9, and human source and target synthesis, human translations, are from the public benchmark WMT English to French, New Stats 2014, DeadSet. The right hand column shows the human ratings. So the right hand column shows the human ratings on a scale of 0, complete no sense, to 6, perfect translation. We disagree with some of the human ratings. For example, the translation, this is a French word or French phrase, contains grammatical mistakes and change semantics, and is still scored 6. We present it to illustrate the potential problems of the scoring process. Here you can see we have the source sentence, and if you use the reason Boeing are doing this is to cram more seats in to make their plane more competitive with our products, and said Kevin Kinston, head of passenger comfort at Europe's Airbus. If you use the PPMT model, it will translate like this in the French translation. And here we have the GNMT model translates into this, and then we have the human translation. You can see PPMT scores at 3, the GNMT scores at 6, and the human scores at 6. Let's copy this sentence, for example. Let's copy the French translation and go to Google Translate. Now let make the Google Translate detect the language. You can see it's a French language, and this is the corresponding English version. The reason Boeing is doing this is to concentrate more seats to make their aircraft more competitive with our products, said Kevin M. Kinston, head of passenger comfort at Airbus Europe. So you can see the transition here said aircraft, whereas here in the paper it said airplane, their plane. So you can see the differences, and note the differences between the Google Translate currently and the paper. And here let's try the GNMT. You can see the GNMT model here la raison pour the French translation. Let's take the GNMT translation and paste it here. The reason Boeing is doing this is to create more seats to make its aircraft more competitive with our products, said Kevin Kinston, head of passenger comfort at Airbus. So you can see the GNMT translation is better. Here it scored 6, and also the PPMT scored at 3. And the human here, you can see this is the human translation, and you can try that with the rest of the sentences. For example, here this sentence, when asked about this, an official of the American administration replied, the United States isn't conducting electronic surveillance aimed at offices in the World Bank and IMF in Washington. If we take the PPMT translation and paste it in this box, it will translate into this. You can see asked about this, a U.S. administration. So rather than saying like this, an official of the American administration, it said a U.S. It said directly a U.S. administration official replied, the U.S. isn't conducting electronic surveillance of the World Bank and IMF offices in Washington. And let's try with the Google Neural Machine Translation System. Here, asked about this, a U.S. administration official replied, the United States doesn't conduct. The United States doesn't. You can see here the difference. Here they said the United States isn't conducting, whereas it says here the U.S. doesn't conduct electronic. So you can note the differences. And here we have the human transition. The GNMT scored at 6. It has a performance of 6 on this transition, and human scored at 6, while the PPMT scored at 3. And you can try with the rest. So this was the discussing of the paper, which is introduced the idea of GNMT, Google Neural Machine Translation, to bridge the gap between human and machine translation. Let's dive into replicating the paper Google Neural Machine Translation, GNMT. Google introduces GNMT, an end-to-end neural machine translation NMT system that surpasses conventional phrase-based machine translation. Key features: deep LSTMs with residual plus attention connections, word piece segmentation for rare words, quantization for fast inference, and improved beam search for decoding. And here you can go to the paper via this link. We have the GNMT paper introduced by Google for Google Neural Machine Translation. So you are more than welcome to explore this paper in your free time. But now let's dive into straight away the model architecture. Here we have some imports, then we have some language pairs as we have discussed earlier. We have the English sentences paired to the French version sentences or the German. Here you have I am a student, here the German corresponding language, and then he loves dogs, the German language pair, and so on. Here we have the function build vocab, which builds the vocabulary. We have padding, BOS, EOS, and unknown tokens. These are special tokens. After this, we have here, you can see the build vocab function. We have called it and looped for each source and target in toy data, and then we have applied the build vocab function. After this, we have the encode function. Here we encode the vocabulary. You can see encode takes from me two parameters, sentence and vocabulary. Then it returns a list comprehension. So this is a list for each W in sentence with split. We split it and tokenize it, and then we get the W, and otherwise, if it's unknown, we return unknown token. Here you can see we have 4 source and target in toy datasets. So we are looping through for each source sentence, and for each target sentence, we are looping through that, and we are turning it into tenses via torch to tensor, as you can see, and passing here the BOS, which is the beginning of sentence, plus encode, and then pass into here the target, and the same for the source. We pass the source plus the end of sentence at the end. So here we inject the beginning and inject the ending of the sentence, and in between them we have the encoded version of the sentence of the source sentences and the encoded version of the target sentences. Then we have here dataset to append source IDs and then target IDs. Then we have a function called collate function or collate function that takes from me source batch, target batch equals zip batch. So here we pass a batch, a parameter batch, then we unzip it, then we zip it and unpack that into source batch and target batch. After that, we have the pad sequence function to add padding to pad the sequences. We pass the source batch, comma padding value equals pad index, and the same goes for the target batch. Then we return source batch in alongside with the target batch. Then we convert this dataset into a data loader to be able or to be compatible with the PyTorch models. So we pass a dataset, batch size equals 2, shuffle. Do you want to shuffle it? Yes, true. And then collate function equals collate function. This is the train iterator. But let's focus on the architecture, the model architecture. Here we have the encoder. First, as we have mentioned earlier, we need a way to represent the words. So we need an embedding layer. Converts each token ID, like 5, 6 for student, into a dense vector. This dense vector is the preferred representation form for the models of size embedding dimension. Words with similar meaning end up similar embeddings. So words with similar meaning end up with similar embeddings. Then we have a bidirectional LSTM. Reads the sentence forward and backward from both directions, capturing both past and future context for each word. Then at the last, we have linear compression layer. This is a linear compression layer that compresses the representation vector into the space hidden dimension. So we input combines the two LSTM directions, forward plus backward, by going 2 times hidden dimension. So we combine the two, then we map this in features into the out features, which is the hidden dimension. So here we have into a single hidden state, which is hidden dimension. Now we have defined these items, these elements. We need to call them to invoke them inside the forward method. Here we have def forward self comma source. We pass the source sentence, pass this source sentence or sequence into the embedding, turn it into embedding vectors. Then we take this embedded version and pass it into the RNN layer. This is an LSTM layer that will apply the gating mechanism, apply the LSTM algorithm on it to study its features, and then it will return the outputs in addition to the hidden cell and the hidden state and the cell state. After that, we will leverage the hidden here, or hidden equals torch.tanch equals self.fully connected, then pass torch.concatenate hidden at index 2, hidden at index 1, dimension 1. So here we are combining, or we are merging the forward reading and the backward reading of the bidirectional we are concatenating them, then passing them to the fully connected layer that will study more fine-grained details and map it to the hidden dimension, and it will we will squash these values into the -1 and 1 range via the attach function, and it will return the hidden here. Then at the end we will return the outputs that is gotten from here, comma hidden dot unsqueeze at index 0, and then cell at index 1. So all we are doing here is outputs as hidden states for all tokens needed for attention later, and we have hidden the final, so the hidden here is the final summary vector of the sentence, compressed with tanh, compressed and summarized with tanh. Then we have the cell, which is LSTM memory state trimmed to match decoder shape. The encoder is the listener, is the reader. It processes the whole input sentence and produces both word level features, outputs, and a compressed summary of hidden and cell. After that, we have an attention class. So we have a class called attention, and it inherits from, or it gets its features from the module-based class in PyTorch for building neural network models. After that, we have an init constructor that takes from me a self, hidden dimension. Then we have this self.attention that will be a simple linear layer, and the in features is hidden dimension times 3 will be mapped to the hidden dimension. Then we have self.v, nn.linear, hidden dimension, 1, and then set the bias as false. Attention is the spotlight mechanism that decides which words is the source sentence are most in the source sentence are the most relevant at each decoding step. Which words are the significant words to focus on the most and ignore the rest of the words that are not relevant or that are irrelevant. And this linear layer will project the hidden dimension into the space of 1 and set the bias term as false. Once we've defined these components or elements, let's call them in the for method. Concatenate decoder hidden state with each encoder output. Pass through a small neural net, linear, tanh, linear. Then we have a softmax of all source words that will produce attention weights. Attention is the focus. Instead of remembering the whole input sentence, the decoder only looks where it matters, only focus on what matters and ignores what doesn't matter. And here we have, as you can see, we pass the hidden, encoder outputs. So the hidden state of the LSTM alongside with the encoder outputs. The encoder outputs dot shape at index 0 will be stored in this source length. So if you want to get the source length, it's the shape at index 0. So here we have source length, batch, hidden dimension. So if you want the source length, it's at index 0. Then we have hidden equals hidden dot repeat source length 1 1. Here we repeat the hidden state. After that, we take this hidden and pass it to the concatenation function to concatenate it with the encoder outputs at dimension 2. So the join dimension will be at dimension 2, and then apply the addition mechanism to focus on the most important and salient parts, and we pass into the tanh function to squash the values into -1 and 1 range. Then we have an energy value here. We'll pass it into the V layer, which is this simple linear layer that will produce. It will take hidden dimension and map it to the 1 neuron. And after that, dot squeeze, we have to squeeze it, then apply the softmax Y to normalize the weights and to produce normalized attention weights. At the end, we retain these attention scores. Let's dive into the decoder class. Here, the decoder is as the following. We have an embedding layer, turns the previous predicted token into a vector. We have attention posed in context from the encoder outputs. After that, we have LSTM process the embedding plus attention context. And then we have a final linear layer that combines output, context, embedding, and projects to the vocabulary size, predicts the next word. So as you can see, here we have an embedding layer that takes from me the vocabulary size, which is this hyperparameter, maps it to embedding dimension, this vector. From its name, we can derive that. You can derive this from its meaning. We have embedding. So we can specify the embedding dimension here. It will map the vocabulary size that you have to this embedding dimension. whatever you specify here. Then the padding index equals pad index or pad IDX. Then we have a self.RNN. This RNN is the recurrent neural network. In this case, it's an LSTM layer of hidden dimension times 2 plus embedding dimension. Then we map this in features, we map it into the hidden dimension, comma 1. Here you can see we have the out features as hidden dimension, and we have another linear layer. This layer is the final layer that combines output, context, and embedding, and projects to the vocabulary size by, you can see here, we project or map to the vocab size. Then we have the attention, we apply the attention class and pass into the hidden dimension. Now let's dive into the fourth function. The fourth function here is, you can see, we have multiple different operations. The first one is that looks at its previous word, pays attention to the source sentence, then speaks the next word in the target language. So the most important thing here is that we first take the input and unsqueeze it to add a batch dimension. Then we have an unbatched input. We pass this input to the embedding layer to map this input to an embedding dimensionality. After that, we have this embedded version. We will use it later in the concat function to concatenate with the context. So we concatenate or combine the embedded version with the context vector, and then we apply the RNN input, which we will apply later. The RNN, the LSM layer, apply it on this input, and then the RNN will produce the output in addition to the hidden state and cell state. And here we have the attention weights. We apply the attention layer and pass the hidden at -1, and also we provide to the attention, we provide it with the encoder outputs. And also we have attention weights. You can see dot permute. We have to permute to align the shapes 1, 0 dot unsqueeze 1. After that, we have encoder outputs dot permute, and also we apply the BMM function, batch matrix to multiply the attention weights by the encoder output. Then you can see here we have the prediction, the final linear layer that we said this is a compression layer. Fully connected output will compress the output, context vector, embedded vector into this dimensionality, and then we return prediction and hidden state and cell state. The next step is we have the sec-to-sec class sequence to sequence that inherits from NN module, combines encoder plus decoder into one translation model. So now it connects or it ties the encoder with the decoder into one segment, into one model. Runs the encoder once on the source, starts decoder with BOS, then step by step predict next word with teacher forcing mechanism, sometimes feed the true word instead of prediction. So sometimes we feed the true word instead of the prediction. Then the sec-to-sec loop is the translator. Encoder listens to the decoder, speaks, attention, helps focus. So the most important ideas in here, we instantiate the init method. We provide as parameters the encoder and decoder. We will pass them later. Then we store them in these properties to be accessible from this method. This method here, the for method, takes from me a source sentence, target sentence, teacher forcing ratio as 0.5. Then here you can see we have the batch size equals target.shape at index 1. Why? Because the target shape at index 1 will represent the batch size value. Then we have target.shape at index 0 will represent the target length, not the batch size. So we store these values in variables to be able to use them here freely. After that, we have the vocabulary size. The vocab size here is self.decoder.fully connected output.out features. So we need to get the out features property. After that, we initialize the zeros tensor of this starting value, target length, the ending value, batch 0, batch size, and then the vocab size is the shape of this matrix, then to device to move or send this tensor of zeros into the target device. And then we will apply the encoder and pass the source sentence to it. The encoder will try to map this source sentence into very rich representation vector, and then we will have an encoder output, hidden state, cell state, because the encoder applies an LSTM After that, here you can see we have a nice for loop that loops through the target length, and then for each target length we will decode, we will try to generate, to talk, to speak freely. We pass the input token, the hidden, the cell state, the encoded output. We need to guide the decoder. So the encoder here helps to guide, to help the decoder. The decoder will be able to generate. Then we have output, hidden, cell. We apply the argmax function on the output. Because why? You take the largest probability value. You take the index with the largest probability value, or the biggest logit value. Then if this token is less than the teacher forcing ratio, then use this target token. Otherwise, use the top one. Then return outputs. In summary, encoder is a reader, process, source sentence. Intention is spotlight, what to focus on and what to not focus on. Focus on important words. So you can highlight the most important parts of the sentence, and you can turn off the light about the words that don't contribute much. Then we have decoder, which is the speaker or the writer, generates target sentence word by word. At the end, we combine this encoder, attention decoder, into one giant model called sec-to-sec, the whole translator. And here we have the training loop, as we discussed earlier. Here we have some hyperparameters. You can set them in your own free time as you would like. You can try different values. I've set the hidden dimension to 128 and the embedding dimension to 128. And here we have the encoder initialized, the decoder initialized, sec-to-sec initialized. Here we are initializing the models. After that, we have the optimizer as Adam optimizer, criterion as our cross entropy loss, and here we have the train epoch. As you can see, the train loop, as we have discussed earlier, we have the zero gradient to zero the optimizer and make the optimizer robust and faster. Here we have the forward pass model and pass source sentence alongside with the target sentence. So the model will take the x's and the y, the inputs and the outputs, and will try to figure the function that maps and links between the source and the target, the forward pass. After that, we will hold some outputs in this variable, and we will judge whether this output is really good or bad via the criterion, the loss function. After that, we have the backpropagation algorithm that will compute the gradients based on the loss function and the weights. And then we have optimize step, which will tell Adam, hey, please, Adam, help us and fine-tune the weights. After that, train total loss plus equal loss item. At the end, we divide the total loss by the length of the train iterator and retain them. So this is the idea of training. After that, here you can see we have trained the model for 10 epochs. For each epoch in range 10, run that function, which is train law. So here we have wrapped all these steps into one function, which is a really wonderful and nice trick. You can wrap these steps in function, and you can store this function in a helper file, for example, in GitHub account or something, or in some cloud storage, and then you can grab this functionality and just, rather than every time over and over and over write this functionality, you can just call the function without considering how these steps work. Here we have train epoch. So for each epoch in range 10, just run this function. This function will automatically train the model. After that, we have the loss. We need to append this loss to the losses list and then print the loss at each epoch. Here you can see epoch 1, the loss is 3.5, and the loss is decreasing, getting lower and lower until epoch 4, you can see 0.4, and then at epoch 7, the loss is 0.01, and at the last epoch 10, you have the loss 0.001. And here the loss is reducing, getting lower and lower over time. Over the many epochs, the loss is getting lower and lower, and this is the result of our model. And here the prediction here you can see for each sentence, comma, index in target vocabulary, please map the index to the sentence. So this is the inverse process. And then translate sentence, a function takes from me sentence and tries to translate it. We turn the model into evaluation mode by .eval, by calling the .eval function, or method. Then we pass this sentence into the encode to encode it alongside with the source vocabulary, and we start with the beginning of sentence and we end with the end of sentence. Then we combine or we concatenate. These are the tokens. We use these tokens and transform it into a tensor, into a torch tensor via the function tensor, and unsqueeze them to add a batch dimension, because the model will fail if the model deals with data that is unbatched. You need to batch your data. After that, we turn off the gradient tracking. We are turning off the back propagation. We are turning off the gradient descent by doing this with torch.nograd, no gradient, do the following, which is taking the model encoder, passing the source sentence or source sensor into the encoder. The encoder will do all the process of understanding. Then it will produce a rich representation encoder output, rich representation hidden, and rich representation cell state, and these will guide the decoder data, the hidden, the cell state, the encoder output will all help the decoder generate the output, hidden, and cell. Then we take the argmax. This is equivalent to the softmax. We'll take the largest probability value, and then if this top one equals end of sentence, then break out of the loop. Otherwise, take this predicted output, top one, and append it to the outputs list. Then input token equals torch to tensor top one dot to device. Here we are simply moving the top one tensor. We are turning the top one into a tensor and then sending it to the target device by going to device. At the end, we convert it from a list format, from a list form into a string form by going to join. Then we pass this iterations target at index I for each I in outputs, and here we are calling the function translate sentence and passing the sentence I love deep learning. It will translate. Our model can translate now into Germany. You can see input I love deep learning, and the output is the Germany version. It's the German sentence version. So you can see output. If we take this output and paste it into Google Translate, it detects the language as it's a German language. You can see as a German language, and its corresponding version sentence in English is I love deep learning. So this is how to train models, how to map sequences with sequences, and how to translate in the world of natural language processing. So this was a replica of the Google Neural Machine Translation paper, GNMT, which is a groundbreaking model, a paper that introduced the machine translation model into a product-ready, deployable app. Let's dive into Google's Multilingual Neural Machine Translation Systems by Johnson et al. 2017. This paper introduces a multilingual neural machine translation NMT approach that allows a single model to translate between multiple language pairs by adding an artificial token specifying the target language. The system leverages a shared encoder decoder with attention and a joint subword vocabulary. The model not only achieves competitive or superior results compared to bilingual systems, but also demonstrates zero-shot translation, direct translation between language pairs unseen during training. Visualization of learned representations suggests the emergence of an interlingua-like structure. What are the problems that they faced? Number one, traditional NMT, neural machine translation, requires separate models for each language pair, which is computationally inefficient at scale. So the traditional neural machine translation way is to create or to build a model for each language pair, a separate model, a stand-alone model for each language pair to be able to translate between two different languages, which is computationally inefficient at scale. For example, if you wanted to translate between English and Spanish, you would need to create, you will have to create a model or build a model that maps English to Spanish. And also, you will have to create a model to map English to French, to map English to Germany, and so on. Poor performance on low resource language pairs due to limited parallel data. No mechanism for direct translation between language pairs, lacking training data. For example, Japanese to Korean. Scalability issues. 100 languages would naively require 10,000 bilingual models. And what are the proposed solutions? What are the suggested solutions to solve these problems? The first solution is that target language tokens. Add a token like 2FR, which is short for 2 French, to mark the target language. And you can imagine for every language you would have to write 2, for example, Spanish, which is ES for Espanol, and so on and so forth. So here we have a token, a starting token that tells the model what is the target language, what you will have to map this language into to what, to mark the target language. Second, shared architecture. One encoder, decoder, attention model across all languages. So we have one encoder, one decoder, and one attention model across all languages. We don't build multiple languages or numerous languages to handle different languages, or build several models to handle different languages. Third, word piece model, 32,000 vocabulary, subword units to handle rare words or unseen words and diverse scripts. Number 4, balanced training, oversampling low resource pairs to prevent domination by high resource pairs. Number 5, zero-shot translation, translate between unseen language pairs using shared representations. So we have the idea or the concept of shared representations. For example, if you trained a model to map English to Spanish, and also trained another model to map between English and Portuguese, you will be able to map Spanish to Portuguese. And the same idea for any other language. For example, if you train a model to map English to Chinese and train a model to map English to Japanese, then you will be able to map Japanese to Chinese or Chinese to Japanese. Because of why? Because of the shared representations. The model is able to share the weights, to share the coefficients, and apply what it learned to every single other language. Representation analysis. TSNE visualizations reveal clustering across languages. So they used TSNE, T-distributed stochastic neighbor embedding algorithm, to reveal clustering across languages. For example, the word hello has a vector close to the word hola in Spanish, and close to the word hola in Portuguese, and also close to ni hao, whereas in Chinese. Whereas if you have another word, for example, lion, it would be like that. So it clusters similar words, or it groups similar words towards each other, and the theta angle will be close compared to this theta, which is a very high degree theta. And also we have the purpose here: simplify large-scale transition with one multilingual model instead of many bilingual ones. So instead of building many bilingual models, we just build one multilingual model capable of dealing and handling and also translating in many different languages. Number 2, improve low resource translation quality through parameter sharing. Number 3, enable zero-shot translation between unseen language pairs. Number 4, explore whether NMT learns a universal interlingua representation. So the model is able to learn universal interlingua representations that is capable of generalizing beyond 2 languages. The methodology, architecture. The architecture is GNMT, the same architecture, GNMT style, which we have discussed earlier, 8-layer LSTMs with attention and residual connections. Datasets. The dataset here is WMT14 English to French and English to German. Massive, and also the second dataset is massive multilingual datasets from Google Translate production. And also the training, here we have mixed mini batches, oversampling of low resource languages, evaluation, BLEU scores, and human side-by-side ratings, analysis, projection of embeddings to test for interlingua structure. Results: WMT14 benchmarks multilingual model matches or surpasses strong bilingual baselines. Production systems. One model reduces maintenance costs while maintaining quality. So if you have one model, it reduces the maintenance cost compared if you have, for example, versus you have 10,000 bilingual models. Zero-shot transition achieves non-trivial accuracy without direct training data. Representation analysis. A cross-lingual clustering supports universal interlingua hypothesis. Conclusion. The first conclusion is that a single multilingual NMT model can replace thousands of bilingual models at scale. So instead of training and maintaining several thousands of bilingual models, we now have just one single multilingual model. And we don't have to train English to English with French, for example, and map French to English, and map English to Germany, and also map Germany to French. We just train these pairs: English to French, English to Germany, English to Chinese, and then we will be able to map Chinese to Germany, Chinese to French, and so on. Target language tokens and shared word piece vocabularies ensure robust performance. Number 3, multilingual training boosts low resource translation and enables zero-shot learning. Evidence of a universal interlingua emerges in the model's representations. This work paved the way for multilingual pre-training frameworks like BERT, XLMR, and MT5. The multilingual NMT system marked a bold philosophical leap in how we think about transition, how we deal with transition. Instead of building thousands of bilingual models for every language pair, for example, training a model English to Portuguese, English to Spanish, Johnson and et al. Proposed that a single model could learn to translate across many languages simultaneously. And then if you wanted to map Spanish to Portuguese, we will be able. Why? Because the model has learned how to map English to Spanish and how to map English to Portuguese. By introducing target language tokens, and by introducing and starting with a token that tells the model and informs the model what is the target language. By introducing target language tokens and a shared word piece vocabulary, the paper showed that neural networks could discover cross-lingual patterns and even achieves zero-shot translation, translating between language pairs never explicitly seen during training. This work introduced the idea of a learned interlingua within neural models, evidenced by TSNE visualizations of embeddings, where semantically similar sentences clustered together, semantically related sentence clustered together, regardless of language. It redefined the philosophy of machine transition from building systems for each pair to training one system that speaks them all. Beyond translation, this paper seeded the vision of multilingual pre-training, inspiring future advances like BERT, XLMR, and MT5. It proved that NMT wasn't just about higher BLEU scores, but about enabling a more universal, inclusive approach to language understanding in AI. And here we have this paper, Google's multilingual neural machine transition system enabling zero-shot translation. And feel free to read it in your own time. This is the paper here. You can view it via this button and it will show up a pop-up. You can see we have many authors, starting with Melvin Johnson, Mike Scuster, Cook V. Lee, and the rest of the authors. So you can see here we have a lot of diagrams. As you can see here we have this diagram. As they said, they never changed the architecture. They have 8 layers of LSTM. We have encoder LSTMs. Then it computes the attention weights, and here we have attention. Then we pass it to the decoder, and here we have softmax, and then it generates the Ys or the outputs. And you can see here we have 8 GPUs, GPU 1, 2, 3, 4, until 8. But here in the abstract here, they said we propose a simple solution to use a single neural machine transition NMT model to translate between multiple languages. Our solution requires no change to the model architecture from a standard NMT system, but instead introduces an artificial token, an artificial and starting token at the beginning of the input sentence to specify the required target language. The rest of the model, which includes an encoder, decoder, and attention module, remains unchanged and is shared across all languages. Using a shared word piece vocabulary, our approach enables multilingual NMT using a single model without any increase in parameters, which is significantly simpler than previous proposals for multilingual NMT. On the WMT14 benchmarks, a single multilingual model achieves comparable performance for English to French and surpass state-of-the-art results for English to German. Similarly, a single multilingual model surpasses state-of-the-art results for French to English and German to English on WMT14 and WMT15 benchmarks, respectively. On production corpora, multilingual models of up to 12 language pairs allow for better translation of many individual pairs. In addition to improving the transition quality of language pairs that the model was trained with, our models can also learn to perform implicit bridging between language pairs never seen explicitly. So the model here, this technique allows this model to be able to map two different languages that the model wasn't trained on them explicitly. Here we have seen explicitly during training, that the model never seen explicitly during training, showing that the transfer learning, the transfer of the knowledge, and zero-shot translation is possible for neural transition. And here we have zero-shot transition, means that maybe there's two different languages that doesn't have a shot between them. The model, for example, trained to map English to Swedish, and trained to map English to, for example, Norway language. Then the Swedish language, we can map it to Norway language because they don't have any shot between them. There's any shot or relation or language pairs or sentence pairs that the model has never has seen before. So the model with meaning that even if the model has never seen the language pairs or the sentence pairs between these two different languages, the model can map between these two different languages. Finally, we show analyses that hints at a universal interlingua representation in our models and show some interesting examples when mixing languages. And feel free to read through the rest. And as you can see here, they have the representation using TSNE, a TSNE projection. This is the projection of the TSNE algorithm, a TSNE projection of the embedding of 74 semantically identical sentences translated across all 6 possible directions, yielding a total of 9,978 steps, dots in the image. From the model trained on English to Japanese, you can see trained on English to Japanese and English to Korean examples. Then the model will be able to map Korean to Japanese, a bird's eye view of the embedding, coloring by index of the semantic sentence. Well-defined clusters, each having a single color, are apparent. As you can see, this is the projection of the TSNE. We have English sentence. The stratosphere extends from about 10 kilometer to about 50 kilometer in altitude. And this is the Korean phrase, and this is the Japanese phrase. They all clustered together or close to each other. And here we have English, Espanol, and you can see this is the projection of the TSNE, a TSNE projection. A bird's eye view of a TSNE projection of an embedding of the model trained on Portuguese to English and an English to Spanish, yellow. Examples with the Portuguese to Spanish zero-shot bridge. So we have a zero-shot bridge between the Portuguese languages and Spanish language. The large and red region on the left primarily contains the zero-shot Portuguese to Spanish translations. And as you can see, you can read through the paper in your own time. So now we have finished discussing this paper, which is making the model at large scale or at a wide scale capable of handling not just bilingual, as we've seen in the previous papers. They handled bilingual. They used English to Germany or English to French datasets. But here they scaled it up. They've gone far away beyond and scale it up to handle multilingual neural machine translation system to handle many different languages. Let's dive into replicating the paper, Google's multilingual neural machine translation system enabling zero-shot translation. And here we have the link of the paper. Feel free to read it in your own time. You can go directly to it and start reading it, which is Google multilingual neural machine translation. But now let's straight away dive into the code. So first things first, here we have some imports. You can see we have import torch, the main library for PyTorch. Then we have import torch.nn as nn. nn is a sub package that contains multiple building blocks to build neural network models. Then we have import torch.optim that contains many optimizers. And also we have import random, which generates random numbers. And then we have import matplotlib.pyplot for visualizing different plots. And we have from sklearn.manifold import the algorithm tsna, t-distributed stochastic neighbor embedding, to visualize the feature space or manifold of the words. Here, as you can see, we have a toy dataset which maps English to Espanol and maps English to French and maps English to Germany. Why? Because this is a multilingual neural machine translation app or multilingual model. So we need multiple languages, and we just need to map English to every single language. Then the model will be able to map different languages that wasn't explicitly trained on. For example, the model can map Espanol to French, and also the same idea can map French to Germany without needing to train the model explicitly on those sentence pairs. Here we have this data list which contains these pairs. We have a special token called 2S, which means to Espanol. This is the starting token that they introduced in the paper. Then they have to French and we have to Germany. I love cats, I love cats, I love cats, and we map them respectively into the respective languages. We have here Espanol, here we have the French version, and here we have the Germany version. And the same idea, how are you? We map them into their respective languages, and good morning, we map them into the respective languages. Here we have the build vocabulary, which is a dictionary that maps the padding token to the number 0. And we map here the start of sentence to 1, and also we connect the end of sentence to the number 2. These tokens are special tokens that we'll use later to pad the sentence and also to pad. This is specialized for the source vocabulary, and this dictionary is specialized and used for the target vocabulary. So we use padding to pad the sentences, and we use SOS to start the sentence and EOS to end the sentence. After this, we have a nice function, an awesome function that is called add vocab. So define a new function called add vocabulary, takes from me a sentence and vocabulary. Then it loops through the sentence for each token in sentence.split. So we need to split the sentence, tokenize it, segment it, and then we're looping through each token. So for each token in this split version of the sentence, and then if this token is not in the vocabulary, then please go ahead and do the following. Vocab at index token equals the length of the vocabulary. Then we will create another loop outside of this function for each source and target sentence in data, in that data structure. If we go ahead, here we have a list that contains multiple tuples. Each tuple contains the English version mapped to a list containing the language version, another language, the corresponding language version. Here for each source and target, add this vocabulary. So we call that function, here we call it, and pass the source to the sentence parameter, and pass the source vocab to the vocabulary. Then we check here, if this token is not in the target vocabulary, do the following. Target vocabulary at index token equals length of the target vocabulary. Then here we have the inverse version, where we do some dictionary comprehension. So for each K and V in the target vocabulary, map the V to the K. So here we are inversing. Rather than K is mapped to V, we map the value to the key. After that, we have the encode sentence, sequences function. You can see def encode, it takes from me several parameters. Sequence vocabulary add EOS equals true. So do you want to add the end of sentence? If you want, please put true. If you don't, please pass in here false. Then we have here IDs, which will create another list comprehension. So for each token in sequence.split, if this token in vocabulary, then please add it to the vocabulary. Otherwise, do not do this. And then if add EOS is true, this will be here replaced by true, and the if condition will be triggered. Then IDs dot append, we need to append at the last token. So at the very last token, we need to append this token, EOS, end of sequence. Then we need to, at the end, finally return torch to tensor and reconstruct or build a new tensor of these IDs. Then we have the pairs, which is another list comprehension. Here you can see we pass the encode function, we use it, we leverage it, then pass the source vocab, and then we build another tensor of the target vocabulary. But this time we start with the start of sequence token. This is a special token to start the sequences, to trigger the model to be able to encode and decode the sentences. Then we have the target vocabularies, the rest of the tokens, and at the end we end with an EOS token for each source. This will happen for each source and target pairs in data. Here, let's dive into the actual architecture of the model. So we begin by class encoder that inherits from NN module. So class encoder, NN module defines an encoder block as a neural model. After this, we have an embedding layer. This is a layer that converts every token ID into dense vector representation. So word embedding. Example, it converts the I like reading into three dense vectors that is of size embed size. Here we pass the embed size. This size will be used to convert every single ID into a rich vector representation of this size. After this, we have a GRU layer. You can see a GRU layer is simpler than LSTM, but the GRU layer processes the embeddings and produces hidden states. Here we pass the hidden size. This will be the number of neurons of this GRU layer. So how many neurons do you want to put in this GRU layer? This will be defined by this parameter. Then we set the batch first equals true. Why? This means that you will start by the batch size, comma sequence, comma embedding. So here we start by the batch size, which is useful and really handy. After this, we have a forward method. In this forward method, we will call and invoke these layers respectively. So we have an embedding variable equals self.embed. So look up embeddings for all source words. Here we turn the source sentence into embedding vector representations. Then we pass this embedding to the RNN layer, which is a GRU layer that will process and understand the text. After that, it will return the outputs alongside with the hidden state, and final GRU hidden state is a compressed summary of the sentence. Then we return them finally. After that, let's dive into the class attention module. So here we have attention is a small feed-forward network. As you can see, the attention layer is a simple linear layer. It's a simple feed-forward layer that scores and weighs how well each encoder output matches the current decoder state. After this, we have a linear layer that accepts here the hidden size and maps it into a single neuron. So reduces it to a single scalar score importance of that word, which represents the importance weight of that word. And the bias here is set as false because we don't need to use a bias term. Then, once we've defined these components, let's call them respectively in the forward method. The first thing here is that, as you can see, we have encoder outputs.size1. We get the size at the index 1 and store it in the variable sequence length. After that, here we combine the hidden. You can see hidden at -1 dot unsqueeze to batch it to add a batch size. Then dot repeat 1 comma sequence length comma 1. So dot repeat, what it does, it expands it across all encoder time steps, so you can compare against each word. So we are expanding or making that expanded. After this, we have a torch concatenate function. We will concatenate or combine the hidden state alongside with the encoder outputs. After this, we will pass it to the attention. The attention will attend every single element to every other single element, and will compute the attention weights, attention scores, and pass them to a tanh activation function. Then this will be stored in the variable energy. After that, these are raw logits, raw attention scores. Let's pass them to the V layer, which is a simple linear layer that will produce just one value, one attention weight. This weight will be passed into the softmax. The softmax will process it and normalize it And then, as you can see here, we have the softmax normalized into probabilities, attention distribution over source weight. After that, we will store it in the attention weights variable. Then we will take the sum of it using the sum function inside PyTorch. So you can see torch.sum attention weights multiplied by the encoder outputs at the dimension 1. And finally, we retain that context vector. So as a spotlight, the attention is a spotlight. It decides which source words are most relevant, are most salient at this decoding step. So without any further ado, let's dive into the decoder class. Here we have class decoder that inherits from NN.module. We have an embedding layer, as you can see. We start by an embedding layer that converts previous target token into a vector dense representation. Then we have another GRU layer, takes as input both the word embedding and the context vector from the attention. After this, we have a simple linear layer that projects the decoder output alongside with the context into a distribution over the target vocabulary. So this linear layer will talk, will speak. It will project these understood representations into the vocabulary space, into the vocab size. Then the model will be able to predict or to generate. After this, we will call the attention module or the attention class over the hidden size and store that inside the property or inside the attribute self.attention. And then we have a simple forward method. As you can see, in this forward method, we have the x equals x.unsqueeze1. Make the input first begin by the batch. So unsqueeze adds a dimension. Unsqueeze appends a new dimension, which is the batch dimension at index 1, a single token step. After that, we take this x and pass it to the embedding layer. The embedding layer will turn this x or input into a vector representation, embed the current input token or last predicted word. After that, we take this embedding representation and pass it into the concatenation and concat with the context vector. And then we have the RNN ready input. We pass this RNN input to the actual RNN layer, which is a GRU layer. This GRU layer will apply the two gates, the reset gate and the update gate, that will regulate the flow of the information. After this, we store it. It produces two different outputs. It produces the output alongside with the hidden state, the understood hidden state from the GRU layer. Then we'll use this hidden state and retain it. As you can see, retain hidden state. And then we use the fully connected layer, pass to it the concatenated version of the output that is produced by the RNN. So we take the RNN output and then squeeze it and also combine with it the context. So we provide the concatenation function, the output, and the context vector. Then we feed them into the fully connected layer. This fully connected layer will project these land representations into the vocabulary space that will speak freely. Then we return at the end the prediction that is resulted by the fully connected layer. The decoder is the speaker, is the writer. It decides what word to say next. It decides which word to say next by combining what it just said, what it remembers, and what part of the input it should focus on. After that, let's move on to the sec-to-sec model, which connects the encoder, the decoder, and builds a whole model, combines the decoder alongside the decoder into one translation system. So you can see we have the encoder and decoder equals enc and dec for shorts. After that, we have the forward method. The forward method here, it takes from me the source sentence, the target sentence, and the teacher forcing rate as 0.5. Because why? Because it has a probability. Sometimes we need the model to feed itself from its past info, and sometimes we need to teach it, to teacher force it. So here we have the run encoder once on the source. Here we pass the source into the encoder. The encoder will understand, will try to remember what this source means, what this source sentence means, and then initialize with the decoder the SOS starts of sentence as the first input. So as you can see here, we have the output equals nothing. Then we start by this colon comma 0, which instantiates a new token of this token SOS. So it starts reading or starts writing by writing the first token, which is SOS. After this, we loop through each token in this range in the target tokens. Let's go ahead and pass the X alongside with the hidden. In addition to the encoder output, we pass these all as inputs to the decoder. So we feed the decoder the current time step, the past time step, and the learned representations from the encoder, and we feed them into the decoder. The decoder will take this information plus this, and will decide which is the best appropriate next word to say. After this, the decoder will produce the output and the learned hidden state. Then we take this outputs dot append, we append into the outputs list. So yeah, here we have an empty list. We'll take this list outputs and append to it, add a new element to it, to this list, which is this output that is generated by the decoder, and then we unsqueeze on the first dimension. Then we have a teacher, which is target colon comma t. Here we have the teacher forcing, and then if this teacher, we will generate a random number. So if random.random, if this random number is less than the teacher forcing rate, then use the teacher forcing. Else use the output from the model, out.argmax as 1. So this is the idea of making the teacher forcing property or operation randomly happening. Sometimes it's being done. Sometimes we use the normal output from the model. Sometimes we feed the model with the truth, which is the teacher forcing property of teacher forcing operation. At the end, we retain the concatenated version of the outputs and then dimension 1. So we concatenate the outputs. So now, congratulations, we have built the model. Let's dive into the training, the training process. Here we initialize the variables or the hyperparameters with values. You can see we have hidden size as 64, the embedding size as 32. Feel free to change them, to fine tune them, to play around with them in your own free time. You are more than welcome to play around with these values. Then we have the encoder. Let's instantiate a new encoder model. You can see I have the encoder class. We are passing in the source vocabulary in addition to the embedding, in addition to the hidden size, which we have initialized in the last step. So hidden size equals 64 and the embedding dimensionality equals 32. So we'll convert every single word token ID into a dense vector of size 32. Then we have a decoder, which will pass in here the target vocabulary, in addition to the embedding size, also the hidden size. Then after that, we have now an encoder, we have a ready decoder. Let's combine them, the encoder and the decoder, combine them and build the sec-to-sec model. After this, we have the optimizer equals add optimizer. The add optimizer will help us to fine-tune, to update, to play around with the weights, and then choose the best set of the weights, which will pass into here, model.parameters. The add optimizer will take the parameters and fine-tune them, update them with this learning rate. The learning rate is the step of the updates. So how aggressive do you want Adam to play around with weights? This is the learning rate. What is the step size of updating? Learning rate will be 0.001 or 0.01, just 0.01. After this, after the optimizer, we have a loss function that will judge on the model's outputs, comparing it to the truth or to ground truth outputs. Here we have the cross entropy loss, which is very useful for multi-class classification, because here we are classifying into the vocabulary space. Here we are generating. So this is the cross entropy loss. After this, here you can see we have the for epoch in range 300. We will initialize the total loss as 0. So first we begin the loss value as 0. After this, we are going to loop through the source sentences and the target sentences. So for source, comma target in pairs, let's take this source sentence and unsqueeze it, add a batch dimension. In addition to the target, we need to add a batch dimension by doing unsqueeze function. Then we need to zero the gradients of the optimizer by going optimizer.zeroGrad, really important step. Then we pass this source sentence. In addition to the target, we pass them as the forward pass to the model. The model will take this source and target and say, thanks, I will try to do my first forward pass. Then the model have random weights, random biases, random coefficients, and do its forward pass. Then the forward pass will compute the outputs. It will compute here the outputs, the predictions of the model. Then we'll take this outputs and compare it to the ground truth targets and pass the ground truth alongside with the outputs from the model, pass them to the loss function. The loss function here will compare between the ground truth and the predicted items. Then the loss will judge the model, will tell us how much the model is far away from the ground truth values. It will store this value in the loss variable. After this, let's go ahead and optimize the model and fine-tune the model. The first thing, we need an algorithm that is named as backpropagation. This is done via loss.backward to backpropagate the errors. After this, we have the optimizer step, which will trigger Adam and ask for help from Adam to fine-tune the weights. Then we will increment the loss by this idea. Total loss plus equals loss item. So we are taking the loss, taking the item of it, the scalar, and then increment or add to the output, to the total loss value, which is starting as 0. So we initialize the loss as 0, and then for every step, for each training loop, we will increment the loss value by what we get from here, the loss. And every 100 epoch, we will print the loss value. As you can see, print epoch, then we inject the epoch number, whatever it was, 100, 200, 300, and then the loss value will be as this loss value, and just will keep the first 3 decimal places. And here we have a nice function, an awesome function that will translate. As you can see, define a new function, translate, takes from me a sentence and the maximum length as 15. Then here we need to turn the model into evaluation mode. We need to convert the mode of the model into eval mode to tell the model that now we don't need to play around with weights. Now we don't need to play around with backpropagation or Adam. Just we need to do some inference mode. After this, we have the encode function that will encode the sentence and convert it into dense representation vectors and pass the source vocabulary. .unsqueeze, because we need to add a batch dimension, otherwise the model will fail processing data which is unbatched. So we need to batch the data to add a batch dimension, to add a batch access for the model to be able to process it without failing. After this, we have the encode out and the hidden. Here we take the encoder of the model and pass the source sentence. So we are taking this source, this encode source sentence, pass it to the encode function, to the encoder function. The encoder here will understand its hidden linguistic, semantic, syntactic representations, and then store it in the encoder output and also in the hidden state. Then we'll use these 2 values and pass them to the decoder. The decoder will take the current time step alongside with the hidden that is outputted by the encoder, in addition to the encoder output that is outputted by the encoder. So we guide the decoder. We guide it. We tell it, you need to take this encoder output, this hidden state, this current time step, and go ahead and try to generate. The decoder will produce an output and also a hidden state. We'll emit this hidden state for now. We'll take the output here, you can see, and then take the argmax. Why? Because we need the largest probability. We need to take the largest the index of the largest probability. What is the most probable word that the model thinks that this is the most fit word to be in the next word? Then we have this x. We'll check if x is .item equals the target vocabulary EOS. That's meaning that we have finished the end. We are now near the end. We need to break the loop. So if this generated x is now equals the end of sentence, then break the loop. Otherwise, go ahead and take the out tokens. Here we have an empty list, as you can see. We'll take this empty list, and every loop in this for loop will append the generated inverse vocabulary using this x dot item, and then we'll pass it to the inverse target vocabulary and append it to the out tokens. At the very last step, finally, we need to convert this list into a string format. We need to destroy this list into a string by going ahead and return a empty string, but we're going to populate it with the join method and pass the out tokens list. So here we are passing the out tokens list. After it has been populated to the join method, the join method will take this list and say, okay, I will turn it into a string. And then this translate function will return this translated string, the translated sentence string. Here we have some test predictions. So we have some test sentences. We have to Espanol, I love cats, to French, I love cats. So we need to provide the model with the info. What is this token tells the model or informs the model what is the target language. What is the language you need to translate English into. Whether it was Espanol, French, or Germany, and you can play around with that to try different languages. So this is the idea of multilingual neural machine transition system, enabling zero-shot transition. So we have zero-shot relationship between Espanol and French, but the model somehow can map Espanol to French, since the model is trained how to map English to Espanol and how to map English to French. After this, we have this print predictions. You can see here for each sentence in this test sentences. Let's go ahead and pass each sentence into the translate function. So here we are looping through this list. Here we have test sentences, okay? For each sentence in test sentences in this list, go ahead and print that from this sentence, we map it into the translate function and pass sentence. And the translate function will take care of that sentence and translate it. After this, we have the visualize embeddings block. As you can see, we have here embeddings. Here we have the encoder of the model, dot embed the embedding layer, dot weight, the weights and the hidden representations, dot data, dot detach, dot numpy. This is telling that we need to access the encoder of the model. We need to access specifically the embeddings layer. We need to access its weights, its hidden coefficients. Then we need the data. We need to detach it and convert it into a normal numpy. You would say, why? Because Matplotlib doesn't deal with PyTorch tenses. Matplotlib cannot handle data living on the GPU. Matplotlib can deal with NumPy, and NumPy have operations that is being done on the CPU. NumPy doesn't live on the GPU. Whereas TensorFlow and PyTorch, since they are model libraries to build models, they need to store their tensors on the GPU. But here we need to degrade the tensor from the GPU level into the CPU level. After this, we have here this TSNE algorithm that we have imported earlier from scikit-learn. From sklearn.manifold import TSNE, which will generate a manifold. And here we have n components equals 2. So how many components do you want to preserve? How many components do you want to keep? Because TSNE is a dimensionality reduction algorithm. And here we are telling how many components do you want to keep, or do you want to preserve or maintain? We just need to keep 2 components. The TSNE will take high dimensional data and then reduce it into just 2 dimensions, 2 components. We have random state as 0. This is for reproducibility purposes. And then perplexity equals 5. Then dot fit transform. Let's fit this awesome algorithm, fit it on the embeddings. The TSNE will somehow automatically learn the hidden representations or the latent representations of these embeddings. And then we have this TSNE value. Let's go ahead and do some matplotlib, create a figure, specify the fig size as 6,6, and then we need to create a scatter plot of the TSNE values. As you can see, we have the first axis and then the second axis. Then for each token and index, in the source vocabulary, go ahead and annotate this word by its name, whatever it was, and then let's title it as TSNE T-distributed stochastic neighbor embedding algorithm of shared source embeddings. And then we can go down. You can see here we have these words. So you can see here how is near the French, cats, Espanol, good. So here you can see the words, how they are scattered. But since the model is trained on a small scale dataset, since the model isn't trained for a large amount of epochs, you can see that we have pretty scattered data. But if you train it for large scale data, it will be clustered. The more closer words will be clustered together or closer. Epoch 0, the loss is 27.5. The epoch 100, the loss is reduced to 0.004, and the epoch 200, the loss is 0.001, which is really awesome. The predictions here, we have to Espanol, I love cats. It mapped this English version text into the Espanol version, which is Yo amo los gatos. Then we have to French, I love cats. It mapped it into the French version. And also you can see here, the model can translate from English into Germany version, and the model is also capable of mapping the good morning in English version, capable of mapping it into the Espanol version. Good morning in Espanol is, in French is bonjour, and good morning in Germany is guten Morgen. So you can see here, these are the mappings or the truth mappings, and the model successfully, correctly mapped our English sentence pairs into its respective or their respective language pairs. And also you can verify that through taking the Spanish version, and you can see detect language. it detects it as Spanish version, and it is translated into English. You can see it says in here, I love cats. So we have correctly and successfully trained a model to map Spanish versions into English versions. And also let's take the Germany version, or the German sentence, Guten Morgen. It will be detected via the Google Translate tool as Germany language and will be translated into good morning. So we have successfully built a model and teach it how to map sentences into another sentences in another language. And you can see here the loss is decreasing, getting lower, reducing. And here we have another visualization to map these sentences. So French, here we have to French. Then the model will say, I need to map this English sentence into the French language. When we say to DE, it maps it into the Germany language, and so on. So this token tells the model what is the transferred language should be. The loss is reducing or getting down, and feel free to explore these later in your own time. You are more than welcome to explore these figures. So this was the replication of the paper, Google's Multilingual Neural Machine Translation System enabling zero-shot translation. In this section, let's discuss the three big families, Transformer, GPT, and BERT architectures. These diagrams illustrate the core mechanics of encoder-decoder architectures, the introduction of attention, and the structural differences between landmark transformer-based models. Source: Data Scientist. Here in this image, you can see that we have three different architectures: Transformer, GPT, and BERT. Let's start by the Transformer. In the Transformer architecture, you can see first we have inputs. We start by inputting a sentence or a sequence of tokens. For example, I like reading. We input this sentence, and then we need to segment it, to split it into sub-tokens, into sub-words. For example, I is a token, like is a separate token, reading is another separate token. Then we map these tokens into IDs, into integer IDs. For example, I is 2000, like is 2100, and so on. You can map it to whatever integer ID you would like. These integer IDs are poor representations. They don't reflect the semantic and the syntactic meaning. So we need to map it to a more richer representation. The best representation now, and it is now based on multiple architectures, multiple architectures use it, is the vector, the dense vector representation. So we map these integer IDs into dense vectors that reflect the meaning and the semantic meaning via the input embedding layer. So we use input embedding layer to map these token IDs, these IDs, into high representation vector or high representational vectors. Then we need to preserve the order of the words. Since the transformer as a standalone architecture doesn't preserve the order of the words, doesn't maintain the order, we need to preserve that meaning via positional encoding layer. And usually we have many different ways, but usually it is a sinusoidal function. And also we have many different other ways. Once we pre-process that data via the input embedding and positional encoding, we are now ready to pass them into the encoder block. In the encoder block here, we have the multi-head attention. The multi-head attention, this is a self-attention layer that applies, from its name, multi-head, meaning it applies multiple attention processes in parallel. Each attention head study and finds correlation of each separate token. Then in this layer we apply three different vectors. We have the Q vector, we have the K vector, and also we have the V vector. Each different vector represents a different thing. Q asks what you are looking for, what you are searching for. K is the suggested, for example, answer. So it says me, I have the answer. Then V is the actual content or value that will be passed if the K is similar or close to Q. Okay, and this is usually applied via the equation where we multiply the Q by the K transposed. Here we have the K transposed, then we divide it by the square root of the dimensions of K, then we pass it to the softmax layer, let's say ST softmax, then we multiply by the V. So this is the equation that they use for the attention mechanism. Here we find how similar Q to K, then we divide it by the square root of D to scale it, to normalize it, then we map it to normalized logits, normalized scores via the softmax activation layer, then we multiply by the V. As an analogy or a quick analogy, we have search engine Google. When you type in the text, so the type in text that you type in the search bar in the search engine, this is the Q, what you are looking for. For example, what is machine learning? Here, this is the Q, what you are looking for, what you are specifically searching for. And here we have several websites. Google suggests several websites. We have the IBM blog, we have Wikipedia blog, Google developers blog. So each different blog, each different website is a K. This is a K. This is another K. And they are saying, me, I have the question, I have the answer, I have the answer. Then you can choose how similar each blog, how similar or how close is it that fits your question. How similar each blog to your question. What is the most appropriate blog that fits the answer of your question? Then you can go into it. This is the actual V, the actual content. This is the answer. So here the V, machine learning is the subset of AI focused on algorithms. So this is the actual V that will be used or will be passed if this K is closely related to the Q. So this is as an analogy. And as another analogy, imagine a classroom with many students and a teacher. One student asks a question. The teacher hands this task to the students. Who can answer this question? Then the other students raise their hands. Me, I have the question, I have the question. Then the teacher assigns a weight to every single student based on his knowledge on the performance and the grades, the different grades of each student. Then the teacher lets the student answer these questions. So here you have a query, which is the student who asks, Q query. He is looking for some correlation. He is looking for some info. Then this info is carried by the K, the Ks. So the Ks carry the value, and they say me. They suggest themselves. The teacher assigns some weights to each student, and then when the teacher lets the students answer this question, they will vary based on their ability to answer. They will vary based on their ability to provide the most appropriate and the most fit answer. Then we, by multiplying these two vectors, Q by K, and then scale it up and pass it to a softmax, the teacher normalizes these weights, the teacher normalizes these scores, and he multiplies it by the V, and then we provide several V's, but they are not equal in the importance. They are not equal in their significant rate. Each different V will be how much the Q similar to the K, then its corresponding V will be of high importance, will be of the most greatest importance rate. So we have multiple different V's contributing to answer, but they are not equal in the weight. They are not equal in the importance. This is the main idea of the attention. And here you can see we have the self-attention mechanism. This is an intra-attention mechanism. You can also call it intra-attention. And then we preserve the identity via a residual connection. The residual connection is a mechanism adopted in the transformer. In the paper, attention is all you need. They said that we adopt the idea of the residual connection. Why? Because residual connection stabilize training, stabilize the gradients. They prevent or they mitigate the problem of vanishing gradients and exploding gradients. They make gradients smoother and more robust. So we preserve the identity of the X we pass the raw X or the raw inputs as they are without any transmission via the attention. We pass it and combine it and add it to the output of the attention layer. To the output, add it with the output of the multi-head attention block. And then we apply the normalization, which is the layer norm. This is a layer norm that normalizes the outputs of the attention layer. And then after normalization, with alongside with addition, alongside with residual connection say, don't forget who what you look as. Don't forget who you are. You look like this, so don't forget who you are. Then we pass this into the feed forward layer. We pass the normalized outputs alongside with the addition to the feed forward layer. The feed forward layer discovers and look for more fine-grained details, discovers more fine-grained details and more robust features. So it refines the features. It does a kind of refinement and a look for more robust features. Then after this feed-forward layer, we also preserve the identity. So we take the actual raw output from the add and norm and pass them as they are without any transmission via the feed-forward. We pass them as they are to the output of the feed-forward, and then we combine them. We combine them via the addition operation, and then also we normalize them. So this is a feed-forward layer, also called as a multi-layer perceptron MLP. Sometimes it will be referred to as a MLP, multi-layer perceptron. Then we have finished. Now, congratulations, we have finished the encoder block. We pass this very rich representation vector to the decoder block. And as you can see here, we have an inter-attention. This is called an inter-attention mechanism, which is also referred to as a cross-attention, which is the idea of combining two different attention from two different sources, from the encoder, from the source encoder, and from the target decoder. So we combine these two attentions together. We add them together. And also you will find that the decoder also contributes by its own intra-attention layer or self-attention layer, which is called in here masked multi-head attention. The masked multi-head attention is a normal attention, but it prevents access to the future tokens. The only idea here, the most important idea, is that it prevents looking ahead. It prevents access to the future tokens, which is the shifted right. It shifts right. It does an offset to the next token, and it also prevents looking ahead, prevents looking to the future tokens. This is the masked multi-head attention layer. And then we have also the residual connection. We have the norm layer. We normalize, and then we pass this output to the attention alongside with the K and V. So we pass the K. Here we have the K. Here we have two arrows. Here we have K and V, and the decoder asks for a Q. So the decoder here asks or pass a Q, and here we have the K and V. Okay, the K and V will answer the Q. Will answer what the Q wants. The Q wants some info. This info will be provided by the K. The K says me. I have the answer. Choose me. Please choose me. And the K then, if it's very close to the Q, it will provide its own value. Then we input these arrows into the multi-head attention. This is another intra-attention, self-attention layer that applies. This is the cross-attention layer. The cross-attention layer that will be provided by the two sources, encoder and decoder. So here we have a cross-attention layer. Then we preserve the identity, as you can see, and then we add a residual connection with a normalization layer. Then we pass it to the feed-forward layer to study more fine-grained details. Then we have the same idea, add a norm. Then we pass it to a linear projection layer that projects these logits into the vocabulary space. Then we have a softmax layer that normalizes the logits into probability distribution. So we have a probability distribution like this, and here we have these probabilities, as you can see. Then also we output these probabilities, these normalized probabilities. This is the whole idea of the transformer. What about GPT? GPT is generative pre-trained transformer. It's just a decoder only part. So take just the decoder part here. This is the GPT without using any encoder. This is a GPT architecture. Okay, so take this path, and this is called a GPT. Think of a decoder as a writer, as a generator that can generate and talk and speak freely. Then we have BERT. BERT is an encoder only architecture. You can see we have just the encoder part. So if you combine the encoder alongside with the decoder, you have a transformer. And if you separate the encoder from the decoder, well, the encoder is BERT, decoder is GPT. This is the main idea of the BERT. BERT just understands, holds the meaning, holds the contextual vector that represents the meaning and understanding of the data. It understands these inputs and store it in a high representation rich vector. And the GPT take the inputs and tries to generate and talk freely. And you can see here, this was the idea of the transformer versus GPT versus BERT. And by the way, BERT is short for bidirectional encoder representations from transformer. So B is bidirectional, E encoder, R representations from T transformer. And I hope this expression was helpful to you. So this is the main idea between transformer, GPT, and BERT. Let's take a deeper look into the inner workings of the transformer architecture. Here we have this transformer explainer playground, which we can access from our atlas. Click on this link and it will direct us to this poloclub.github.io transformer explainer. So here you can see, first of all, we have some slides that explain the architecture of the transformer. We can close them now, but let's focus on the interface. First, we have an input that will generate. You can see here, data visualization empowers users to visualize. Here you can write whatever sentence you need or whatever sentence you would like, and then you can click generate and it will generate. So let's click generate. You can see now it do one forward pass and then it tries to generate, and now the model generated that. Let's click another time. You can see it will generate another time to visualize the world. So data visualization empowers users to visualize the world, and then click generate around them. First, here you can see we have some embeddings. So we first start by inputting some sentence, inputting a sequence. As we said in here, we first start by inputs. These inputs will be processed by two steps. If we click on the embedding here, you can see we have two steps. We have token embeddings, which are here. We have these IDs. You can see 6,601. So these words, these tokens are mapped into integer IDs. Then these integer IDs are poor representations. They don't convey the semantic meaning. We need another way to represent them. So the best way to represent the words is via the token embeddings and turn them into embeddings, into vector, dense vector embeddings. After that, we preserve the position encoding. Here you can see we have this input embedding layer, which will turn the token IDs, integers, into vectors, high, rich representation vectors. Then we preserve the contextual meaning via this layer, positional encoding layer. Here, this position encoding layer will preserve the meaning. You can see data is at the first position, visualization is at the second position, 1, M is 2, powers 3, uses is 4, 2 is 5, and so forth. So we have token embedding, and then you can see here tokenization splits input text into tokens. Tokenization segments input text into tokens, small units like words or subwords or parts of the words. GPT-2 Small has 50,257 token vocabulary, each with a unique ID. In the token embedding step, every token is matched to a 768 number vector. So each token is converted into a vector of size 768 number inside the vector from a large lookup table. And these vectors are land. These are land vector representations. The model will, when we train the model later, the model will adjust and fine-tune these values inside each vector to best represent the words. And then similar words will be clustered together dissimilar words will be clustered far away. These vectors are learned during training to best represent each token's meaning. After this, we have this position encoding layer, which we can see here. Word order matters in language. So the word order or the order of the words matters. Position encoding gives each token information about its place in the sequence. So since transformer as a standalone architecture doesn't learn the order, doesn't capture the contextual meaning, we need to preserve them. GPT-2 does this by adding a learned positional embedding to the token's embedding. But newer models may use other methods like rope, which encodes position by rotating certain vectors. All aim to help the model understand order in text. After this, after we have processed the text, we can input this processed text into the encoder, which contains the multi-head attention layer. Here we have the you can see we have now the transform block, which is this area that is bordered. If you close this, we have the transformer block, which is the bordered area. We have multi-head self-attention alongside with the multi-layer perceptron. And if you go down here, we have after the embedding, so here we have embedding and we have tokenization, we have token embedding. Here we have the transformer block. The transformer block consists of two things. We have the multi-head self-attention, and then we have after this, we have the multi-layer perceptron. Here, multi-layer perceptron MLP. So these are the two main components. As you can see in the image, we have multi-head self-attention alongside with the feed-forward network. The first thing here, let's start by the first thing, multi-head self-attention. Multi-head means we apply several numerous attention processes in parallel. So here, if you click on them, self-attention lets the model decide which parts of the input are most relevant, are most significant to each token. This helps it capture meaning and relationships, even between far apart words. In multi-head form, the model runs several attention processes in parallel. So in multi-head form, the model runs several attention processes in parallel, each focusing on different patterns in the text. And here you can see inside the multi-head self-attention, we have three key matrices, three important matrices. We have the key matrix, query matrix, and value. The key here, if you click on this, we have query, key, and value. So the key and Q and value are three learned vectors that the attention will learn and update them. To perform self-attention, each token's embedding is transformed into three new embeddings. So each token's embedding, the data, visualization, each word will be converted or transformed into three new embeddings: query, key, and value. You can imagine this as an analogy. We have the search engine Google. When you type in the text, that you type into the search bar, this is the query. So here we have this search bar. You can search in here, what is machine learning? This is the query. This is what you are looking for, what you are searching for. What do you want? What you are looking for behind the scenes. This is the query, the Q. When you click enter, Google suggests multiple websites: IBM blog, Wikipedia blog, Datacam blog. These are the case. These are the case that suggest themselves that say, choose me. I have the answer. I am fit to you. I am appropriate to you. Then we try to multiply, here you can see, we try to multiply the K by Q and see how much or how far or how close these two together. Then when we decide that this is the closest K to Q, we choose or we assign them the highest weight to its corresponding value. The value is the actual content, the actual information inside the K. So K will provide us with this V. This is the V, the actual content that will be used or will be passed. So here we have, you can see these parameters, weight and biases. So this transformation is done by applying different weights and biases to each token embedding. These parameters, weights and biases, are optimized through training. Once created, queries compare with keys to measure relevance, to measure similarity, and the relevance is used to weight the values. So if it represents a higher measure, a higher similarity rate, a higher closeness rate, then we assign a high weight to the value. If it's a low relationship or a low correlation between K and V, between Q and K, we assign a low weight to the V. You can see here, them is assigned a high probability, whereas us is assigned a low probability. So you can see here, the V is passed through here, and then we have data moves through the residual connection, then we have them as 98.32% as a high weight. So we say that the Q is multiplied by the K, and then we scale it via, if you click on here, it will multiply the K by the Q, then it scales that via this equation, Q multiplied by the K transpose divided by the square root of the dimensions of K, then we plus the mask. So here we have the dot product, the multiplication, we multiply Q by K transposed, and we transpose the K because in the multiplication of algebra, we need to transpose the other matrix in order to be compatible to multiply the two matrices or the two vectors. Then we mask it to prevent access to future tokens, and then we have the softmax. We apply the softmax on this masked addition. Then we have a probabilities here. You can see we have some high probabilities. For example, the word visualization is assigned a higher probability. You can see 84, whereas some words here have low probability. For example, 0.03. Then we have this value. We will take these values and then will be passed as the output here. Then we'll go through the multi-layer perceptron. So the main idea of the addition here is that it's a mechanism in machine learning that directs deep learning models what to focus on, what to prioritize. So which parts here should we prioritize? Should the model prioritize and gives the most attention and pay attention to? After this, we have the multi-layer perceptron. The multi-layer perceptron is a feed-forward network that refines the land representations by the attention. Here we have, you can see MLP. So the attention output goes through an MLP, multi-layer perceptron, to refine token representations. A linear layer, which is a feed-forward layer, a simple feed-forward layer, changes embedding values and size using learned weights and bias. Here in the MLP, also we have learned weights, learned biases. So the embeddings here are learned, the KQV are learned, the MLP weights and biases are learned. So you have here three main areas that those areas are learned. A linear layer changes embedding values and size using learned weights and bias. Then a nonlinear activation decides how much each value passes. Many activation types here in the MLP exist. GPT-2 uses GLU, which lets small values pass partially and large values pass fully, helping capture both subtle and strong, robust patterns. After this multi-layer perceptron, here you can see we have this residual connection, and also here we have a residual connection. You can see we have this residual. We pass the raw input as it is without any transformation as the output of this attention or multi-heads of attention. So we combine the transformed data that goes through this attention layer. We combine it with the raw unchanged input from here. We pass it as a residual. You can see residual connection. What is the main idea of residual? Residual connections helps to stabilize the training and the gradient flow of the neural network. So transformers have extra features that enhance the model performance, but aren't core to understanding the basics. For example, a residual connection adds a layer's input to its outputs, keeping information and learning signals from fading, keeping them to not fade, to not vanish through many layers. In GPT-2, it's used twice per block to train deeper stacks effectively. And the same idea, we apply another residual connection in the multi-layer perceptron. So we take the inputs of the multi-layer perceptron and then we pass them here to combine them, to add them with the outputs of the multi-layer perceptron. So here you can see we have residual connection. And also here you can see the layer normalization. So if we return to the image, here we have the inputs to the multi-head attention. We add a residual connection and combine the untransformed version with the transformed version, and then we have the normalization layer. The main idea behind the layer normalization helps stabilize both training and inference by adjusting input numbers so their mean and variance stay consistent. This makes the model less sensitive to its starting weights. This makes the model less sensitive to its initialized weights. and helps it learn more effectively. In GPT-2, it's applied before repetition, before the multi-perceptron, and once more before the final output. Then here you can see we have 11 more identical transformer blocks. So we have the same block as this, but multiplied by the nx11. So we can slide between them. You can see we have another block, a third block, and each block tries to learn different representations, different patterns, different weights, and trying to capture the semantic and syntactic representations of each sentence. So here, this block here, you can see, is multiplied nx times. Nx times. They multiplied this block, you can see here, the transformer block, they multiplied this 12 times. So we have 12 of these blocks that will learn the representations in parallel, fully parallelizable manner. After this, so we have here 11 more identical transformer blocks, and then we have the probabilities. You can see here we have the probabilities, and then probability of them, the word them here, token being sampled. We have some sampling techniques here to choose the best next word. You can see we have the scaled logit. So here, temperature hyperparameter. Temperature is the most important hyperparameter in the transformer architecture. It works by scaling the logits before turning them into probabilities. A low temperature, for example 0.2, makes large logits even larger and smaller ones even smaller, favoring the high scoring tokens and leading to more predictable choices. A high temperature, for example 1 or above, flattens the differences, making less likely tokens more competitive and leading to more creative outputs. So if we decrease the temperature, you can see the model is the most deterministic approach. So it takes a strong deterministic approach. So here you can see the word them takes 100%. Whereas if we increase the temperature, the model becomes creative and creative and creative. So the more temperature, the more creative the model. The more creative the model. You can see here the probabilities get distributed over the tokens. And here you can see again we have the top k filtering. We choose the k equals 5. Then you can see the sampling strategy. Finally, we need a strategy, an approach to pick the next token. Many exist, but here are common ones. Greedy search picks. You can see here we have the greedy search. You can change the k. So we can choose the first k, just only the first k. We can choose just 2 k's or 3 k's. Here you have k equals 3. We choose the 3 highest performing k's. And if we increase them, it increases. So here, the top k keeps only the k most likely tokens. And top p keeps the smallest set whose total probability is at least p, trimming unlikely ones early. Then softmax turns the remaining logits into probabilities, and one token is picked at random from the allowed set. So here we can choose whether it was top k or top p. If we choose top p, then it is there. Then it generates the word there. Whereas if we choose the top k, then the top k here is the word. You can see the top k equals 1. It chooses the word them. So you can play around with that in your own free time. And then we can slide between the transformer blocks. We can go to the third block, fourth block, and see the attention weights here change. You can see here the attention weights here are different from here. Every block learns different patterns, learns different representations. Until we have here some examples. For example, IEE this conference highlights then it tries to generate, highlights the importance, generate of generate. So it moves through all these steps, multi-perceptron, residual probabilities of then it generates. Also you can write your own text. For example, I like reading, generate. Then it tries to generate here. You can see the Q, K, V vectors. I like reading about, generate. You can see here, I like reading about the, generate another time. Now we have the V here combined. I like reading about the history, which is a really nice topic. Then if you go down here, you can read more. What is a transformer? Transformer is a neural network architecture that has fundamentally changed the approach to artificial intelligence. Transformer was first introduced in the seminal paper, Attention is All You Need, in 2017. So you can feel free to read this paper. Attention is all you need. Paper. And then we have and has since become the go-to architecture for deep learning models, powering text generative models like OpenAI's GPT, Meta's Llama, and Google's Gemini. Beyond text, Transformer is also applied in audio generation, image recognition, computer vision, protein structure prediction, AlphaFold, and even game playing, demonstrating its versatility across numerous domains. And here we can see we have the Transformer architecture. We have embedding layer. The input text is divided into smaller units called tokens, which can be words or subwords. After this, we have the Transformer block. The block consists of two important mechanisms, the attention mechanism and multi-perceptron. So inside each Transformer block, we have two important core things, attention mechanism and multi-perceptron, and hence the name attention is all you need. We remove recurrence, we remove convolution, we just attend to the most important significant parts and pass them to a multi-perceptron that refines the gradients. Then we have output probabilities, the final linear layer, and softmax says transform the processed embeddings into probabilities. And you can read the rest in your own time. So you are more than welcome to explore the rest of these. And here you can see we have the main idea behind residual connection. Residual connections were first introduced in the ResNet model in 2015. This architectural innovation revolutionized deep learning by enabling the training of very deep neural networks. Essentially, residual connections are shortcuts that bypass one or more layers, adding the input of a layer to its output. This helps mitigate the vanishing gradient problem, making it easier to train deep networks with multiple transformer blocks stacked on top of each other. In GPT-2, residual connections are used twice within each transformer block, once before the MLP and once after, ensuring that gradients flow more easily and early layers receive sufficient updates during backpropagation. So this was the idea of looking inside the transformer block. So feel free to explore it more in your own time, and you can access it via this link. Let's discuss the idea of sequence to sequence or encoder decoder. First, you can see we have here the Google Translate tool. This is just an analogy that how the encoder decoder works behind the scenes. The left box here represents the source language, and the right hand box represents the target language. Here we have the English language as the source language. Let's type in I like teaching AI. You can see it maps these tokens into their corresponding tokens, which is the French language. So the left box is just a user interface front end, but behind it stands the encoder mechanism. The encoder takes from me a source sentence, reads it, and understands what it means, and maps it into very rich representative vector. Then it passes this vector to the decoder. The decoder takes this very high representation vector and maps it to the output tokens and generates the tokens. It acts as a writer that writes the corresponding tokens. The right box is also a front end, a user interface front end, but behind it stands the decoder mechanism. So this is the idea of mapping a sequence into a sequence or translating languages. We have an encoder that takes a source sentence, understands it, and guides the decoder. The decoder will be guided by the encoder plus its own representation vectors, and then it can be able to generate the output sequence. Let's dive into discussing the three architectures: the traditional RNN, recurrent neural networks, versus LSTM, long short-term memory, and GRU, gated recurrent unit, in visual diagrams. The source from Super Data Science blog. Here in this diagram, you can see we have the traditional recurrent neural network model or architecture. First, we start by inputting the current time step, the current input, alongside with the previous hidden state. Then we pass them into a neural network layer with a neuron of activation tanh. So here we have the function, the activation function as tanh. Tanh is a nonlinear or nonlinear activation function that produces outputs limited between -1 and 1, or bounded between -1 and 1. Then this neural network layer produces the new hidden state and the output. This new hidden state will be looped back and will be recursively returned back into this hidden state, and will be inputted as the next new hidden state into the architecture and will be processed. Then we have the same loop and loop and loop over and over and over. So this is the idea of RNN. We just have a simple neural network layer with a tanh activation function that limits the values between 0, -1 and 1, and then produces the new hidden state alongside with the output. This architecture suffered from 3 main problems. Number 1, it can't model long-range dependencies. It can't handle and capture the patterns in long-range dependencies. It quickly forgets. Number 2, this architecture also is slow to train, is slow to converge. And number 3, it suffered from the main problem, which is vanishing gradients and exploding gradients. So these are the main 3 limitations that it faced. To address these problems, in 1997, we have 2 scientists, Sepp Hochreiter and Schmidhuber, introduced a new architecture called LSTM, Long Short Term Memory. This architecture has gating mechanism. You can see, whereas in the traditional RNN, we do not have any gating mechanism. Here, we don't have any gating mechanism, which is a poor thing. But here, we have gating mechanism that regulate the flow of the information. Here, we start by inputting the current time step alongside with the previous hidden state, and then we have 4 key mechanisms. The first mechanism, or the first technique, we have the forget gate. The forget gate processes these 2 inputs combined, the current time step alongside with the previous state, and process it and decides how much of the past information to forget or to be kept. The forget gate is activated using the sigmoid activation function. Then we have another gate, which is the input gate. The input gate is also activated via the sigmoid logistic function. This function also decides whether to pass this information or whether to discard it and remove it. This is the input gate. Then, after the input gate, we have a candidate memory. This candidate memory is really different. Is different from the others. Why? Because it has an activation function, which is tanh, the hyperbolic tangent function, which, as we said, outputs values in the range from -1 to 1. Then the last gate is the output gate. The output gate here is also activated via the sigmoid function, and the idea here is that the forget gate gets multiplied by the previous cell state, and the input gate gets multiplied by the candidate memory, which is the tanh activation. Then, combining these 2 outputs additively using an add operation, we update the cell state and produce a new cell state. And here you can see we take the output gate and multiply it by the cell state applied with the tanh function. So we apply the tanh activation function on the cell state, and then we produce a new hidden state here, or you can also consider it here. We produce a new hidden state. This is a new updated hidden state. Then this hidden state gets looped back again and again and again through this, and will be overwritten here. Then will be also input again. Then we do the same operation. We apply a forget gate, input gate, candidate member, output gate, and this LSTM succeeded in handling and modeling long-range dependencies that lasts for more than 1,000 time steps, that can stay along and stay active for more than 1,000 time steps. And also this LSTM is faster to train and faster to converge, and also it mitigated the problem of vanishing gradients and exploding gradients. So they succeeded. Why? Because they introduced the idea of regulating the flow of information, which is the idea of gating, the gating mechanisms achieved by sigmoid and tanh functions. Then we have the GRU. The GRU is a simplified version of the LSTM, GRU stands for gated recurrent unit, and it has fewer parameters. It has less number of parameters compared to LSTM, and also it is far more faster to train and to converge, and it is considered a simplified version, has fewer number of parameters, and also faster to train and converge. Here we have, instead of 3 gating mechanisms, we have just 2 gates. We first input the current time step alongside or in addition to the previous time step. Then we apply a reset gate that decides how much of the past information to reset and to delete, to get rid of, via the sigmoid function. Then we also have another gate, which is the update gate, the Z gate. Then also you can see here we produce a new hidden state, and this hidden state gets looped back again and enter as gets looped again and enter as the new hidden state that overrides the old hidden state. This is the idea of hence we name these architectures recurrent neural networks, because we have the idea of recurrence. We have the idea of bouncing again, of getting again. So it processes the data sequentially, in a sequential manner. So it preserves the meaning and preserves the contextual representation. Unlike transformer, which we have to do this manually. You have to preserve the order of the words, because transformer handle text and data points in parallelly. And here in this image, you can see we have long short-term memory. Here we have the previous time step, xt minus 1. So t minus 1 stands for the previous time step. Then we input this and gets processed by these gating mechanisms. Then we produce the next, or the current time step. This is the current time step. Then this current time step will be processed to produce the next time step, and so on and so forth, until we finish processing all the tokens or all the data points. So we have a previous time step. We can say here previous. And also we have the current time step. And also here we have the next time step. The coming time step, the future tokens. And here you can see we have the same idea here. These 4 mechanics, or these 3 gates alongside with the candidate memory, are all neural networks layers. They are normal layers, but with recurrence gating. Here you can see the input, the forget gate. Here we have the input gate, and here we have the candidate memory, and here we have the output gate. These are all normal neural network layers with neurons, but these neurons have the idea of recurrence and getting back, and they are connected together with weights and biases. They have weights and they have biases. For example, the forget gate function, or the equation, is forget gate equals sigmoid function, and then we pass into here the weights multiplied by the previous hidden state, the previous time step, which is ht minus 1 plus the current time step x. Then we add the bias. So this is a normal layer. You can see this is a simple linear operation wrapped with a non-linearity, which is the sigmoid function. Then this is the whole idea of artificial intelligence. We have some sort of linear layer, linear equation, which is W, the weights, the learnable weights, the learned representations, the learned patterns, multiplied by the previous hidden state. So the previous hidden state is also learned. It's also learned and it is studied. And the X, the current time step, is also learned. Then we have an intercept in case that the W's are 0 or these are 0 and they are removed. We have some sort of value, starting value. So the bias, then we wrap this with a sigmoid function or a tangent function depending on the operation. So this is the idea. And we train these networks, the recurrent networks, via the algorithm backpropagation through time. Backpropagation through time is better than the normal backpropagation in the case of RNNs, because they backpropagate through the time and update these weights adaptively through time, allowing for what to forget and what to remember. And here also we have the same idea. Here we have the GRU architecture. You can see we have 2 gates. We have reset gate with sigmoid activation function, and we have also the update gate with sigmoid activation function. And then we produce a new hidden state. Then we overwrite over the previous hidden state. and we have some kind of feedback loops. The hidden state is a compressed version of all the previous tokens or all the previous time steps. So this was the idea of discussing the recurrent networks in short, but now transformers dominate the field of NLP, and transformers take over these architectures, and now these architectures are rare to use compared to transformer-based models. Let's delve into discussing the difference between LSTM and GRU, two important architectures in the world of natural language processing, core equations and explanations. First, we have the model by Hochreiter and Schmid-Huber, 1997, the LSTM, long short-term memory. Here we have the key equations. Let's read each equation. First, we have the forget gate, denoted as F. So F of t. The forget gate equals the sigmoid function, the sigmoid activation function, and then we pass here the weights, the learnable weights, multiplied by the previous hidden state alongside with the current time step, and then plus bias. The bias is the intercept, the starting value, the initial value that will be used in case of this multiplication results in a 0. This is called as the forget gate. So the weights and the biases are the learnable numbers, are the learned representations that will be fine-tuned by the backpropagation through time, algorithm. The sigmoid function, this sigmoid activation function, will output values between 0 and 1, limited between 0 and 1, or bounded between 0 and 1. So it's not considered zero-centered. Then, if you read here, forget gate decides what past memory to erase, decides what past memory to forget, to remove, to get rid of, values close to 0 to get rid of, or keep values close to 1. So if the sigmoid function here, the sigmoid activation function, outputs a value close to 0, it will forget, it will discard. Whereas if it outputs a value close to 1, it will remember, it will keep. Then after this forget gate, we have the input gate. The same idea. We have the sigmoid activation function. Then we wrap here a linear equation, which is the weights, the learnable representations, multiplied by the previous hidden state, comma the x, the current time step plus the bias. The same idea. We have this intercept, which is the starting value in case this multiplication operation gets to 0. And then we wrap this linear equation, linear operation, we wrap it inside nonlinearity, the sigmoid function, which is like this, starting from 0 to 1. Here, the sigmoid outputs value between 0 and 1. Let's read into here. Input gate controls how much of the new candidate information enters memory. So how much of the new candidate information enters and will be written into memory. Why? Remember, we will later multiply the input gate by the candidate information. So the input gate will play around with the candidate and decides how much of the previous info to enter and to be written inside the memory. Then we have the candidate memory, which is this. The candidate memory equals tang. So now we have a new function, tang, hyperbolic tangent, which outputs values limited between -1 and 1. So the tang will be between -1 and 1. So it is considered a smoother gradient or smoother value. Because why? Because it is zero-centered. Tang is zero-centered. We have the same linear equation, the same linear combination. We multiply the weights, the patterns, the learned representations by the previous time steps, by the old time steps, alongside with the current time step, the input, x, and then plus bias. This is called the candidate. The candidate proposed new content. So the candidate is the proposed new content, the suggested new content that will be written into the memory, bounded by tang. Tang outputs values or produces values stored between -1 and 1, limited between -1 and 1. So it's considered zero-centered. Here we have -1, here we have 1, and here we have the 0 value. Then we have the cell state, C of t. The cell state, here we have the function, the forget gate multiplied by the previous time step. So the forget gate multiplied by the previous time step, and then plus we add the input gate multiplied by the candidate memory. Why? Because if I ask you why do we need to multiply the input gate by the candidate memory, because the candidate memory is the new proposed information, the new suggested information, and then we ask the input, hey input, do you want to enter or write this information, this new proposed content into the memory or not? And the input will decide. We'll say okay if it's close to 0 because it's sigmoid. If it's close to 1, it will say okay, write it, go, pass. We need you. And if it's close to 0, we don't need you now. Go ahead, go away. Okay, so this is the cell update. Here you can see cell state long-term memory pipeline. So the cell state preserves the long-term learning, preserves the long-term memory or long-term remembrance, updated additively to preserve gradients. So updated additively to preserve the gradients and to maintain gradients. Then we have, so this is what has enabled LSTM to remember for long-term period, to remember for long time lag, unlike the traditional vanilla RNNs, which forget quickly and easily. Then we have the output gate equals a sigmoid activation function, and then we wrap inside this nonlinearity, inside this nonlinear function, we wrap a linear equation, a linear combination. We have the weights, the learnable representations, the learnable weights, then multiply by the hidden state, comma, the current time step plus the bias. The bias is the intercept or starting value. Here, the output gate is also a sigmoid function. So you can see here, output gate controls how much memory is exposed to the next layer or time step. Controls how much of the past memory is passed to the next layer or time step. So these gates, you can see, regulate the flow of the information or make the flow of the information easier and robust, more robust. Then we have the hidden state. Then hidden state, this is the new hidden state that will be used back and back and back throughout this whole process. So you can see we have HT minus 1, HT minus 1, HT minus 1. These are the previous, the previous time steps. Whereas this is the new hidden state that will be computed to use instead of the previous, and so on and so forth. So this is the recurrence, the idea of recurrence. Then we multiply the output gate by the tanh of the cell state. So we need to take the cell state and wrap it inside the tanh. Then we multiply by the output gate. So here, impact, LSTM's gated memory solves vanishing gradient and captures long dependencies, resulting in essential for translation and language modeling. And since then, LSTM became the default RNN used from that year, 1997. Then we have the gated recurrent unit by Cho et al. 2014. Gated recurrent unit GRU. Here, the equations are simple. We have, instead of 3 gates, we have now 2 gates. Just 2 gates. We have the update gate and the reset gate. The same idea. We have weights, coefficients, multiplied by the previous time steps, by the previous state, and then multiply alongside with the current time step. And here we emit the bias. They emitted the bias in the GRU. So here we have the update gate. Update gate blends old memory with new candidate. 0, keep past. 1, fully update. So if it's close to 0, keep past. Keep the past information. And if it's 1, fully update the memory. So this is the update gate. Weights, learnable weights, multiplied by the previous time step, comma, x. Then we have the reset gate. The reset gate is also using the sigmoid function. And then we have a linear equation. So linear equation wrapped between nonlinearity function. The weights multiplied by the hidden state alongside with the current time step. This is the reset gate. Reset gate decides how much of past state to ignore when forming the candidate. So from its name, reset, how much of the past state, how much of the past info to ignore, to discard, to get rid of when forming the candidate. And then we have candidate. Here, the candidate memory. We have a tanh function. Then we wrap here the linear function. Weights or coefficients multiplied by the reset gate. Why? Because the reset is what? How much of info, how much of past information to ignore. So we multiply this, the reset gate, by the previous hidden state. So the same idea here. Here, you can consider the reset gate is another form of forget gate. So reset, how much of past info to ignore. There, we multiplied the forget gate here by the previous cell state. And the same idea here. They multiplied the reset gate, which is how much of past info to forget or to discard. They multiplied it by the previous hidden state. And then alongside with the current time step or the input. So this is the candidate. And here we have the candidate proposed new hidden state values regulated by tench. Then we have the last hidden state, which is this equation. The new hidden state equals 1 minus z, which is update gate multiplied by the previous hidden state plus the update gate multiplied by the candidate memory. Here, the same idea. They multiplied there the input gate by the candidate memory. And here, the same idea. We multiply the update gate by the candidate memory. And also we add, additively, we add the previous time step multiplied by 1 minus z. Here we have the hidden state directly updated without a separate cell state. So the GRU gets rid of the cell state. It doesn't have a cell state. You can see we do not have here any cell state. So directly updated without a separate cell state, simpler than LSTM. Thus simpler. It has fewer parameters and faster to converge, faster to train. Impact, GRU is computationally cheaper with fewer parameters but strong performance in neural machine transition and speech tasks. So this was the idea of the difference between LSTM and GRU, two main architectures in the world of recurrent neural networks. But as we said, in the world, when they introduced transformer, the transformer took over and dominated the field of NLP and the world of dealing with text and also dealing with time series data.